Good, Good morning, everyone. Welcome to the third final day of our international conference on graph theory and its applications, ICGTA 2024. We are thrilled to have you with us as we continue our exploration of this fascinating field. Let's dive into the exciting sessions we have lined up, and we encourage each of you to share your ideas and connect with one another. Thank you for being here, and let's make this day a memorable one.
We start our day with an online session. Speaker for the session is Dr. Jay Bagga, presenting on the topic Superline Graphs and Line Completion Numbers of Multipartite Graphs. The chair for the session is Professor Madhumangal Pal. Dr. Madhumangal Pal is a distinguished professor, head Department of Applied Mathematics with Oceanology and Computer Programming, Vidyasagar University, Midnapur. Possessing an exemplary academic record, he has received prestigious accolades, including the Computer Division Medal from Institute of Engineers and Bharat Jyoti Award. He has demonstrated exceptional research prowess, guiding more 34 PhD scholars and publishing over 320 articles in esteemed international and national journals. His expertise encompasses algorithmic and fuzzy graph theory, fuzzy matrices, genetic algorithms, and parallel algorithms. As a renowned author, he serves as an editor-in-chief for the Journal of Physical Sciences and Annals of Pure and Applied Mathematics and holds membership in prestigious professional organizations, including the American Mathematical Society. We welcome you, sir, to chair the session.
Good morning, Professor Vagga. It's my pleasure to introduce Professor Vagga. He is currently working as a professor of computer science at Bell State University. He is an eminent professor with over 40 years of experience in research and teaching in a wide varieties of graduate and undergraduate topics in computer security, graph theory, graph algorithms, computational geometry, and many much more. He holds PhD and master's degrees in mathematics from Purdue University and a master's degree in computer science from Bell State University. Professor Vaggai has published 2 books, a book chapter and many research papers. He has presented lectures with US and in many other countries. He has collaborated in research with scholars from many universities and guided many PhD students. He has organized national and international professional conferences. Dr. Vagga has received several honors and awards, including Bell State Summer Commencement Speaker, Outstanding Faculty Awards, Researcher of the Year, etc. So I welcome Professor Vagga to deliver your lecture, and thank you. The floor is yours now.
Thank you, Professor, for that very kind introduction. I would like to start. I hope you can all hear me all right. I would like to start to express my appreciation and thanks to Dr. Sina, head of the Department of Mathematics, the organizers of ICGTA 2024, and also Christ College for extending an invitation to me and asking me to be on the advisory committee. And I'm pleased to do so. So I'm happy that this conference is going well, and I wish the conference great success. So I'm going to talk about superline graphs and line completion numbers of multipartite graphs. This is an area in which I have been working for a very long time, and there are very interesting problems in this area of line graphs and also many generalizations. So I'm in the Department of Computer Science here at Ball State University, which is located in Indiana, USA, and I've been here for a long time. but my interests overlap with graph theory, graph algorithms, and some other mathematical areas too. So that's what makes our work and our profession exciting, because there's so much overlap between theory and applications. Okay, so I think most of you would know what a line graph is, but just to make sure that we are following the right ideas and definitions, I will start with the definition of the line graph. So suppose I have a graph G. The idea of a line graph comes by looking at the edges of G, or the lines of G, as some people would say. And that's why it's called line graph L of G. So the focus of the line graph is we look at the lines of the graph or the edges of the graph. So here is the transformation that's called the line graph transformation. So in the original graph G, suppose you have two edges E and F on the left here, which are adjacent, then we convert these edges E and F to points. So in the line graph transformation, those will be considered the vertices or the points. And 2 points are adjacent if the corresponding edges were also adjacent. And that's what this definition says. So the edges of G become the vertices of L of G, and 2 of those are adjacent if the corresponding edges are adjacent. So from this very simple definition, there is such a rich variety of properties and interesting problems that follows, because now we are converting the graph, the original graph, by looking at its lines and looking at their adjacencies and coming up with new graph. Okay, so here is a quick example for us. So here on the left side, you see a graph G, which has a 3 cycle with edges BCD, a triangle, if you like. And then there's a star here at this point with 3 edges A, B, C. So as you convert this graph to a line graph, you get the graph on the right. And of course, as you can see, the star, which is ABC, has 3 adjacent edges. So therefore, the edges corresponding to A, B, and C also become adjacent. So you get a triangle. So stars go to triangles. More generally, it's a 3-star. More generally, a star of a degree will go to a complete graph, as you can see, because they'll all be adjacent. Now here a triangle BCD goes to this triangle BCD, but in general, complete graphs don't go to complete graphs. But here, of course, B is adjacent to C and D, C is adjacent to B and D, and so on. Notice that A and D are 2 edges which are not adjacent. So therefore, here also, there is no edge between A and D. Those are not adjacent. So this is a simple example. So therefore, the order of the line graph is the size of the graph. What that means is that the number of vertices in the line graph is equal to the number of edges in the original graph. And then in a minute, we'll see how many edges are there in terms of other parameters. So this simple idea, as I said, leads to a lot of interesting. So the theory of line graphs is one of the most extensively studied theory. What is interesting is that this concept also generalizes to digraphs. So also there is a lot of research and rich theory of line digraphs. Now, of course, in digraphs, we have to follow arcs, we have to follow directions. So here the line digraph transformation is similar. So if you have an arc A with this origin and terminus, and then an arc B, so from A to B, we have a 2-path, if you will, a directed 2-path. So then in the line digraph, A and B, the arcs become the vertices, and you get an arc from A to B. So here we have to worry about not just incidence, but also direction. Okay. So line digraphs have a theory of their own, but in this talk, we will not talk about line digraphs, but I wanted to introduce the definition just so that you know that there are line digraph results, quite a few. So recently, Professor Beinecke, who is a well-known name in line graphs and line digraphs, and we wrote a book in this published by Springer. So this is a good introduction and quite a bit of detailed results of line graphs and line digraphs. So if you are interested in this topic, you might want to look in this group. And some of what I'll present today is also in the book, but there is more than that. So one of the first things, one of the most famous theorems in graph theory is called the line graph characterization theorem. Although we won't use it, but I wanted to mention it because that's an important theorem in the theory of line graphs. So how can you tell if a graph is a line graph? Because line graphs have special properties. So in order to do that, I will just cover it briefly. We say that a triangle in a graph is odd if some vertex of G is adjacent to an odd number of vertices of this triangle. Otherwise, that triangle is called even. So this set of equivalent characterizations of a graph are the result of many researchers, and they've been known since the middle part of 1900s, between 1950s and 1970s. These results were shown. And how do we know that a graph is a line graph? Well, it must satisfy one of these three equivalent conditions. And I won't go over the details of these, but just want to mention that one of the most famous characterizations and well-known is what's called the forbidden graph characterization of Beinecke. Beinecke is also my PhD supervisor, so he and I have done a lot of work on this area. So the 9 graphs that are shown on the next slide, this slide, are called the 9 line forbidden graphs. So a graph is a line graph if and only if it doesn't have one of these as an induced subgraph, and that's the last condition here. None of the 9 graphs in the figure is an induced subgraph of G if and only if the graph is a line graph. And the proof is quite interesting and fascinating, and you should be able to find it in the book and other places. We won't talk much about the characterization, but there's also algorithmic characterizations or algorithmic constructions to recognize line graphs, and you can look at that. This is a quick theorem that follows from the definition of line graphs. So if you know the number of vertices in the line graph, which is same as the number of edges in the original graph. So G is a non-empty graph with n vertices and m edges. Then the line graph has m vertices. We already said that. And then it has this many edges. So you take the sum of the square of each degree of the original graph and half of that minus the number. And you can easily prove this as a simple exercise for yourself as to how to find these number of edges. Now the degree of a vertex E, where E is an edge in the original graph, is the degree of its two endpoints minus 2. So you look at a line and look at its connected edges on either adjacent edges. So every edge adds to a degree except that one. So that's why. And now you can also see what the minimum degree and the maximum degree in the line graph look like. So we won't use this result much in the sequel in the remaining part, but we will look at other results similar to this. So I wanted to mention this result, but this is one of the basic results of line graphs. Okay, so line graphs, as I said, have a very rich theory. There are so many properties of line graphs, like cycles in line graph, Hamiltonian properties, colorability, planarity, and many other conditions and properties. But that's not the subject of tonight's presentation. I'm saying tonight, but because right now it is night here. It's around, in US where I am, it's almost midnight. It's 11:45 p.m. So I should say this morning's presentation for you, this is the morning presentation. So we want to discuss some generalizations of line graphs and line diagrams, and I'll mostly stick to line graphs. So one of the generalizations of line graphs is path graphs. So again, recall the definition of a line graph. In the line graph, we take a path of length 1 because an edge is a path of length 1. So Broersma and Huide generalize that to paths of bigger lengths. So the vertices of line graph are paths of length 1. So the path graph is where the vertices are paths of length 2. and two of them are adjacent if they overlap an edge. So instead of taking a single line, you take two adjacent lines or a path of length 2. So here is an example of the path graph. So if you have E, F, and G as edges in a graph, so EF form a path of length 2 and FG also form a path of length 2. So in the path graph, EF and FG are adjacent because this is overlap. But there's also another case that is covered. If EF and G form a triangle, then also we say EF. So either EF and G overlap in an edge or they form a triangle. Now this is only a path graphs for paths of length 2, but clearly this can be generalized to path graphs of fixed length k. So those are called k path graphs, where you take all the paths in a graph of length k, where k is a number greater than 2, and then define the adjacency suitably, similar to this kind of adjacency. Again, we won't go into this definition, we won't need this, but I wanted to mention a generalization. Another generalization that was given by Alavi and others is called the double vertex graph. So the double vertex graph, DVG, where we, instead of taking lines, we take pairs of vertices of G. The pairs of vertices of G are the vertices of the double vertex graph, and two pairs are adjacent if they have one vertex in common and the other two are adjacent. Let me show you an example. So here is the original graph. 1, 2, 3, and 4 are the vertices. Now take all the two sets of vertices, 1, 2, 1, 3, 1, 4, so on, all pairs of vertices. Notice that 1, 2, and 1, 3 are adjacent in the double vertex graph because there's a common vertex 1 and 2 and 3 are adjacent. 2 and 3 are adjacent. Now 1, 2, and 1, 4 are not adjacent because there's a common vertex 1, but 2 and 4 are not adjacent. So both the conditions must be satisfied. So again, there's quite a few of these results, of the results that have been shown for double vertex graphs. That's a good generalization, and there are many others. Now with Beinecke and Verma, we defined another kind of graph, which is a generalization. We call it the double line graph. In fact, that's a special case of what we'll call superline graph here in a minute. But if you follow the terminology of Alavi, then we can call it double line graphs. So in double line graphs, we take the pair of edges as the vertices, and we say two vertices are adjacent if at least one edge in each set is adjacent to one in the other. So here's an example of a double line graph. So on the left, you see this graph G, the original graph G, with edges A, B, C, and D. So the vertices of the double line graph are all pairs of edges. So since there are 4 here, you get 4 choose to 6 pairs of edges. And then you define adjacency between two pairs if at least one edge of one is adjacent to one of the other. So there could be multiple adjacencies. And later on, we generalize this concept to multi-double line graphs too. And so you can look at some of our papers and look at some multi-graphs which also come out of this. But in this definition, we ignore the multiplicity. We just say the two are adjacent. So for example, AB and AC are adjacent because B and C are adjacent, and even A and B are adjacent. So A and B are adjacent from this set, whereas B and so that's why that, and similarly the others. So you can see that we get quite a few edges in the double line graph from this definition, and that will come in handy later, as you'll see. So by looking at the definition of double line graphs, you can immediately deduce some properties. So if S and T are two pairs of edges in G, then they are not adjacent if their intersection is either empty or an isolated edge, because that's kind of the negation of when that condition of adjacency is not satisfied. So there's the intersection is empty, that means they don't have any common edge, so no chance of getting adjacency. But if the intersection is not empty, then it should be an isolated edge in the union because you don't want any adjacencies in the two. So that's the straightforward deduction out of the definition. Now, oops, excuse me. I think I moved to another one here. Let me go back to, can you still see my slides?
We can see, sir.
Yeah, you can see your slides, but I can't. I think it has moved. So let me get those back. Just a minute, please. Okay, there it is. Just a minute.
Yeah. So we are on the slide, some properties of double line graphs.
Yes, I'm going to go to that one. Somehow I'm not seeing my. Okay, there it is. Okay, I'll share again. Okay, are we good? Can you still see the slide? All right. So if neither S nor T is a set of two isolated edges, then the distance between S and T is 1 or 2. And you can easily check this out by looking at the cases. If you take S and T to be two sets, which is not sets of isolated edges, because then there are no adjacencies, then you can show that the distance between these two in the double line graph is 1 or 2. So just take another vertex with one edge from each set that is not in the other set. So that will give us the answer. So that leads to this theorem that if G has at most one isolated edge, then the diameter of the double line graph is 1 or 2. So you saw in that example, we had quite a few edges. So these are graphs with small diameter 1 or 2. And if G has at most one isolated edge, then DLG is path comprehensive. That also can be proved easily. So there's some interesting properties. Path comprehensive means that all pairs of vertices are joined by paths of all lengths between 2, 3, up to n. DLG is vertex pancyclic. That is, it has not just cycle of all lengths, but it has every vertex lies on a cycle of each length from 3 all the way to the maximum. Okay, so that was double line graph, but there remember we just took pairs of edges. But you don't have to stick with pairs. You can go to any fixed number of edges, and that's what leads to the superline graphs, which is the superline graph of index R. So fix a number R between 2 and the number of edges, or even between 1 and the number of edges in the graph. If you just take R to be 1, then you just get the line graph. If you take R to be 2, you get the double line graph. And now you can go to any R. And so take all these subsets of R edges. So since there are M edges, then M choose R is the order of that. And we say that 2 are adjacent if some edge in to some edge in T. And that gives us interesting properties. Now, this is a generalization of the earlier theorem that we did for double line graph. We also get it for superline graphs of a fixed index R, L, R, G. So here is an example which illustrates what happens as you take different indices of superline graphs. So here's the original graph G. Again, we saw this example earlier. If you take R to be 1, L1G, you just take sets of one edge. So it's just a usual line graph. So that says that this is a generalization of line graphs. So superline graph of index 1 is just the usual line graph. Superline graph of length 2 is the one we saw earlier. So here you take pairs of edges and join if the conditions are satisfied. Now you take superline graph of index 3. Since the original graph has 4 edges, you get 4 choose 3 to, so 4 triples, ABC, ABD, so on. And you get actually the complete graph K4 as L3 of G. And finally, if you take L4 of G, you're taking all the edges, you just get a singleton. So you can start from 1 and go all the way up to the number of edges. So you have all the superline graphs of indices 1 through M, where M is the number of edges. So eventually the graph does become complete because it just becomes a singleton. But actually, as you look at these indices, the graph becomes complete much sooner, as we'll see. And that's the interesting topic of when does a graph become complete when you take its superline graphs of larger indices. So that leads to this result or definition of line completion number is what we want to talk about. So suppose you take a graph with p edges, then there's a natural sequence of superline graph L1G, which is same as LG, L2G up to LP of G. And that, of course, we saw as K1. And it's not hard to show that if L sub I of G is complete with I less than B, then so is L sub I plus 1. Of course, if any two subsets with I edges, there's adjacency, then if you take I plus 1 edges subsets, certainly there'll be adjacencies. So once it becomes complete at some stage, then to stay complete throughout. Of course, remember that the number of vertices goes up, this is the combinatorial coefficient, and then down. Eventually, there's a single vertex. So the number of vertices increases about halfway and then goes down. But if it stays, once it is complete, it will stay complete. Therefore, we are interested in the least value L for which Lij is complete. And that value is called the line completion number, which we denote by LC of G. So the line completion number, just to repeat, is the smallest index I at which the superline graph Li of G becomes complete, which means that if you take any two subsets of I edges from the original graph, you'll always find an adjacency. One edge in one set would be adjacent to one edge in another, is what that means. So it really gives you a nice property of subsets of edges of the original graph G. So in this presentation, we'll mostly talk about line completion numbers of some families of graphs. So as I said earlier, eventually the line graph, as you take these not iterated, but the different indices, then it becomes complete. And you can show that if G is a connected graph, then it becomes complete at less than about half M, ceiling of M over 2, where M is the number of edges. So L is the greatest number of edges that each of the two vertex disjoint induced subgraphs. Then that becomes the lower bound, and that's easy to show from the definition. So as we said earlier, we are interested in the line completion numbers of many families of graphs. So once we looked at this concept of line completion number, many people looked at line completion numbers of families of graphs, and these are you can find these in the book I mentioned or in the published literature. Complete graphs, we know what the line completion number is. Paths, we know the line completion number is about half, same as for cycles. Fans and wheels, we know. Windmills, which you can check the definition. I won't define that here. Generalized cubes or hypercubes also have been discussed, and the line completion number of cubes is known. So this is the theorem about hypercubes, which was proved by Tapadia and Wafare some years ago, and it's the proof is in the literature. The line completion number of the d-dimensional hypercube is 1 plus this. And they have an interesting proof that you can look at. Then Kurithira and Sebastian proved the line completion number of grid graphs. So you take grid graphs are graphs which are products of paths, PS cross PT. And so they gave a complete result for that. So recapping this and going back to this, we see that we have many families of graphs that we talked about, including grids and cubes. But one family that we don't see here is bipartite graphs, complete bipartite graphs, KMN. And it's not here covered directly. And there's a reason for that, and you will see that here in a minute. Why bipartite graphs, the line completion number. That problem is actually still open, although many parts of that proof are known, many cases, but the problem is open. So even for a simple graph, KMN or KRS, the line completion number is still open. So what is the line completion number of KRS? So again, you take the complete bipartite graph, KRS, and you are interested in finding out what's that number where if you take any two sets of edges within KRS, then one set and second set, there'll always be an adjacency. And you can start, as you start thinking about it, you can get a feeling for what that number might look like. And for many cases, that number happens to be true, but in general, the proof gets quite hard. So just like I said, to find the line completion number of the complete bipartite graph, you have to split the KRS into two parts in terms of edges. You have to partition the edges so that the number of edges in the smaller part is as large as possible, and then the line completion number is just one more than the minimum. The reason we take the smaller part because you want to make sure that the two sets are non-adjacent, and that will give you the answer. But then you want to make it as large as possible. So it's a max-min kind of result. But actually, this turns out to be a number theory problem, a problem about numbers. So for KRS, the line completion number problem turns out to be an interesting problem for numbers, which is that given two integers R and S, what is the maximum value of min of A, B, C, D, where, and that's why I said max min, the maximum value of A, B, comma, C, D, where A, B, C, and D vary over all partitions of R and S. So that is R is A plus C and S is B plus D, and you want to take the product of A with B and C with D because that's where the complete bipartite graph is. In other words, you are splitting the complete bipartite graph into two parts, one with parts A and B and the other with parts C and D. And then you take A, B, and C, D are the number of edges in each part, and you minimize that and then try to maximize this value. So this is a very simply stated problem, but the proof turns out to be hard in general. And it's open, the general proof. So let's look at an example just to get a feeling for this. For example, if you take 27 and 45, so you have the KRS, R is 27, S is 25. So partition 27 and 45 and define alpha of AC to be the min of ACBD. So for example, if you partition it as 11 and 26, so look at this 11 and 16, those two add up to 27, 26 and 19 add up to 45. And if you take the products, you get 286 as the minimum. So the question is, what is the largest possible value of this where overall the field? So we are just restating the question as a max-min question for integers. And that's why we found this problem fascinating, as is the case in graph theory. Many of the problems about properties of graphs turn out to be problems which can be stated in terms of numbers. So there are cases of R and S, and the cases depend on the parity of R and S. If R and S are given two numbers, then you would think that the reasonable thing to do would be to divide the parts into roughly equal parts to maximize this. And that is true in general, but the exact values are hard. So you take P to be about half of R, the floor, and Q to be the floor, S over 2. So if R is 2P or 2P plus 1, S is 2Q or 2Q plus 1, depending on the parity. So we look at 4 possible cases, assuming R is less than or equal to S. So both are even, and we call that the base case, if both R and S are even. Smaller is odd and the bigger is odd. 2, both are odd. Then smaller is even, the bigger is odd, or the smaller is odd and the bigger is even. And remember, we are assuming R less than or equal to S, so those two will be the different cases. So those are the 4 cases depending on the parity. So we say that the pair AB is optimal if that achieves the value that we are interested in. And the base case is where you take R to be 2P and S to be 2Q, then it's PQ. If you take R to be 2P plus 1 and S to be 2Q plus 1, it's P and Q plus 1 because that gives you a better value, and so on. So in each case, we define roughly half to be the base case. So here is a table of results that if R and S are both even, the base case is the answer. If R and S are both odd, then the base case never holds if S is greater than 2R plus 3. Not only it depends on the parity of R and S, the results also depend on the difference, how far apart R and S are. So if S gets larger than 2R plus 3, we can show that the base case does not hold. So we have some specific answers, but we don't have the general case. On the other hand, if R is even in the third case and S is odd, the base case will always hold beyond some critical value, which we have to figure out yet. And finally, in the odd even case, the base case holds only in one case when S is R plus 1. So it almost never holds, only holds when S is R plus 1, unlike this. So there is a lot of variety in these results, and that's what makes the problem interesting. So we have these theorems which were published some time ago. The line completion number LCKRS of the complete bipartite graph. If R is even and S is also even, then it's just the base case. There will be half R times half S, and then you have to add 1 to get the line completion number, because at that point they'll have the adjacency. If S is odd, R is even and S is odd, then we have these values in case R is congruent to 0 or R is congruent to. So you can see we have partial results. And if R is odd and S is even, then we have this value for S greater than or equal to R plus 3. And if S is also odd, then we have this result for all S greater than 2R plus 3. So there are interesting sub cases that we have. But so I invite you to take a look at this problem. It's an interesting open problem in general at the bipartite case. So now we have also looked at when is LCKRS numerically close to the base case, but it's not. When R is odd and S is even. So what we've done is we wrote some computer programs to check a lot of these results empirically. And with those computer programs and the data that we have, and we have lots of data, it shows that the difference between the actual value of LC of KRS and the base case can be arbitrarily large, so it can change quite a bit. For example, when R is 11 and S is 1000, we saw, and we found this example in our data, the base case is 2501 by taking that. But the actual value of the line completion number is 2720. So quite a bit of difference in this case, but we can make it arbitrarily large also. So that's where the status of the problem is when this was published. And some other people have looked at it, but the general problem is still open. And I invite you, if you are interested, and we can work on the general case. So now, of course, the next generalization, obviously, is to go to higher partite sets. So I see that it's about 9:50 a.m., Professor. So I have about 10 more minutes. Is that right? Or should we stop at some point?
Sir, you can continue, sir. No problem.
All right, great. So I have a few more slides to talk about. Great. So now let's look at complete tripartite graphs. So even though there is much left undone on the problem of line completion number of complete bipartite graphs, there are interesting facts about the corresponding problem for tripartite graphs. And as you can imagine, the problem gets harder as you increase the number of partite sets. So again, as with complete bipartite graphs, every new subgraph of a complete tripartite graph is also a complete tripartite graph, allowing for some degenerate cases. Therefore, you are again looking at it as a number theory problem. So for example, look at K3, 4, 5. So there are 4 plus 3, 7 plus 5, 12 vertices and 47 edges, 12 and so on you can find. So its beta value it turns out to be 11, and the number of edges in K1 to 3 with its counterpart K to 2 being 12. So there the answer is 11. So this, you can see that as an example of splitting complete tripartite graphs into. So here's the complete tripartite graph 3, 4, 5, and I split it into red and blue edges, those two sets, and you can see that there's no adjacency between any blue edge and any red edge. So that gives you an example. So again, similar to the number theory problem, we are looking at three partite sets, and we have to split each set into two parts and look at the complete tripartite graph on one side versus the complete tripartite on the other side, and try to take the minimum and then maximize it over all partitions. So we define this number beta, which is beta of RST. So take the minimum of AB plus AC plus BC and A prime, B prime, A prime, C prime, B, where you have those partitions. And after taking the minimum, you vary over all partitions and take the maximum over all partitions. And that's the value beta RST. And the line completion number will be one more than that, because at that point there'll be adjacencies. So here we saw earlier 4 cases in the bipartite case. Here we see 8 types of cases. Assuming R is less than equal to S less than equal to T, there are various parities and combinations of those cases. I won't go over the details. And the numerical values are given here of these cases. So you can see that we looked at some special cases in case the partite sets are equal. 2 are even about equal, and the third is one more, or the 2 are 1 and then 2 more than the smallest, and so on. Number of special cases that we found. So we made a number of conjectures and we proved some of these. And again, in order to respect the time, which I'll try to finish in another few minutes, I will mention these conjectures. There are several open problems here about these special cases. So out of these conjectures that we made, and we thought that we had some answers, we've been able to prove some of those. For example, the case when the parities, the partite sets are all even. They don't have to be equal. So I have 2A elements in the first partite set, 2B in the second, vertices 2C in the third. Then it's as expected, you split them right in the middle. So you take A and A, and B and B, and so you get the pairs of products AB, AC, and BC. And that turns out to be beta. So the line completion number is one more than that. Similarly, if you take 2K plus 1, hang on, I just lost my window again. So I'll have to go back. I'm not sure why it does that. Okay, there it is. I can see. And so just to show you some illustration, I'm going to try to quickly show you a proof of this first theorem here. So for A, B, and C, A less than equal to, we want to prove that beta of 2A, 2B, 2C is as we expect. And we work on this proof by contradiction. Assume that this is not the optimal value. That means some other partition will have to achieve the optimal value. So therefore, we look at a general partition. That is, instead of A and A, we take A minus X and A plus X. Instead of B and B, we take B minus Y, B plus Y, and similarly C plus C. Of course, you have to take some more. If you take all negatives, then of course, that number is smaller. So that partition minus minus plus 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 minus denotes this particular. Now, you don't want the partition where you decrease all three, because if you decrease all three from A, B, and C, then the number will be smaller. So clearly, you don't want that. So there are three possible cases to consider for these partitions, which we denote. And then we look at each one of those. The proofs are similar. And we assume that the optimal is not there for A, B, A, C. And we get these lots of inequalities that you have to algebraically deal with. And I will skip the details. And then eventually it leads to a contradiction. Now, this contradiction was easier to obtain in the bipartite case. In the tripartite case, it gets a little more messy. And now, of course, we can go to the n-partite case. And there also we think this is true, but that proof is still open. But we made a conjecture. So I'll skip over these. So I'll go to the complete n-partite graphs. So it'll be interesting to extend these results even to n-partite graphs. So we conjecture that the results for 2A, 2B, 2C, partite, tripartite, and 2K plus 1, all odd equal, will also hold in the general case. And the proof will look like a generalization of the proof that I indicated to you. Will get much more messier. And so that's something we would like to see happen. So that's the conjecture that I would like to stop with. And thank you very much.
Thank you very much, Professor Vagga, for your nice informative lecture. So, any question from audience? Yes.
Hi, sir.
Yes.
Is there any two non-isomorphic graphs which gives the same line graph?
Of course, if you take the K13 and the K3, then the line graph is triangle. So there's an interesting result about when the graph, so in our book you can find that. So that result is already known, yes. But a simple example is take K13 and K3. Those are not isomorphic, but their line graphs are both K3s, so they are isomorphic. But there are very few examples like that.
Is there an example like both the graph and the line graphs are say isomorphic?
Yes, there are many examples. So these are some interesting questions. For example, a cycle. Line graph of a cycle is a cycle.
Other than cycles?
There are some results. Those have been completely characterized. All the graphs, and I'll refer to our book to find that. Yeah, so there's some other possibilities, but not many. Cycles are mainly the ones. Then if you look at disconnected graphs, you get some. So, yeah.
Thank
you. Great. Hopefully that answers your question.
Sir, thank you for this interesting talk. So, sir, my first question is, are these double line graphs always simple and connected?
The way we define these graphs, they are simple, yes. But we can also, as I may have mentioned in one of the remarks, you can also look at the multiple variation. So you can define multiple. So for example, if you take two pairs, and there may be more than one adjacency between the pairs. So ABA and AC, for example, or AB and CD. And if you have multiple adjacencies, then you will draw multiple lines between those two vertices. And there are some interesting results about multi-line graphs, multi-superline graphs too. There was a paper that appeared in Discrete Math some time ago. You can look for that paper, and there's some interesting questions about there. But that area of multi-superline graphs is largely unexplored. So there's some interesting questions there. Yes, so the answer is yes, there are multi-graphs there.
Oh, okay.
Depends on how you define the adjacency.
So, sir, is there any relation between double vertex and double line graphs?
Double vertex graph and double line graphs are not directly related because in one case you are taking vertices in the other lines, but their properties are similar. The definitions are quite different, but they have similar properties about cycles and about other properties which you can find.
Okay, thank you, sir.
You are very welcome. So another interesting problem is there is the double vertex graph and the double line graph. And now the double line graph we generalize to superline graph. So it'll be interesting to see if the double vertex graph can also be generalized to super vertex or some similar definition. Instead of taking only two, what if you take more? But the definition will have to be changed suitably. And I'm not aware if somebody has looked at it. Perhaps there's some interesting questions there.
So any more question?
Sir, is there any study done on click transversal number of line graphs?
I'm not aware offhand. I don't know. That's something I'll have to look into, transversal numbers. So you might want to check the literature. I don't know if there is offhand. I have not seen any, but that doesn't mean there isn't.
Okay, sir.
So thanks for your nice lecture. The concept is interesting. Is there any real-time application, sir?
The applications of line graphs is just like that of graphs. There are many areas in which the connections are based on lines rather than on vertices. So I've seen some applications of line graphs that you can look at in terms of signed graphs. There are some applications. In our book, we talk about those applications also and some others.
Okay, sir. Thank you, sir.
Any question? So thank you, Professor Bhagga, for your informative talk. And there are lot of conjecture are there in this related to your lecture. So this is these are the open problem for the those who are interested to work on graph. So thank you very much, sir.
Yes, and I'm happy to discuss with anyone who is interested to work in this area of superline graphs and also line graphs. And please feel free, Dr. Sina, to share my email with participants.
Thank you so much, sir, for being with us in online mode. We expect your
Thank you for
presence
having me.
in
Yeah,
our
I
next
enjoyed.
conference.
Yes. Good luck with the rest of the conference, the last day, and my best wishes to you all.
Thank you so much, sir. Kindly accept our virtual memento, sir.
Thank you very much. It looks great. I'm happy to accept the virtual. Looks nice. Thank you.
This is designed by our students, sir.
Oh, this is excellent. Very good. So I see. I can't see it very well. Maybe we can zoom in.
Yeah, I
but
will
it looks-
share the soft copy, sir.
Yes, that's good. If you share anyway. So please thank all the talented students who helped make this, and I'm very pleased to see it, and I appreciate it. greatly. Thank you.
Okay. Thank you, sir. Thank you so much.
All right, all of you have a nice day, and I'm going to have a, this is after midnight, so it's time for me to say good night too.
Good night,
Thank
sir.
you. All right.
Okay, sir. Okay.
Bye-bye.
Bye.
Thank you, sir, and thank you, Cinemas.
Next, we move on to the second session of the day. The speaker for this session is Professor Madhumangal Pal, and the chair for the session is Professor Ayman Baravi. I kindly invite you, sir, to chair the session.
Mention the Computer Division Medal from the Institute of Engineers in 1996, and the other one is Bharat Jyoti Award. Is that close, the name? Am I right? Or you can correct me. 2013. He has exceptional research record guiding 34 PhD students and over 320 articles. And he worked in many different areas like algorithm, fuzzy graph theory. Well, the fuzzy person is not here with us today. You remember the story yesterday. So I think he will be happy to meet you. He was not happy about the fuzzy graph. Anyway, and he is has about 8 textbooks and edited 2 books, and he is the editor-in-chief for the Journal of Physical Science and Annal of Pure and Applied Mathematics. And he has many memberships. One of them is a member of the American Mathematical Society. Welcome, Professor Pal.
Hello.
Yes.
That's fine. So, good morning, everybody. So, first of all, I am very grateful to the organizer of this college, and particularly Dr. Sina for inviting me, and also thankful to the chairman. And just now I'll discuss regarding topological indices of fuzzy graphs and their applications. So there are 2 things, major things. One is the topological indices or topological index of graph. and another one is the fuzzy graph. Okay, so this is the combination of two things. So topological index is defined in 1947. This is the very old concept of graph theory. And topological indexes on fuzzy graph theory, that concept is new. That one, as far as my knowledge, that one is started in 2017 or 18 like that. So outline of my talk is molecular graphs, topological indices on the conventional graphs or Krebs graphs, topological indices on fuzzy graphs, and applications, and then references. Okay. So now I start with your chemical graphs. That means chemical graph means a graph coming from chemistry or the chemical compounds basically, particularly the carbon compounds, and in more particularly we can say this is coming from the alkanes. Alkanes is a particular type of carbon compound. So from that your carbon compound are alkanes or paraffins. Alkanes and or paraffins are the same thing. This is the terms coming from the chemistry. So from the chemical compound, a graph is defined, and that graph is called the chemical graphs or your molecular graphs like that. So I think we remember regarding the few terms of chemistry, atoms, molecules like that. No, the carbon is atom, hydrogen is another atom, but your methane is a molecule, water is another molecule like that. So combination of atoms forms a molecule. So see that here your hydrogen, oxygen, magnesium, these are the atoms, and H2O, H2O, there are two H and one oxygen atom. So this is a your representation, graphical representation of your water. No, H2O is the chemical formula for water. So this is the water molecules. That means in chemical graph theory, the atoms are considered as vertices, and there is a bond between, bond means single bond, double bond, triple bonds. No, these are the terms coming from chemistry. So if there is a connection between the two atoms, then we draw an edge between the particular atoms. Okay. So this is an example of your C10H22. This is a particular paraffin. I am coming from that after in the next slide. So this is the chemical formula or chemical representation. This is the chemical formula, and this is the diagrammatic representation. So this diagram is already studied in class 12, no, 11 or 12 class in the subject of chemistry. So this is the related to chemistry basically. So see that in this diagram some carbon atoms are there. How many carbon atoms are there? 10, because the chemical formula is C10H22. So in this diagram there are 10 carbon atoms and 22 hydrogen atoms. And see that each carbon atom has 4 edges. The lines means edges, and it is nothing but the valence or bond between the carbon atom and hydrogen atom. And the valence of each hydrogen atom is 1. So see that each hydrogen atom has only one edge. No, only one edge, and each carbon atom has 4 edges because the carbon atoms has bond 4. Sorry, valence 4. So after removing all hydrogen atoms and associated edges, the reduced structure is this one. Only carbon atoms are present in this diagram. So this is called the chemical graph corresponding to the paraffins or alkanes. Okay. So this is called the chemical graphs or your molecular graphs like that. After removing the hydrogen atoms, the reduced graph is called the your chemical graphs or molecular graphs or constitutional graphs. Now see that the molecular graphs of acyclic compounds are trees. Trees is subclass of graph, you know, everybody know. So the acyclic compounds are trees in the molecular graphs. So for example, the alkanes, the general formula for alkanes is CnHm. M is basically, this is nothing but 2n plus 2. So CnHm, if you consider alkanes like this one, CnHm, it has no circuit and no multiple bonds. Okay, so there is a single bonds between carbon and hydrogen and carbon-carbon. So all these bonds are a single bond. There is no double bonds or triple bonds like that. So no circuit and no multiple bonds for all alkanes for any values of n. Okay. And number of vertices of this kind of graph is n, because total number of carbon is n and total number of hydrogen is m. So number of vertices is n plus m. And n number of vertices with degree 4, because carbon has 4 degrees or 4 valence. So the degree of each carbon atom is 4. And hydrogen atom, there are n number of hydrogen atoms, so number of vertices with degree 1. Okay, m number of vertices with degree 1. So total number of edges of this kind of graph is 4n. 4n means 4 into n and m into 1. So 4n plus m by 2. Okay, so one edge is counting 2 times, so entire expression is divided by 2. And this formula represents alkanes if and only if n equal to twice n plus 2. That means the general formula for alkane is CnH2n plus 2. Okay. For different values of n, we have different alkanes. For n equal to 1, the formula is CH4. This is known as methane, the very popular gas, methane. When n equal to 2, it is nothing but your C2H6. This is known as your ethane. There are 2 carbon atoms and other your 6 hydrogen atoms. And for n equal to 3, this is nothing but propane. For n equal to 4, there is butane and many other alkanes. So this is a sequence of alkanes. And the leftmost diagram represents the actual your microscopic representation, microscopic molecules in a particular type of alkane. And this is the 3-dimensional graphical representation. Each circle or sphere, small sphere, represent a vertex or a particular atoms, and the bonds between the atoms represents the edges. Okay, so this is the 3-dimensional. We can say this is the 3-dimensional representation of this your chemical compound. And this is the plane representation, 2-dimensional representation. And in this diagram, there are some hydrogen atoms. So empty circle represents the hydrogen atoms. After removing the hydrogen atoms, we obtain this, the fourth graph, and this is the final your hydrogen suppressed graph. Okay. So this is the transition from the chemical compound to the our ordinary graph. Next, we are coming in the topological indices. So what is the topological indices? It is nothing but a graph parameter. Simply a mathematical formula. So see that the interesting thing is that a topological graph index, or simply topological index, also this is known as molecular descriptor. Not only a mathematical terms of formula, it actually describes some chemical or physiochemical property of a chemical compound. So that's why it is an important index, and this is known. This is called your molecular descriptor. It is a mathematical formula that can be applied to any graph which models some molecular structure. Okay. From this index, it is possible to analyze mathematical values and further investigate some physiochemical properties of a molecule. So this is the very interesting things. From a graph, from a chemical compound, we can draw a graph, and for that particular graph, we can determine the topological index. Topological index means structural index. The structural form is there for every chemical compound. So topology means structure basically. So for that particular type of graph, we can calculate a mathematical value, a graph parameter, and from that topological index, we can analyze the some specific properties of particular type of chemical compound. So this is the interesting thing, or we can say this is the application of topological index. So lot of topological indices are available or defined by the famous graph theoretician, the Wiener index, SI index, hyper Wiener index. These are the several standard or old your topological indices. And you can also define new type of topological indices. There is a very wide scope to work on this area. So see that the Wiener index, basically Wiener index is the your commonly considered or most classical or widely used distance-based index in chemical graph theory, and this is the oldest one or the first topological index is the winner index. Basically, see that the winner is a chemist, not your graph theoretician or mathematician. Is a chemist, and he defined in 1947 distance-based winner index. That one is denoted by W of G equal to half of summation over distance of EV. Distance means the distance between two vertices. Means minimum number of edges between two vertices U and V. So that one is called the distance between the vertices. It is the well-known terminology of graph theory. So this is nothing but the sum of all pairs of distance, shortest distance. Distance means obviously shortest distance. This is the sum of all pair of vertices, and that one is divided by 2 because the distance U and V and U are coming twice. No, same distance is coming twice. So entire sum of all pairs distance is divided by 2. So this is distance based topological index. Okay, so what is the advantage or use of this topological index? So in 1947, see that in 1947 we now defined this topological index, and it is developed to determine the boiling point of paraffins. Okay, so this is the application of winner index. That mathematical formula or the parameter connecting to a graph that actually determines the boiling point. Okay, without your actual experiment, you can determine the boiling point. But this is not the direct formula. There is a regression equation that one is not with me. This particular slide is not available with me. But there is a regression equation between your topological index and the boiling point of the paraffins. Okay. So using a particular regression equation, we can determine the boiling point without actual experiment. We can determine the boiling point of all paraffins. Okay. So this is the application, and this paper is published in Journal of American Chemical Society in 1947. Okay. Now I am coming in my main topics, the topological indexes of fuzzy graph. Okay. So fuzzy graph is the extension of graph theory. You know, the graph theory is a very well-known subject, but fuzzy graph is not very old one. The graph theory is initiated in 1975. Okay. So see that the fuzzy graph theory is initiated in 1975. Fuzzy graph theory is basically coming when the vertices and edges are uncertain. If the vertices and edges are certain, there is no doubt among their existence in a graph structure, then the graph is our conventional graph, or in contrast of fuzzy graph, that graph is referred as Krebs graphs. Okay, the conventional graph. And when the vertices and edges or one of them is uncertain, then the fuzzy graph is the interesting thing or gives the new results. Okay. For example, our social networks, the WhatsApp, Facebook. No, we are using Facebook and WhatsApp and many other social networks. So in WhatsApp or Facebook, every individual or a particular organization may be considered as the vertices of a graph. Okay, a particular individual or organization or group a group of a WhatsApp may be considered as a vertex. And if there is an interaction between two groups or two individuals, then we can consider there is an edge between them. Okay, and see that. So the lot of people have WhatsApp your accounts. No, almost all young young people have the WhatsApp your accounts. No? So see that what happened in the WhatsApp group. So somebody created a WhatsApp account in his mobile phone. No, just install the WhatsApp app, and he or she never use that apps, but he has a WhatsApp facility. So this is a kind of people present in the WhatsApp network. Some people are just using WhatsApp, to send the New Year's message. So happy New Year message are sending just yearly one time he or she is using the WhatsApp to send the New Year's your greetings. Okay. Some people every day using the every day, or we can say 6 or 7 hours or more than that times spending in WhatsApp, no, communicating with other friends. So depending on the depending on the interaction between the friends, between two friends in the WhatsApp or between two friends in the your Facebook, so depending on the amount of interaction, depending on the amount of interaction, we can assign some number. That number is called the degree of interaction or degree of presence in the WhatsApp network or Facebook network. So in this context, we can define, so degree of interaction, that may be say 100%, degree of interaction may be 0, degree of interaction may be say 50% like this. So depending on the interaction, we can consider a new type of graph. That graph is known as the fuzzy graph. So see that the in mathematical form notation, the fuzzy graph is defined by this symbol V, sigma and mu. In conventional graph theory, there are two sets. One is set of vertices, another is set of edges. But in fuzzy graph theory, we consider the set of vertices. That one is denoted by V, like the conventional graph. And there are two associated function, mathematical function. One is sigma associated with each vertex, and another function mu is associated to each edges. Okay. So sigma represents the degree of membership value or degree of occurrence in the entire fuzzy graph. It may be in the WhatsApp, Facebook, or any other kind of fuzzy graph. So this represents, sigma represents the degree of membership value. So sigma is a mapping from V to the unit interval 0, 1. The membership value represents between 0 and 1, not in 0 to 100, not in a percentage scale. It is between 0 and 1. And mu, basically see that mu is a function of V cross V to 0, 1. So any subset of V cross V may constitute the set of edges of a graph. No. So V cross V, mu is a function from V cross V to unit interval 0, 1. And this function mu of xy is less than or equal to minimum among the degree of membership values of the n vertices. Sigma x and sigma y are the membership value of the vertices x and y. So x and y are the n vertices of the edge xy, and mu xy is the membership value. That means the membership value of an edge is less than or equal to minimum among the membership value of the n vertices. Okay, so this condition should be satisfied for the fuzzy graph. But if we remove this condition, this restriction, then the graph is called the generalized fuzzy graph. Okay. So this is the condition imposed for the fuzzy graph. So see that the new thing is that the set of vertices are there and two functions are associated with a fuzzy graph that represents the degree of membership value of vertices and degree of membership value of edges. So these are the new concept for the fuzzy graph. Okay. And this is an example of fuzzy graph. So structurally fuzzy graphs and your Krebs graphs look like same. There is no difference. It has some vertices, it has some edges. So new thing is that every vertices and every edges are connected with some numbers. That numbers lies between 0 and 1, and that numbers are known as degree of membership value of the vertices and edges. Okay. So the number associated to the vertices are the degree of membership values, and the number associated with edges are the degree of membership value of the edges. So these are the new concept in the fuzzy graph. And like a different definition associated in any particular graph, here also new definitions are available for fuzzy graph. Strength of a path. This is not available for our conventional graph, the strength of a path. But for fuzzy graph, this parameter is defined, strength of a path. That means path means sequence of vertices and edges. No, everybody knows about the definition of path in a Krebs graph. So x0, x1, xn is a sequence of vertices already mentioned here. So see that what is the strength of that particular path. See that that one is denoted by SP, and this is the notation to find out the minimum. Minimum among the membership value of the edges in the path. Okay, so minimum among the membership value of the edges present in the path is called the strength of the path. Okay, that means the minimum. If the membership value is less, then that edge is weak. If the membership value is more, then that edge is strong. And the highest membership value is 1 and lowest membership value is 0. If the membership values of all vertices and edges are 1, then the fuzzy graph is nothing but the Krebs graph or conventional graph. If all the vertices and edges are certain, that means membership values are 1. So it is the generalization, basically the fuzzy graph is the generalization of our conventional graph. So this is one definition. Another is the connectivity between the vertices x and y. Connectivity means that this is the notation to find the maximum among the strength of all possible paths. So between any two vertices there are multiple paths, no? So among the multiple paths we are determining the maximum strength of the path. So maximum strength of the paths between the vertices x and y is called the connectivity. Connectivity between the vertices x and y in the graph G. And geodesic is another terminology similar to the distance between the vertices. So see that for a fuzzy graph, geodesic between the two vertices x and y is the shortest strong path between x and y. Shortest strong path, and that one is denoted by dsxy. Okay, shortest strong path. And the degree of a fuzzy graph, degree means in the conventional graph, degree means the number of adjacent edges. No, here the degree means the sum of the your membership value of the adjacent edges. Okay, sum of the membership value of the adjacent edge is called the degree of the vertex. That one is slightly modified, the degree of vertex. And see that the winner index in the Krebs graph. I have already mentioned this formula. I have shown this formula. The winner index for the Krebs graph is this one, half of summation between the all pair shortest distance between the vertices x and 1. But for the fuzzy graph, the winner index for the fuzzy graph is denoted by WIG, and this is equal to half of summation of us sigma u into sigma v into geodesic between u and v. So that distance is replaced by geodesic, okay, and the two terms are multiplied, sigma u and sigma v. Sigma u is the membership value of the vertex u and sigma v is the membership value of the vertex v. So this is the fudgification of the winner index. So this is the winner index for Krebs graph and this is the winner index for the fuzzy graph. So basically this is nothing but the fudgification, okay. The formula is available for Krebs graph and that one is fudgified for the fuzzy graph, and this is the your slightly change in the winner index. So these topics basically is a fuzzy winner index, fuzzy topological indices for fuzzy graph is started. I forget actual year, but it is not very old topics. It is started in 2017 or 18. So Sunil Mathus is there in NIT Calicut. He delivered a lecture yesterday, no? So he and his another co-researchers, they have started working on this area, okay. And nowadays a lot of people are working in this area throughout the countries. During last 3 years, I have review or edited at least 40 papers on this area, topological indices for fuzzy graph or topological indices for the Krebs graph. So recently, lot of people from different countries are working on this particular topics. So for this fuzzy graph, this is a triangle with some your membership values 0.1, 0.1, etc. And for this graph, we have calculated the this is the connectivity index. Okay, sorry, winner index. Winner index for this graph is 0.3. And this is another formula, another very important topological index, Randic index. So see that Randic index of a graph equal to your degree of u into degree of v whole to the power minus half. Power is minus half. So this is the degree based topological index. Du and dv represents the degree of the vertices u and v. So it is called the degree based topological index, and that one is defined in 1975. Okay. And the generalized formula of this Randic index is that the generalized Randic index is R alpha G equal to du dv whole to the power alpha. If alpha equal to minus half, then this is the conventional Randick's index. If alpha equal to 1, then there is one particular type of your topological index. If alpha equal to 2, there is another formula. If alpha equal to 3, then there is another formula. If alpha equal to say plus half, then you have another topological index. So for different values of alpha, you can define different topological indices. So this is the very interesting things. No, for different values of alpha, we get the different topological index. So this is called the generalized topological index, and good correlation ability for many physical and biochemical properties are available, or we can investigate many physical and chemical properties using Randick's index. Okay. So fudgification of Randick's index, fudgification of Randick's index is this one. du and dv's are already present in the formula, and the degree of membership value of the vertex u and v are multiplied with the formula. Okay, so this is the fudgification of Randick's index. So very simple fudgification technique, no? And this is the generalized fuzzy Randick's index, sigma u into sigma v into du dv whole to the power half. Okay. And based on the connectivity index, connectivity between the vertices x and y, so a connectivity index is defined. This is not defined for the Krebs graph. Connectivity index is defined only for the fuzzy graph, because connectivity parameter is defined only for the fuzzy graph, because it is the maximum among the strength of the possible paths. So connectivity index only defined for the fuzzy graphs, and that one is published in 2019. That one is you are defined Benu, Mathews and Madhurson. Okay. So see that the definition is simply fuzzified definition is sigma u sigma v and into the connectivity between the u and v, and u and v are any two vertices in the graph. Okay, so this is called the connectivity index. And the average connectivity index is this expression is divided by NC2. What is the total number of edges in a simple graph? NC2, no, different number of edges is NC2 for the undirected graph. So that so this expression is divided by NC2. This is nothing but NC2. So this is called the average connectivity index. And there is another type of your topological index for your Krebs graph as well as for fuzzy graph, first Zagreb index. So see that the first Zagreb index is DGV, degree of V power 2. Okay, degree of V power 2. So this is called the first Zagreb index. There is second Zagreb index. I am coming in the next slide. What is the second Zagreb index? So first Zagreb index for fuzzy graph is this one, sigma V into degree of V. Degree of V means the degree in fuzzy sense. Here the degree of V means the degree of vertex in Krebs sense. Okay, here degree in fuzzy sense, and that terms is multiplied by the corresponding membership value of the vertex V. Okay, so this is the fuzzification. So this is not a straightforward your fuzzification. Here the degree is the Krebs sense, here the degree is the fuzzy sense. That one is different. Okay, degree in fuzzy sense, and that one is multiplied the membership value of the vertex V. And this is the second Zagreb index, degree of U into degree of V in the Krebs sense. And see this in the Randick's index. What is the formula in the Randick's index? In generalized Randick's index, see that this one, no. If alpha equal to 1, then see that that formula is nothing but your second Zagreb index. If power is 1, alpha equal to 1, then that formula is nothing but your second Zagreb index, and its fuzzified formula is this one, sigma u into sigma v into degree of u and v in fuzzy sense. Okay, and this is a fuzzy graph. Its first Zagreb index is this one. It is calculated. It is the routine calculation. There is nothing any complicated things. Now this is my students' work basically. First Zagreb index on fuzzy graph. We have defined the first Zagreb index for fuzzy graph, basically extended form of the first Zagreb index in Krebs graph. So for fuzzy graph with n vertices and m edges, we have shown that the upper bound of first Jacobi index for fuzzy graph is 4n square into m square. This is the one of the upper bound. Another upper bound also we have proved. And see that if H is a fuzzy subgraph of the graph G, fuzzy subgraph is similar to your conventional graph. That means a part of the graph is the subgraph, no. And the one condition is that the membership value of each vertex and edges should be less than or equal to the membership value of the vertices and edges in the corresponding your super graph, okay, or original graph. So this is the your definition of subgraph. So for if H is a partial your H is a partial fuzzy subgraph and G is the original fuzzy graph, then see that the first Jacobi index of H is less than or equal to first Jacobi index of the graph G. Obviously, see that in the definition, no, this is the sum of the degrees. Sum of the degrees. If the number of degrees is more, then obviously the first Jacobi index will be more. If the graph is less, then the values, the expression of the summation expression gives the less value. So it is obvious your theories. It is not very difficult to prove. And for the path, the upper bound of first Jacobi index is 2 into 2n minus 3. For path, the formula is this one. For cycle, the upper bound is 4n. For your star, upper bound is n into n minus 1. For your complete graph, it is n into n minus 1 power 2. And these are the results regarding your graph composition, or different type of graph composition are there. For different graph composition, we have also defined or determined the different your Jacobi index. And this is the upper bound as well as lower bound of the first Jacobi index for fuzzy graph. See that this is the new, by another, we can say another upper bound n into delta square. Delta square means the maximum among the degrees. Maximum among the degrees is the capital delta, and small delta is also here. So small delta represents the minimum among the degrees. Degree means the fuzzy cells. Degree is fuzzy cells. So the first Jacobi index is bounded. Obviously, it is bounded for finite graph, and upper bound upper bound is this one, and lower bound is this one. And if G1 and G2 are two fuzzy graphs, and this is the Cartesian product between the fuzzy graphs. So Cartesian product is well known your graph operation for the Krebs graph. No, it is available in any graph book on the graph theory. But there are little bit changes or new things is present in the Cartesian product of the fuzzy graphs. So in fuzzy graph, the new thing is that what are the membership values of the vertices and what are the membership value of the edges. So that should be defined. Okay. And another things are similar to the Krebs graph. New thing is you have to give some concentration regarding the membership value of the vertices and edges. And this is the another upper bound. This is the other results. Okay. Now another type of your topological index for fuzzy graph, that one is known as F index. F index for fuzzy graph is sigma u v into sigma dv power 3. If alpha equal to 3, basically if alpha equal to 3 in the generalized Randex index, then we can define another topological index for fuzzy graph. That one is known as F index. Okay. And it has several bounds like your previous one. So these are the bounds for the F index of different type of fuzzy graph. Similar bounds. And now we define another type of your topological index, hyper winner index. Winner index we have already mentioned, distance means topological index. And in here we hyper winner index, you see that here. So this is the geodesic between A and B plus geodesic between A and B and its square. No, in winner index, this term also only Only sigma A into sigma B into geodesic between A and B was there. No, only the first term is present in only Wiener index, but in hyper Wiener index this term is additionally included. Okay, the square of the geodesic. So here that formula is changed. This one also your distance based Wiener distance based topological index, the previous Randic index and its variations are your degree based, but this one is the distance based. Particularly for fuzzy graph, this is your geodesic based topological index. And this is some lower. This is the lower bound. Your T is the minimum among the membership value of all the edges, strong edges basically, and this is the lower bound for the fuzzy hyperwiener index. And this is the, if two graphs are isomorphic in fuzzy sense, then their hyper topological index, hyperwiener index are same for isomorphic graph. For path, the upper bound is this one, a very big expression. For stud, this expression up into n minus 1 into n minus 4. And for connectivity index, hyper connectivity index, the previous one was the hyper Wiener index, similar to the your Wiener index, but for hyper connectivity index, the geodesic is replaced by connectivity. In the previous formula, see that I'm coming in the formula, see that one geodesic between AB plus square of the geodesic between AB. And when we are considering the connectivity index, so hyperconnectivity index, when we are considering this one or defining hyperconnectivity index, that geodesic between AB is replaced by connectivity between AB. So these are the simply changes, very simple change among the different type of your topological indices. And we have also proved some your upper bound or relation among the other graphs like that for hyperconnectivity indices. And this is another result for any fuzzy graph containing n vertices with sigma A equal to 1. Sigma equal to 1 for all vertices means all the vertices are considered as certain. Okay, all the, if the membership values of the vertices are 1, then the vertices are certain. And we consider the membership value of an edge equal to x, is any arbitrary edge, and all the membership value of all edges are considered as x. That means membership values are equal basically. That should be lies between 0 and 1. Then FCI, the hyperconnectivity index, equal to n into n minus 1 by 2 into x. And your fuzzy hyperconnectivity index is equal to this one, x plus x square. Okay. So these are the generalized formula if the membership value of the edges are equal and the vertices are certain. This is another result. Now we are interested, no, after theoretical development we are interested what are the applications. No, every your lecture the candidates are asking what is the application of this thing. So just I am trying to present the application in chemical compounds. So see that these are the 18 isomers of CH18. CH18. I am coming back to the chemical compound. So when n equal to in the alkanes, when n equal to 8, not much more, then it has 18 alkanes. If n equal to 4, methane, ethane, propane, then n equal to 4 means butane. It has 2 isomers. If n increases, then the number of isomers are increases. So when n equal to 8, C8H18, it has 18 isomers. So see that all the diagram are different, no? All the representations are different, but the chemical formula is CH818. Chemical formula is same, but the representation are different. So for different representation, all this graph has different your topological index. Any kind of topological index, if defined by your, if you want to calculate the Wiener index, its values are different for the different isomers. If you calculate the Randic index, the indices should be different. So for different representation, different indices are there. So these are the octane isomer. This is called the octane isomer. For different in, it has different name also. Okay, so 18 different isomer has 18 different names. So these are the name of the isomers. We have no idea about this naming, why it is called this particular name, why the second one is called another name. This is the subject of chemistry. And for this, your 18 chemical compound, the ascending factor, this is a particular type of chemical properties. You just remember it. It is not the mathematical term, this is the chemistry term. So ascending factor is the chemical properties or chemical values, and entropy is little bit known to us. No, this actually measures the your uncertainty. Entropy is used in different situations. The entropy mainly determines or measures the uncertainty of the system. So entropy of the that particular type of compounds and second Zagreb index, these are the mathematical values calculated for 18 isomers. So this is the mathematical values based on the graphical representation, and these two are the chemical parameters. So see that for ascending factor we have calculated this particular regression equation. Okay, based on the experimental value ascending factors. No, for 18 compounds there are ascending factors. So based on these values we have determined this regression equation. This is the y equal to mx plus c. No, regression equation means straight line fitting, y equal to mx plus c. So y means ascending factor. This is m into second Zagreb index is the x, and this is constant. And the correlation coefficient between your second Zagreb index and ascending factor is minus 0.977, this one. And for entropy, the another regression equation is this one, this time into second Zagreb index plus 136.77, and r equal to correlation coefficient is minus 0.9196, etc. If the correlation values is very close to 1, that means there is a high connection or relation between the parameters. No, so 0.9 means high values very close to 1, but see that this value is more better than this value is more better than this one. No, so what is the diagrammatic representation? So this straight line is the regression equation for the ascending factor, and dot represents the actual experimental values. So the horizontal line represents the second Zagreb index, the vertical line y-axis represents the ascending factor. So see that almost all points are very close to the straight line regression line or on the regression line. So we can say that from this regression equation or that line, we can determine the ascending factor of all other alkanes. No. Similarly, for this diagram or regression line, see that this is the regression line for the entropy, and dots are the exact experimental values. But see that no dots, some dots are very far away from this regression line. So this regression line also gives the good your measure of entropy for other alkanes, but the correlation coefficient for this case is less than the previous one. See that the regression is 0.91 and regression is 0.97. So the first regression equation gives the more better result compared to the second one. So this should be analyzed, and this equation actually gives the relationship between the experimental values and the mathematical equation. But from the mathematical equation, from the regression equation, we can determine the your entropy or ascending factor. Or you can modify this type of regression equation to get the more better result. Okay. So this is one application for the Krebs graph. Okay. And for fuzzy graph, we are trying to present one application regarding the kidnapping among the cities. No, lot of kidnappers are there in different cities. So we have considered around 15 cities. We have considered around 15 cities to illustrate our problem, and the cities are considered as vertices of the graph. Okay, And if the two cities are in the same state, then there is an edge between the cities. Or if the cities are belongs to the adjacent state, we draw an edge between that particular city. So using this concept, we consider a graph. This is the graph. This is the corresponding graph, and the cities are this one: Ahmedabad, Bengaluru, and Delhi, etc. So vertex names, short names are this one. Rate of kidnapping per 1 lakh population. Okay. So these are arbitrary values we have considered to illustrate our your topological index. Okay, this is the rate of kidnapping per 1 lakh population. Okay, so this is not the exact value. You don't think that the rate of kidnapping is 24 in Delhi. It is not the truth. This is arbitrarily chosen value to illustrate our method. And correspondingly, we calculate the vertex membership value. So this is the formula to calculate the membership value of vertices. Sigma of Cj. Cj means the ith city. Sigma Cj means the membership value of the city Cj. So this is a formula to calculate the membership value of vertex, and this is the formula to calculate the membership value of a between two cities or of an edge. So R basically represents the radius, covering radius of the kidnapper. Okay, so from a kidnapper from Kochi, he or she has a certain particular region, no? So it may be 100 kilometer or it may be 200 kilometer. Within that particular region, he or she can do his crime. So R is a particular radius, covering radius for the kidnappers. So this is the formula. That one is initiated by my student. And this is the corresponding graph. And these are the age name, distance between the cities, age membership value. So this is the table. And this table contains that different ages and their membership values. Okay, as per that formula we have calculated. And this table calculates the membership value of each vertex as per the definition. And we have defined multiplicative first Zagreb index. See that in the I have already mentioned the first Zagreb index. In that notation or in that definition, this one that this is a product, and in first Zagreb index, this one was the summation of that thing. But in multiplicative Zagreb index, the summation is replaced by multiplication. So this is known as multiplicative first Zagreb index. So see that using this notation, we have another topological index. So we consider this multiplicative first Zagreb index. We define the score of a graph. Score of a graph means the first Zagreb index, multiplicative first Zagreb index power 1 by twice n. N means number of vertices. This formula calculate the score of a graph or score of a subgraph, and this formula calculate the score of a particular edge. And using this formula, we calculate the score of the subgraph and score of the edges here. And using this computation, we consider that if the score of a particular edge is high, then we can say that, so edge means there are two cities, no? So there is a, if the score of an edge is high, then we can conclude that there is a high chances between the high chances or kidnapping between the two cities. The kidnapper between the two cities. Okay, so this is the ultimate conclusion. So this is one application. So lot of efforts we have given to model that particular type of problem, to define the how we can calculate the membership value of the vertex, and how we calculate the membership value of edges and score function. So these are the main invention of this your work. And lastly, these are the references. So the few references. My student Islam, he published a lot of papers on topological index on fuzzy graph. Recently he has published, and these are my recent book published in Springer or Elsevier. So this book is published in 2024, Recent Developments of Fuzzy Matrix Theory and Application. Okay, and this is another edited book published from Elsevier Academic Press you know, this is a very prestigious publishers. Picture fuzzy logic and its application in decision making problem. Picture fuzzy means a particular type of fuzzy sets. Okay, picture fuzzy set. And this one, another book on fuzzy optimization, decision making and operation issues. That one is edited book. And this one is a book on graph theory, textbook, Modern Trends in Fuzzy Graph Theory. This one published in 2020. So this book is very good as per my knowledge, because we have, I am one of the author. So this is a very good book for the fuzzy graph theoretician, for the beginners as well as for the expert. And this book contains 10 application in a chapter. Okay, 10 application we have provided. And the first chapter is the introductory chapter for the people who can start or who can initiate the work on fuzzy graph theory. The first chapter is important for the beginners, and last chapter is important for the applications. And in between, all the chapters are useful. So this is my important books, and these are the other edited book published by IGI Global. And thank you for your patience. Okay. Thank you.
Hello.
Sir, I want to ask that fuzzy graph theory is mainly used to study the networks, and the topological indices is mainly used to study the chemical compounds. Now you combine both them and you give the application of topological indices of fuzzy graph in network analysis. Can we use them? Can we have any application of topological indices of fuzzy graph in chemical compounds?
Yes. See that the number of edges, that means the number of bonds, etc., are certain. There is no uncertainty. No, it is well known the balance of carbon is 4, balance of hydrogen is 1. Okay, there is no uncertainty. But the transformation of energy is there is no specific amount. The energy transform from one chemical compound to another chemical compound. So that one is uncertain things. Okay, entropy is little bit uncertain. So if the some chemical properties or edges, or if you consider some chemical property, actually see that in this presentation we are just consider the degree of the carbon atoms and degree of the hydrogen atom. If you consider the another thing regarding related to or passing through the edges, okay, so something is passing from one carbon compound to hydrogen atom, carbon to hydrogen atom, that may be your energy, that may your another chemical compound. No, that properties, that values are not certain. If you consider that type of properties, then you can properly define the topological indices for chemical compound, fuzzy topological indices for such type of chemical compounds. If the chemical properties are uncertain, if you consider some chemical properties are there, these are uncertain, and in that particular case you can go for fuzzy chemical graph theory. Okay,
thank you, sir.
And if the things are certain, there is no need for fuzzy graph. Okay,
thank you.
Any other questions?
Sir, it was a wonderful session. I have a small doubt. Sir, in the first slide which you shown, is all the molecular graph, are they line graphs?
Line graphs? No, not necessary.
Okay, sir. So my next doubt is, my next query is, can you tell me some of the applications of fuzzy topological indices in artificial intelligence?
What is the meaning of artificial intelligence?
Sir, like...
It is a very big topics, no?
Yeah.
So that application I have mentioned, no, that one is an example of artificial intelligence.
Okay, sir.
Some cities are there, and some kidnapping rates are you may given, and there is your software or your apps. From that apps or your software, you can determine the relationship between the kidnapping, like that. So this is the problem of artificial intelligence.
Okay, sir.
Thank you, sir.
Sir, if we are introducing a new topological index, whether there is any set of rules or properties it should satisfy?
No, you can define in different way. The topological index, lot of scopes are there, lot of another scopes are there that are not mentioned in this lecture. So you can define the topological index in any arbitrary way. Okay, there is a lot of scopes, but that topological index should have either mathematical properties, interesting mathematical properties, or it should have some application. If it is at either application to solve any kind of problem, it may be your problems related to chemistry, or your related to any social problems, or your medical problems, or any other kind of problems, or it may have some mathematical interesting properties. Now see that factorial n, the factorial n has very useful mathematical properties, and it is used in many applications. So that's why factorial n is a very simple thing, but it is interesting thing. No, similarly you can define any arbitrary topological index, but either it should have mathematical properties, interesting mathematical properties, or either it has some application. So most of the people are asking what is the application of these things. So it is better to find out the application along with your formula.
One more question is there. Is there any relation between centrality measures and topological indexes? Centrality measures like degree centrality, between a centrality, those kinds of centrality measures and topological.
I don't have that idea.
Okay, sir.
Any more questions?
So, molecular graph theory, when combined with deep learning, has some applications in.
I have no idea on deep learning.
Okay, sir. So it is a common question. So it has some application in drug toxicity prediction. So if someone has to pursue their research in drug toxicity prediction, how would they prove the authenticity of their result?
So I see that if you use the topological index, so there should be a regression equation. It may be linear regression, or it may be other type of regression. If the correlation coefficient is very high, and if it is you are satisfied or very close to the experimental data, then it gives the guarantee that your prediction from that regression line or your analysis is correct.
For that experimental data, should we pursue
You need some experimental data.
Yes.
And you should fit your experimental data with your mathematical expression or your topological index. If it is very good, your correlation coefficient very close to 0.99 like that, or 97, etc., then you can give your theoretical your formula is good or correct.
Okay. Thank you, sir.
Any more questions? Okay, I think we thank the speaker.
Thank you very much.
Thank you, Ayman sir, for chairing the session. And I invite you to honor our speaker and Professor Madhumangal Pal sir to accept a token of gratitude. Thank you, Madhumangal sir and Ayman sir. Now it's time for a break. We invite you to enjoy a tea time. We will reconvene here at 11:15. Thank you.
Yeah, good morning, everyone. I'm presenting on this topic, descending endomorphism graphs of groups. So what we have tried to do is define a kind of graphs on a group, representing a group. So basically, we know that there are different representations of graphical representations of groups, starting with Cayley graphs, which depend on a connector set, right, for defining them. And then recently there has been much study on power graphs, for example. And yesterday, day before, we saw the generating graph of a group, which is also a very interesting concept. So I have tried to add to this literature by coming up with some new representations of graphs. So in particular, we will be looking at the descending endomorphism graph as well as the normal closure graph. So the descending endomorphism graph is something I've studied before and as part of my PhD, and the normal closure graph is something I've defined recently. So I'm just now introducing it. So a very quick introduction to what is a descending endomorphism. So we know that in the study of groups, quotienting is an important operation. We can simplify the structure of a group by going to the quotient group with respect to some normal subgroup, and then looking at its properties and seeing which properties translate and reflect. Okay. So if you look at endomorphisms of groups, so automorphisms and endomorphisms of groups tell us about the structure of the group. So if you look at the endomorphisms of groups, then even if the group G has an endomorphism, when you come to the quotient group, that endomorphism may not come down to the, so to speak, come down to the quotient necessarily. That means it may not induce a corresponding endomorphism of the quotient group. Okay, so we are defining an endomorphism called descending endomorphism, which is one that descends to every quotient of the group. Equivalently, we can say that whenever there is a epimorphism, surjective group homomorphism from G to any group Q, then this descending endomorphism is an endomorphism delta that will always go to the or induce a corresponding endomorphism of Q. Okay, that we can say in category theoretic language that this diagram commutes. So for example, if we consider Z direct sum with Z as a group, then scaling the elements by 2, that will be a descending endomorphism. It's quite obvious. Even if you take any quotient, the same scaling by 2 will be an endomorphism of the quotient also. Whereas if we take this other operation of interchanging the elements, swapping the two coordinates, twist, right, epsilon of AB is equal to BA, then that will not descend. We can see from a particular example that it will not descend. Okay, so there are descending and non-descending endomorphisms in general. So we are studying descending endomorphisms, and this is just a simple lemma that says that when you have the descending endomorphism, so in the definition, if you see this, in the induced endomorphism in the quotient group is denoted by phi. Okay, sorry, delta bar. Okay, so point. Okay, sorry. It's okay then, it's fine. I'll just explain. So the descent of the endomorphism is delta bar, and that's a unique endomorphism. So what this says is that the descent is also going to be a descending endomorphism. So it's a property that is inherited by the quotient. Okay. So let me get to the main matter. So this is a characterization of descending endomorphisms. Firstly, this one, we can say that an endomorphism of a group G is descending if and only if it leaves all normal subgroups invariant. That is, it maps every normal subgroup to a subgroup of itself. That's a very simple characterization. And similarly, in terms of normal closures, we can say that an endomorphism is descending if it maps each element to some element in its normal closure. Normal closure of an element is the smallest normal subgroup containing that element. So there is something called power endomorphism. That is, we know power maps. So any element can be mapped to some power of itself. So power endomorphism is an endomorphism that maps every element to a power of itself. Okay. So this is another way to say power endomorphism is it maps every element to some element in the cyclic subgroup generated by that element. So similarly, we can say that descending endomorphism is an endomorphism that maps every element to some element in the normal closure instead of the cyclic subgroup generated by the element, normal closure generated by the element. So this is a relation that is motivating the definition, as we will see. So this is a result that says that if the normal subgroups of a finite group form a chain under inclusion, like in symmetric group, for example, or a cyclic group of prime power order, then every endomorphism will be descending. Okay, such a group is called normally uniserial groups, sometimes just serial groups, uniserial groups. Okay, so this says that descending endomorphisms of abelian groups are exactly the power endomorphisms or power maps, all the power maps. Okay, nothing else. In fact, universal power endomorphisms. So this is the definition of the power graph, which was defined some time ago by Kelrev and Quinn for semi-groups, and then extended to groups also. Peter Cameron has done a lot of work on this. So the power graph of a group is a graph on the defined on the vertex set of the group in which every element is adjacent to all its powers. Okay, except itself, because we want to avoid self loops. But here we are going to consider self loops also for a particular reasons. So there is a directed and undirected version of that. So similarly, we define the directed descending endomorphism group of a graph of a group as one that maps each element to all the images under the different descending endomorphisms. So the motivation for this particular definition is that we can see the power graph as mapping every element to images under power maps. In the particular case of abelian groups, power maps will be endomorphisms. All power maps are endomorphisms. So under the power endomorphisms in the case of abelian group. So this works for non-abelian group also. We take the descending endomorphism and map the elements. Okay. So similarly, we define normal. So this I have defined before. So this is new. The directed normal closure, not endomorphism. Sorry, that's a typo. Directed normal closure graph, where we map every element to all the elements in its normal closure. Again, this is another way to generalize the power graph. Not generalize, but analogous to the power graph. Okay. So I'll just quickly go to the results. This is just showing that this mapping of graphs to groups, whether it is through power graphs or descending endomorphism graphs or normal closure graphs, that will be a functor from the category of groups to the category of graphs, but if you consider self loops. Okay, so these are examples of, the first one is a power graph of symmetric group S3, and second is, what, time over? 7 minutes over. Okay, this is the power graph of S3, the descending endomorphism graph of S3, and the normal closure graph of S3. So we have some results which are parallel to the results on power graphs, and in some case the results are different. So this is characterizing bipartite power graphs and descending endomorphism graphs and normal closure graphs. Similarly, this is if you remove the identity element and it's still bipartite. So it is K4 free, in other words, but not triangle free. Yes. The descending endomorphism graph one is published, but normal closure graph is not. So this is a case where the power graph and descending endomorphism graph are different. Okay. So, and just I would like to show one final result. Because it is analogous to the, I mean, it's very similar to the result that you showed, sir, the other day. That is, in the case of, if n is even, then the descending endomorphism graph of D2n of order 4n and dicyclic group of order 4n as well, they will be equal. In fact, not just isomorphic, they will be equal. Okay. So that I would conclude. So thank you. Yes, sir. Sir, I think something is gone missing. The published work is also there in this. The other references are basically the group. Yeah, yes, the order is changed, that's all. So these are the published papers, and these are the other references. Questions? Thank you.
Thank you. Next we have Ms. Danyasri H. dealing with the title, The Non-Distributing Graph of an Earring.
Good morning, everyone. So the title of my talk is the non-distributing graph of a nearing. So if you consider a ring in general, we know that a ring has three properties. That is, if you take R with respect to addition, that is, if you call R as a ring, R with respect to addition will be an abelian group. R with respect to multiplication will be a semi-group, and it will have two distributive laws. But if you consider nearing, so the basic definition of nearing says that it's a generalized version of ring actually. So here we say a set n together with these properties as a nearing. If n with respect to addition is just a group, abelian is not necessary here, and n with respect to multiplication is a semi-group, and it has only one distributive law. So if it has only right distributive law, we say that it is a right nearing. If it has only left distributive law, we say it is a left nearing. So here in this presentation, we have mainly considered right nearing. So here's an example of a nearing, that is, we have taken the symmetric group S3 with the following elements, and here addition is considered as usual composition, and instead of the multiplication, we have taken the following multiplication table. And these are some of the substructures of nearing. That is, if you take the zero symmetric part of a nearing, that is, if you consider those elements of the nearing where n into 0 is always equal to 0 for all elements of the nearing n, then that set is called as the zero symmetric part of the nearing. And if you consider those elements of the nearing where n into 0 is always equal to n, or if in general if I take n into n dash is equal to n for all elements of n dash in n, we call this set as zero symmetric part of the nearing. Then we have the Pierce decomposition, which says that every element in the nearing can be uniquely decomposed as zero symmetric part and constant part. So here we have the expression, and we say that a nearing is zero symmetric if n is equal to n naught. That is, if all elements in the nearing have the property that n into 0 is equal to 0. So here, in case of nearing, since one of the distributive law is failing, we have introduced a graph called non-distributing graph of a nearing. So here what we do is, our graph definition says that all the nearing elements are considered as vertex set here, and we say that two distinct elements x and y are adjacent if this holds. That is, if n into x plus y is not equal to nx plus ny for some n in n, not for all, for some n in n. Then similarly, using that, we have also defined undirected non-distributing graph, and here's an example. And these are the few basic observations. That is, if you say that n is distributive, that is, if the nearing is distributive, we say that the nearing is distributive if it satisfies left distributive law as well as right distributive law. Since our edge condition here says that n into x plus y should not be equal to nx plus ny, here we can see that since a nearing is distributive, it will hold left distributive law also. So from this case, we can say that the graph is totally disconnected, directed as well as undirected graph. And if you take the other case, that is, if the nearing is not zero symmetric, that is, if all the elements in the nearing are from the constant part, then we have the following observation that the graph is complete graph, that is, underlying directed graph as well as undirected graph, both will be complete. And we have the observation that the vertex 0 is not isolated. So from these observations, we can very well see that instead of considering the constant nearing, we can consider the zero symmetric nearing, which is not distributive, and we consider our studies based on that. So here's the first result. So here the result says that the set of isolated vertices in the graph in ndg of n forms a subgroup of the additive group of n if n is finite and zero symmetric. Please note we are considering only finite and zero symmetric case here. So first of all, from the previous observation, we can say that if you consider I as isolated vertices, 0 will definitely belong to the set of isolated vertices, and we show the closure property, which is enough to show that the group is a subgroup of NDG. And here we have one more result for coset related, that is if n is a finite nearing and the set of isolated vertices here is considered, and here we can say that for all x, y and in n, either every vertex of I plus x will be adjacent to every vertex of y plus I, or no vertex of I plus x is adjacent to any vertex in y plus I. And here's the proof. So if you take, if you consider that the set of isolated vertices form a normal subgroup, then we know that there will be only two cosets. So it says that in particular each coset I in n either forms an independent set of vertices, that is nothing will be adjacent to each other, or it forms a complete subgraph. And here's one more result, that if n is finite and if it is zero symmetric nearing, then if the non-distributing graph has exactly half the number of vertices, half number of isolated vertices, then the resulting graph will be isomorphic to Km, that is complete graph with m vertices, union Km bar. And here's an example. So if xy is not an edge in NDG of n, then for all n in n, nx plus ny will be equal to ny plus nx. And we have taken some results from non-commuting graph. These are my references. Thank you. So it's just a preliminary work I have just started.
It's okay. Is it a diameter to graph?
No, sir, because we are getting disconnected graphs here. So the concept of diameter,
Isolated
because isolated
when
vertices are
consider
there.
the connected component or connected components separately, will it be diameter to graphs?
That is, if we have a universal vertex, then we can say about, otherwise no, sir, diameter is greater
That
than
characterization is not done, right?
No, not
so
done.
Will there be any possibility to have universal vertices?
Because in case of constant nearings, in constant nearing we are getting complete graphs.
Okay.
So in that case, diameter and other study can be done, sir. But
other possibilities are
too.
So is it possible to be connected graph?
Yes, sir. We have got components which are connected graphs. So from that we can, like, if you remove the isolated vertices and then form a graph, maybe then we can study. That's possible.
Then you can think about the completion concept also, right?
Sorry, sir?
You can consider about the completion concept also.
Yes, sir, we can see. That is in case of...
So in today's first talk, you might have heard about that idea,
Yes, sir.
idea of completion.
Yes.
He talked.
Yes, sir.
Completion concept with respect to any property also.
Okay.
Okay.
Yeah. Thank you, sir.
So you took S3 and you applied some
Yes,
multiplication.
Sir. Yes, yes.
So what are other things we can do? Means for example, for a given n, number of non-isomorphic groups concept is there.
Yes, sir.
Similarly for rings also people are studying.
Yes.
I think up to 11 or something people classified. For near rings, first before constructing the graph, first we need to know for a given n, how many near rings we can construct, right?
Yeah.
So before I'm not complete. Just one more point I want to add. If the group is cyclic, how it affects your n of x plus y not equal to n of x plus. For example, you are already confined to finite.
Yes, sir.
In your definition, it is a group, need not be abelian.
Yes, sir.
But if it is abelian, also works.
Yes, sir.
Right.
Yeah.
You are not asking, but it is just group is sufficient. If it is cyclic, how what is impact?
That I have not checked yet.
Check. Okay. And so for a given n, even for 6, how many near rings you studied till now?
So for Z6, we have some 24 near rings are there, sir. That is, if you want to compute the near rings, we can use gap packages there.
Okay, right.
So using that, we can find out. Then for S3, there are many near rings. Then similarly for D3, which is isomorphic to S3, we can, we have many
is it possible to, is it somebody worked how many non-isomorphic rings are there for a given n equal to 6 itself? Can you go from 3 to 2 onwards? Do you have some number?
Sorry, sir, I didn't get the question.
No, n equal to 2. N equal to 2. How many near rings are there? How do you count? I want to count all of the up to isomorphism. How many near rings are there for n equal to 2?
N equal to 2, I think there are 3 multiplication tables are there.
Possible, okay.
Yeah. So we usually refer to gap software and check.
Yeah, so that's what. So n equal to 2, you know, n equal to 3, like that, you know up to some numbers, how many are there like that? Are you studying that?
Yes, sir.
Okay.
Because whenever we are considering graphs, we are taking this
that one
all
from the
near
gap.
rings we are considering and then generalizing.
So in the gap, how long it will give?
Up to order 15 it will give.
15
sir.
it will
Yes.
give. That means already people know that
Yes, sir.
it is giving means already they know.
Yeah.
Okay.
After 15 we are not able to get
yes.
like that. Yeah.
Okay. Thank you.
Thank you, sir. I thank the organizers for the opportunity provided. Thank you.
Thank you. Our next presenter on stage is Ms. Arati Panikar, and her title of presentation is A Study on Comparison of Different Domination Parameters and K Conversion Set.
A very good morning to all. I am Arati Panikar, research scholar working under Father Joseph Varghese, Department of Mathematics, Christ deemed to be University, Bangalore. My topic for the presentation is a study on comparison of different domination parameters with K conversion set. This is an overview for my presentation. Coming to the basic definitions, I'm considering a graph G with few of its vertices at state red and the rest of the vertices at state white. If a white vertex is having at least k red neighbors at time t, then this white vertex will turn to red at time t equal to t plus 1. Also, once a white vertex is turned to red, it will never come back to white. This process is known as irreversible k threshold process. Now, the set of vertices that should be assigned red initially so that the whole graph eventually turn to red under this process is known as K conversion set. And the minimum cardinality of this set is known as K conversion number. This is an example for one conversion number of C5 and two conversion number for C5. And these are few of the applications of K conversion set. Coming to the domination parameters I've chosen, the first one is K subdomination function. Here, the vertices of a graph can be labeled either with -1 or +1 such that at least k vertices should satisfy the condition that sum of labels of its closed neighborhood should be greater than or equal to 1. Minimum of sum of these labels is known as k subdomination number. This is an example for two subdomination function for a wheel graph. Coming to the second parameter, this is Italian domination function. Here, the vertices of a graph is labeled either with 0, 1 or 2. such that vertices assigned 0 should satisfy the condition that sum of labels of its open neighborhood should be greater than or equal to 2. Again, minimum of sum of these labels is known as Italian domination number. This is an example for Italian domination function for a tree graph. Coming to the literature review, I've got this concept of K conversion set from the first two papers mentioned here. K subdomination function from the third paper and Italian domination function from the fourth paper. Coming to the results, I'm dividing this into three sections: K subdomination function, N subdomination function, and Italian domination function. Coming to K subdomination function, I'm assigning 1 to vertices in minimum 2 conversion set and negative 1 to the other vertices. So following this pattern, considering minimum 2 conversion set of a path graph, I got for odd path graph, floor function n by 2 vertices will satisfy subdomination function. And for even path, n by 2 plus 1 vertices will satisfy subdomination function. Following the same pattern, considering minimum 2 conversion set itself, if 2 conversion number of a graph is less than its minimum degree, then none of the vertices will satisfy subdomination function. Here is the example. Coming to the second section, N subdomination function. So here, all the vertices should satisfy K subdomination function. So vertices assigned 1 will form a 2 conversion set of the graph, but this may not be the minimum one. This is an example, N subdomination function for C8, but this is not minimum. Now, taking N subdomination function for a regular graph, vertices assigned 1 will form 1 plus floor R plus 1 over 2 conversion set of graph G. And if you're taking the graph as a complete graph, vertices assigned 1 will form minimum 1 plus floor R plus 1 over 2 conversion set. Here is an example for 3 regular graphs. And here, a complete graph with 5 vertices. Now, coming to the third section, Italian domination function. Here, 2 conversion number and Italian domination number for a path graph will be always the same. Here is the example. Now, to conduct the study for this, I am choosing few tree graphs. The first one I've chosen is caterpillar tree graph, uniform caterpillar tree graph. So here, 2 conversion number will be equal to Italian domination number if and only if the graph is isomorphic to the mentioned graphs here, C23, C33, and C43. So these are the graphs for mentioned graphs with the assignment. Coming to the second tree graph, I've chosen star-like lobster graph. That is a lobster graph with all the P2s attached to just one vertex of central path. Here I represents the position of P2s attached, N the number of vertices in the central path, R the number of copies of P2. And here 2 conversion number will be equal to Italian domination number for all even n for any I and for all odd n for any odd I. This is the example for odd star-like lobster graph. This is even star-like lobster graph. Coming to the last tree graph, I've chosen lobster graph. Here 2 conversion number will be equal to Italian domination number if and only if P2s are attached to odd positions of Pn if n is odd, or if n is even, P2 should be attached to alternate vertices. That is, no 2 adjacent vertices of Pn should have P2s attached to it. And here is the example for even lobster graph at odd lobster graph. So to conclude with, I've made a study to compare K subdomination function and Italian domination function with K conversion set. To learn the first one, I have assigned 1 to red vertices and negative 1 to white vertices and got the mentioned results. And for Italian domination, I have chosen few tree graphs, and there I got the condition for 2 conversion number to be equal to Italian domination number. So that's about my presentation, and here are the references.
Hello, Arati. Is there any criteria by which you are assigning the values 1 and 0? You have assigned 1 for red and 0 for white, right?
1 for red and negative 1 for white.
White, okay. So
no particular criteria, ma'am, just a random assignment. Because the application here for K conversion set, we'll say that to find the spread of disease, so we'll choose the infected persons as red vertices and the other one as white vertices. So to compare, to learn more about the infected person, I'm giving 1 to the red vertices. That's
Okay, so I think if you can assign an upper bound or something for the number of vertices which can be considered red or which can be white, you can have some more results, right?
Sure, ma'am.
Yeah. Okay.
Are you studied the concept, come across concept like Catalan numbers?
Sorry.
Catalan numbers.
Mm.
Because one of the criteria you took summation of f of v greater than or equal to 1, right? You are acting 1 minus 1. Then please look at that they are related to Catalan numbers, may be useful to you.
Okay, sir. I'll learn.
Okay.
Thank you.
Thank you. Next, we have Mr. Basit Ayobmir. He'll be dealing with the title on the distance spectral radius bounds and improved bounds on the spectral radius of power graphs of some finite groups.
Okay, good morning everyone. So my name is Bastu Mir and I am doing my research at SRM University AP under the supervision of Dr. Fawzil Latif sir. So today the topic of my presentation is improved bounds on the spectral radius of power graph of some finite groups. So this is the structure of my presentation. And here is the introduction first. So we know a graph consists of pair of vertices and edges, and there is an adjacency relation which decides whether two edges will be connected or not. And the degree of vertex is the number of edges incident on that vertex. And a graph is said to be connected if there is a path between every pair of vertices. And a complete graph is a graph in which there is a So if we have an undirected graph on n vertices and there are degrees di's irons from 1 to n, then d max we define it as maximum of the di's where irons from 1 to n, and d minimum is the minimum of di's where irons from 1 to n, and d average is the sum of all di's divided by n. So now we have the main part of this presentation which is regarding the power graph. So power graph of a group is if we have a group, every element of that power graph is represented by the elements of the group, and two vertices are adjacent if and only if one is the integral power of other. So here is an example of power graph of Z6, and there we have an example of power graph of dihedral group of order 12, and here is an example of power graph of dicyclic group of order 12. So there is some previous work regarding the power graphs. So Mehranian et al. They gave the structure of power graph of finite group Zn in terms of complete graph. And Chakrabarty et al. They proved that the power graph of a finite group is complete if and only if the group is of order 1 or p power m. And Cameron proved that the power graph of G with vertex set S joined with all other vertices and order of S is greater than 1, then G is cyclic of prime order, or G is cyclic of non-prime order, and order of S is 1 plus phi of n. And or G is generalized quaternion, and S contains the unique identity, and S contains the identity and the unique involution. Unique involution means order of there is an element whose order is 2. So there is some previous work related to power graphs. Also, Shriparna et al. They found the spectral radius. They found the bounds for the spectral radius of power graph of some finite groups. And actually, my sir and her guide they proved that the spectral radius of a non-negative square matrix A is same as the spectral radius of quotient matrix corresponding to an equitable partition. So these are the existing results. They proved that for n greater or equal to 3, they gave the upper bound and the lower bound for the power graph of Cn, where the Cn is the cyclic group of order n. And this I is equal to phi of n plus 1. D max and D minimum are the maximum and minimum degree of non-identity and non-gender elements of Cn. And this is this equality will hold if and only if this Cn is complete. They also gave the spectral bounds for the power graph of dihedral group of order 2n in terms of spectral radius of power graph of Cn. And similarly, they did it for the power graph of dicyclic group. So what we did is we improved the bounds for these. First, we improved the bound for the power graph of spectral radius of power graph of this Cn. Instead of using D minimum, we used D average, where this D average is the degree of non-identity and non-generator elements of Cn. And this similar, again, equality will hold if and only if this power graph of Cn is complete. Also, we proved that if we have a group of group G equal to ZPQ, where PQ are the primes, then the spectral radius of the power graph of ZPQ is given by the largest root of this cubic equation. We also proved that the spectral radius bounds for the power graph of dihedral group of order 2n, we gave the upper bound and the lower bound for this, and where this D average is the degree of power graph of Cn. Similarly, we did it for the power graph of dicyclic group of order 4n. And here is the comparison how when we were using the D minimum and D maximum, how the bounds were now, how the bounds are when we are using D average. So we can see how close the bounds are coming out. So this was all about my presentation. So these are the references. Thank you.
Actually, D average worked because it is not regular graphs, right? Power graphs, Cn is regular, but power graph of Cn need not be regular. It is not regular.
Yeah.
Because of that, that D average worked.
Actually, this Cn part is, sir, I was having that example there. The upper part is actually the Cn.
Yeah.
That is we are considering. That is need not be regular.
Yeah. Otherwise, average and minimum degree, max and everything is same.
Then that will be same.
That's it. Yeah. Okay.
You have some computational aspect also in the study, right?
What, sir?
You have some computational aspects also in the study, right?
No.
No.
Actually, this paper is distributed into adjacent part, and there was one more distance part. And that part I have done by my senior, actually, that I did not present here.
Thank you. The next presenter on stage is Mrs. Jessalette Ann Matthew, and her title of presentation is The Chromatic Number of Certain Families of Fuzzy Graphs.
Good morning, everyone. My name is Jessalette Ann Matthew. I'm doing my PhD under the guidance of Dr. M.G. Karnambige, Sri Vaspi College, Erode. My title is The Chromatic Number of Certain Families of Fuzzy Graphs. In this paper, the chromatic number of certain families of fuzzy graphs such as path, cycle, star, wheel, complete, graph, tree, caterpillar, and friendship graph are derived. Some relevant properties on fuzzy coloring on fuzzy graph are proved. Furthermore, an application on fuzzy coloring formulated using chromatic number of G. Introduction. Fuzzy graph coloring is one of the most important research area in the combinatorial optimization. Since classical graph coloring fails to address the problem involving uncertainty, fuzzy graph coloring plays a vital role in handling uncertainty, imprecision, ambiguity in various fields. Susan Mons, etc. introduced the concept of coloring fuzzy graph in 2005. The goal of fuzzy graph coloring is to express the fuzziness in the graph data by using the minimum number of colors. This means that the color difference between the connected vertices should reflect the fuzziness in their connection. Some of the most practical problem in the literature are traffic light problem, scheduling problem, frequency assignment problem, etc. Review of literature. In 2005, Susan Mons, etc. introduced the coloring of fuzzy graph, and they designed the traffic light problem using fuzzy graphs. In that paper, they proposed a method for coloring the vertices of the fuzzy graph with the crisp vertex set and a fuzzy edge set. In 2006, Heslashi and Onuga developed a similar method for coloring fuzzy graph with a fuzzy vertex set and a fuzzy edge set based on the strong edges between the vertices. In 2015, Zovan, Samantha, etc. introduced a new concept to color a fuzzy graph by using fuzzy colors based on the strength of an edge incident to a vertex, and they also introduced the fuzzy chromatic number. I'm motivated by this paper, and I extend the procedure for coloring fuzzy graph using the fuzzy colors based on the strength of an edge incident to a vertex. Preliminaries, strength of connectedness between two vertices VA and VJ is defined as the maximum of the strength of full paths between VI and VJ, and the membership value of the edge is greater than or equal to the strength of connectedness, then it is strong, otherwise it is weak. Okay, now mixing of a color with a white color dilutes its intensity. Suppose Q quantity of a color CK is mixed with the 1 minus Q quantity of a white color, then the resultant color is called the fuzzy color of color CK with membership value Q, and where CK is called the basic color. The strength of an edge is defined as like this, where mu of VA VJ is the membership value of the edge, and the sigma of VA and sigma of VJ the membership value of the vertices. So in this article, fuzzy coloring of fuzzy graph, the authors used the same coloring method for both weak and strong edges in certain situations. However, we introduce a refined approach by providing a distinct proper coloring concept specifically adapted for both weak and strong edges. Here following the concepts, if edge is strong, then we can color the end vertices of a edge by the following ways. Both the vertices of E can have a different basic color, or one vertex can have a basic color and other can have a fuzzy color corresponding to a different basic color, or both vertices can have a different fuzzy color if it is necessary only. If an edge E is weaker, then vertices can color by any of the following way. Then one of the vertex can have a basic color and other can have a fuzzy color corresponding to the basic color, or both vertices can have the same fuzzy color, or both vertices can have different fuzzy colors. So the definition: fuzzy coloring is assignment of basic or fuzzy colors to the vertices of fuzzy graph of G, and it is proper, it is satisfying these conditions. And the perfect coloring is an assignment of minimum number of colors for a proper coloring of G, and the minimum number of colors needed for a proper coloring of G is called the chromatic number of G, and is denoted by chi f of G. This is an example. I will explain if I need it. Okay, before I'm going to my lemmas and theorems, I would like to give a brief idea on it. If let G be a fuzzy graph, and if all edges are weak, then we can color the graph with one color. So the chromatic number is 1. If all edges are strong, then the coloring of the fuzzy graph resembles the coloring of the crisp graph. So because of the time limitation, I am focusing only on the case where weak and strong edges are distributed in different ways, different sequences. So the result is for path, the result is 2. For cycle, if weak and strong edges are distributed in any sequence, chromatic number is 3 if n by 2 number of strong and weak edges are alternatively distributed in Cn. 2 otherwise. For similarly, we can I proved for star graph and wheel graph. In wheel graph, weak and strong edges are distributed in any sequence. The chromatic number is 4 or 3, and this is some corollaries related to that theorem. And also I proved for complete graph, if weak and strong edges are distributed in any sequence in Kn, then chromatic number of Kn is equal to n minus floor function of n by 2, where n be the number of vertices having at least one weak edge incident to a incident edge. Similarly, we prove for tree, caterpillar graph, friendship graph, and now its application. Here I am calculating the chromatic number. By calculating the chromatic number, we are finding the solution for how many state can offer high quality education to improve the literacy rate by implementing educational data for other state. For that, I am considering some states of India as a vertices, and with the edges connecting, if they have mutual cooperation to improve the literacy of data. The membership value of the vertices represents the literacy rate of the state, and membership value of an edge represents the level of relationship between the state. So this is the fuzzy graphical representation of the problem, and this is the perfect coloring of the problem. So we need only 3 color to color this graph. So the chromatic number is 3. So the conclusion is 3 states can offer high quality education to improve the literacy by implementing educational data for other state. Therefore, to achieve high quality education, a state must either form strong edge with any of the 3 states or strengthen the existing relationship between other state by enhancing the educational quota. This is the representation, and my conclusion is this. And in our further study, it is proposed to work the fuzzy coloring of product graph, and we analyze the concept of chromatic number on it. This is selected references. Thank you.
So thank you for your presentation, but what is the difference between fuzzy color and conventional color?
So in fuzzy, in crisp environment, we are using only adjacent vertices. When adjacent vertices doesn't have the same color, but when we come into fuzzy environment, in crisp environment, we have only 2 chances. If a edge is there, then we can give 2 different color. But when we come to fuzzy environment, we can represent the relation by coloring by different colors. If the relation, if A and B are 2 friends, and A, B, 3 and A, B, C and 3 friends, and A likes B much more. So we can give a different fuzzy color, like red full color with and yellow full color. If A
I am asking about your fuzzy color.
Fuzzy color.
What do you mean by fuzzy color? No?
Fuzzy color.
And there are conventional colors are there, no? Red, blue, white,
Yes.
etc. The
Yeah.
conventional color, but you have used the fuzzy color
Fuzzy
to
color, yes.
color the
Color,
graphs.
yeah. It makes if we take some q quantity of base color, and it mixes with the 1 minus q quantity of white color, and the resultant will get a diluted form of the base color. The diluted form is called the fuzzy color. To represent
No, see that if you mix the black and white colors, no, you will produce
Yes.
different your gray colors.
diluted the black. So
No, that one is the gray colors. All these things are called
yes.
the gray colors.
Huh.
Mixing of black and white colors produces gray color. Infinite number of gray
Yes.
colors. But if you mix with your black and red, green, then which color will produce?
Sir, here I am only considering that my aim is to dilute the basic color. So I am using the white color and the basic.
But in your presentation, no, you have mentioned your red color, yellow color, all this color you have mentioned.
Yes, sir. Basic color may.
Okay, it's fine. So you read carefully that paper. Based on the paper, no.
Okay.
The Shobhan Samanto, and actually basically Shobhan Samanto my student. This
Yes,
is
yes,
our
yes,
paper.
I know, sir.
So you read carefully that papers. Okay.
Okay, sir.
And then you will understand the entire things.
Okay.
It's okay.
Okay, thank you, sir.
Thank you. Next, we have an online paper presentation. The presenter is Ms. Rajlakshmi RV, and her title is Zagreb Energy of Coalescence of Some Graphs. The presenter will join soon.
Is it audible?
Yes, you're audible. Can you hear me?
Yeah, I can hear you.
Okay, so it's just a gentle reminder to the rules and regulations. So you are given 10 minutes, out of which 7 minutes is for your presentation and 3 minutes for the discussion. In the 7 minutes, there would be a warning bell after the completion of 5 minutes, and at the 7 minutes, there will be a final bell. Okay, so you have to conclude your presentation by 7 minutes. Then the rules of and regulations would be like the judgment would be under clarity of your and organization of your presentation, then subject relevance, presentation skills, and handling your question answer session. Okay, so you can start. Thank you.
Thank you. Is my screen is visible? Is my screen visible?
Yes, yes. Can you make it full screen?
Yeah, sure.
Okay.
Can I start?
Yes. You
Good
can start.
afternoon, everyone. Today I am presenting the paper titled Sacred Energy of Coalescence of Some Graphs. I'm Rajalakshmi RV, research scholar from University College, Trivandrum.
Sorry to interrupt. Can you increase your volume? Can you bring the mic a little closer?
Okay, can you hear me?
Yeah, now it's better. Thank you.
Okay.
And please make the presentation full screen.
It is in full screen?
Yeah, okay, it's fine. Thank you.
Okay. Good afternoon all. Today I am presenting in a paper titled Sacred Energy of Coalescence of Some Graphs. I'm Rajalakshmi RV, research scholar, University College, Trivandrum. Introduction. Let G be a graph of order n with vertices labeled as V1, V2, V3. Let Vi be the degree of the vertex Vi for I is equal to 1 to etc. n. The Zagreb matrix of G is the square matrix of order n whose ijth entry is equal to Di plus Dj if Vi is adjacent to Vj and 0 otherwise. We introduce and investigate the Zagreb characteristic polynomial of coalescence of complete graphs. First, there is some preliminaries. First, Zagreb matrix. Let G be a graph of order n. The Zagreb matrix of G is the square matrix of order n, whose ijth entry is equal to Di plus Dj if Vi is adjacent to Vj and 0 otherwise. Zagreb energy. Let the eigenvalues of Zagreb matrix are Z1, Z2, Z2, etc. Zn. Then Zagreb energy is sum of the absolute values of these eigenvalues. For a complete graph Kn, the Zagreb eigenvalues are -2 into n minus 1 and 2 into n minus 1 the whole square with the multiplicities n minus 1 and 1 respectively. And the Zagreb energy of complete graph is 4 into n minus 1 the whole square. A graph G of order n is said to be Zagreb hyperenergetic if Zagreb energy of G is greater than 4 into n minus 1 the whole square. A graph G of order n is said to be Zagreb non-hyperenergetic if Zagreb energy of G is less than 4 into n minus 1 the whole square. A graph G of order n is said to be Zagreb broader energetic if Zagreb energy of G is equal to 4 into n minus 1 the whole square. If Zagreb energy of G is equal to Zagreb energy of H, then two graphs G and H are called Zagreb equianergetic. First, consider an example. Here is the coalescence of complete graph with 5 vertices. That is K5 coalescence K5. K5 has 5 vertices. This coalescence has 9 vertices. Its Zagreb matrix is this one, and the eigenvalues are that. Similarly, we can, from this example and generalization, we can generalize this as the generalization is consider the graph of Kn coalescence Kn. Then the Zagreb matrix of Kn coalescence Kn is this one. And using the matrix operations, we get the characteristic polynomial as this one. So we can state the theorem as follows. The Zagreb characteristic polynomial of coalescence of two complete graphs with n vertices is lambda plus 2 into n minus 1 raised to 2n minus 3 into lambda minus 2 into n minus 1 into n minus 2 into lambda square minus 2 into n minus 1 into n minus 2 into lambda minus 18 into n minus 1 the whole cube. from the above theorem, we can we get some other results. The eigenvalues of coefficients of complete graph with n vertices corresponding to Zagreb matrix are minus 2 into n minus 1 with the multiplicity 2n minus 3, 2 into n minus 1 into n minus 2 with the multiplicity 1, and n minus 1 into n minus 1 into n minus 2 plus or minus root of n square plus 14n minus 14 with the multiplicity 1. And we get the Zagreb energy of Kn coefficients Kn is equal to 2 into n minus 1 into 2n minus 3 plus 2 into n minus 1 into n minus 2 plus n minus 1 into n minus 2 plus or minus root of n square plus 14n minus 14. Next one, for the complete graphs Kn and Km with the n less than m, minus 2 into m minus 1 is a Zagreb eigenvalue of Kn coefficients Km with the multiplicity m minus 2. This minus 2 into m minus 1 is also a eigenvalue of Zagreb eigenvalue of Km. Next one is the graph Km coefficients Kn is Zagreb non-hyper-energetic. Consider another graph. This is an example. Consider the graph K4 coefficients P2. K4 is the complete graph with the 4 vertices. P2 is the path. Then we get the eigenvalues like that. These results can also be generalized as one of the Zagreb eigenvalues of Kn coefficients Pm is 2 into n minus 1 with the multiplicity n minus 2. That is n minus 2 eigenvalues of Kn are same for Kn coefficients Pm. This 2 into n minus 1 is also the eigenvalue of Kn. Next one, the graph Kn coefficients Pm is Zagreb non-hyper-energetic. Consider the coefficients of 3 regular graph with 6 vertices and 2 regular graph with 4 vertices. We are finding the Zagreb matrix as this one. Then the nullity with respect to this Zagreb matrix of this matrix is 1. The nullity of first graph is 0 and the second graph is 2. These results can also be generalized as, let the G1 be a R1 regular graph with a nullity eta 1 and G2 be a R2 regular graph with a nullity eta 2. Then G1 coefficients G2 have a nullity eta 1 plus eta 2 minus 1 with respect to Zagreb matrix. Another one is that the G1 be a R1 regular graph and G2 be a R2 regular graph. Then G1 coefficient G2 is Zagreb non-hyper-energetic. These are my references. Thank you.
Okay, so we are heading to the discussion session. Please switch on your video.
So you are not cited actually. Who introduced this matrix?
I can't hear you, sir.
So who introduced this matrix, Zagreb matrix? So because we do not see any citations.
Gutman in earlier, sir.
Is it introduced by you, this matrix?
Sir, I can hear you, sir.
Yeah, who introduced this matrix?
Gutman.
Oh, good. Oh. So you already computed for two regular graphs. Then why you again done for complete graphs?
So I know, sir. I first computed for complete graphs. Then find some special case such that like regular graphs with R regular graphs, different R regular graphs.
Okay. Do you know when they are going to be integral? Integral means eigenvalues are integral.
Okay.
Yeah. So when for which graphs the Zagreb matrix going to be integral?
For complete graphs, so it's always integral.
Yeah, that is clear, very much clear. Because degrees are same, na? Even for regular graphs, we can think of. But in general,
for regular graphs, there are results for characteristic polynomial and eigenvalues.
Yeah. So
In general, do you know any results about when they are integral for which graphs, characterizing the graphs based on Jacob matrix integrals? Yeah, you're not studying. Okay. Yeah.
In your studies, some computational aspects are there, right? You computed.
Yes.
So, is there any tool for your computations? Are you using any
No,
tool?
no, sir.
Manual
No.
calculation only.
As sir asked you now, you did not, you didn't use any tools for the computation of the spectrum.
Yes, sir.
So how you generally got the Zagreb spectrum of the coalescence of two complete graphs?
What, sir?
So how you got the Zagreb spectrum of the coalescence of two complete graphs?
Using the matrix operations, sir.
So do you have a general form for the Zagreb
From
matrix?
that, some earlier from some earlier results from earlier proofs with R regular graphs, in which I am derived some matrix operations and then he got that result.
See, I am asking you to give you more light into this. So, do you have any block form or the matrix?
We get some general block form.
Okay,
like
then
something.
what is the tool you have used? Whether you expand the matrix and computed the eigenvalues directly or some other tools?
Some other, I got some other results from previous some proofs that giving R regular. There is some result that.
No, I am not asking that. Whether you are having any eigenvalue, eigenvector technique or the
No,
reduction of block matrix.
Some theoretical formulas I used, sir. Not no tools.
Okay, this was one angle of my question, and the another one is, see, Zagreb matrix, something like that. Other matrices related to the graphs have been defined during these years. So, do you have any insight into the graph structure using the spectrum of the corresponding Zagreb matrix? See, we have several results regarding the adjacency spectrum and the structural properties of graphs. Like that, can you deduce any structural property of the graph from the Zagreb spectrum?
Now I'm working in that, sir.
Okay, fine. Okay, thank you.
Okay, thank you. Thank you, Rajlakshmi.
Thank you, sir.
Thank you. Next, we have Mr. Mohammed Nishad Maniparambatha dealing with the title Graph Laplacian Approach to Tunable Band Structures in Photonic Layer Lattice.
I request Nishad sir to switch on the video.
Am I audible?
You can start sharing the PPT.
Sure. Thank you.
Can you make it full screen, please?
Okay.
No.
Am I audible?
You're audible, but the slides are not anymore shared. Can you share it once again?
Yes, student.
Yeah, earlier it was visible, but now it has gone. Can you reshare? Okay, now it's visible. Can you make it in the okay, you can start.
Is it okay?
No, again it went off.
So while making full screen creates some problem. I just left this one and I will be. Now it's okay?
Can you reshare?
Sure, sure.
Full screen is not required. Please.
Yeah,
Share.
yeah.
Okay.
Okay, thank you. Now it is visible, am I right?
Yes, it is visible. You can start the presentation.
Okay. Okay, thank you.
So,
Respected dignitaries.
As I mentioned before.
Pardon?
Okay, as I mentioned before, there would be a warning bell at 5 minutes and a final bell at the 7th minute.
Okay, okay, thank you. Okay, with your permission, I will start my presentation. My topic is graph Laplacian approach to tunable band structures in photonic lab lattice. And we have discussing a theoretical model, nonlinear dispersion relation, resultant discussions, and our conclusions. This research is, I just skipped all the basic things from here. Here, graph Laplacian approach has facilitated studies of dynamics in waveguide arrays with non-uniform coupling. Additional works have explored completely integrable nonlinear Schrodinger models. Soliton solutions on the network with the dipole graphs are also we referred this one. The photonic lab lattice with the flat bands have generated significant attention due to their potential applications. Further, electromagnetic wave localization photonic flat band has been studied in the quantum regime. In this work, we investigate the photonic spectrum of the waveguide array fabricated from the metamaterial. This is we represent in this graph as a unit cell of the photonic lab lattice with the metamaterial is graphically represents with the waveguides corresponding to the vertices and the coupling between them represented by bands. Here alpha and beta are the coupling coefficients. The generalized nonlinear Schrodinger equation incorporating the graph Laplacian and models nonlinear electromagnetic wave creation. By exploiting the metamaterials tunable parameters, we examine dispersion relation for various nonlinear coefficient matrices, including defocusing nonlinearity. Our research demonstrates the potential of the high-intensity optical light to manipulate the band structures of the photonic lab lattice made from the metamaterial. Here is our theoretical model. High-intensity electromagnetic wave propagation in the array is accurately modeled by the generalized nonlinear Schrodinger equation, wherein the Laplacian operator is replaced by its graph counterpart. See here we have I sigma 1 dou ANM by dou theta plus dou ANM by dou t is equal to alpha into ANM minus Bn minus 1m plus alpha into BNM minus ANM plus beta into CNM minus ANM plus beta into ANM minus CN m minus 1 minus gamma 1 into modulus of ANM square into ANM. See, similarly, we have the other equation is that I into sigma 2 into dou BNM by dou theta plus dou BNM by dou t is equal to alpha into BNM minus ANM plus alpha into AN plus 1 m minus BNM minus gamma 2 into mod BNM square into BNM. I into the next equation is I into sigma 3 into dou CNM by dou theta plus dou CNM by dou t is equal to beta into CNM minus ANM plus beta into ANM m plus AN m plus 1 minus CNM minus gamma 3 into modulus of CNM square into CNM. Here ANM, BNM, CNM are the stands for the amplitude of the waves propagating the waveguides 1, 2, 3 that we mentioned in the figure. The pair of integers NM specifies the location of the unit cells within the two-dimensional lab lattice. The symbol sigma j for j is equal to 1, 2, 3 represent the refractive index signs in each of the three waveguides. Additionally, gamma j denotes the cell phase modulation of the coefficients for waveguides 1, 2, 3. These coefficients alpha beta represent the coupling along the branches 1, 2 respectively. We consider the graph models like this. This is equal to here is the this one visual representation of the waveguide array of the unit cell configuration. The shaded region illustrates the nth unit cell and it's directly coupled waveguides in the nearest neighbor unit cells. Here we can convert the equation 1 into system 1 into in this form. This is equal to, can be written as I into S psi theta plus I psi t is equal to G1 psi plus G2 phi minus gamma P of psi. Here define S as a refractive index matrix, and psi is the amplitude matrix for the nth unit cell, and capital phi is the amplitude matrix for the waveguide linked into the nth unit cell from the adjacent unit cells. The 3x3 matrices G1, G2 stands for the graph Laplacian from the generated from the nonlinear Schrodinger equations, and gamma and P of psi denotes the nonlinear coefficients of the and self-phase modulation matrices respectively. So as it will come like this: S is equal to sigma 1, sigma 2, sigma 3, and similarly psi is equal to ANM, BNM, CNM, and phi is equal to ANM plus 1, BN minus 1, M, CN, M minus 1, and G1, G2, gamma, P of psi respectively like this. See, this is our nonlinear dispersion relation to analyze wave propagation of the lab lattice made of the metamaterial. We now derive the dispersion relation. We have an equation is equal to psi is equal to small psi into e raised to I into omega t plus I kz theta plus I k1n plus I k2m, where psi is equal to a naught, b naught, c naught, the initial amplitude matrices. From there we have this, we can derive an equation dm phi psi is equal to 0. Here dm is the matrix that is represented like this, and f is equal to f1, f2, f3, that is equal to gamma into mod psi square. So from there we have s is equal to 1, minus 1, and minus 1, and kappa 1 is can be represented like this. Alpha is kappa 1 is equal to alpha into 1 plus e raised to ik1, kappa 2 is equal to beta into 1 plus e raised to ik2. The dispersion relation is obtained by setting the determinant of dm is equal to 0. So the vanishing determinant of dm is necessary condition for non-zero solution of the equation for dm is equal to dm psi is equal to 0. Okay, now we have this is equal to nonlinear dispersion relation of the lab lattices with metamaterial is figure wise we represent, and this is our results and discussions on this. This is equal to dispersion relation is obtained by setting the determinant of dm is equal to 0, and vanishing determinant dm is necessary condition for non-zero solution of the equation for dm psi is equal to 0. The dispersion curve properties of the waveguide array is now discussed here, and the engineering flexibility of the metamaterial waveguides enables the combination of the linear nonlinear nodes yielding a nonlinear coefficient matrix that can be adjusted to support diverse dispersion curve based on the nature of the nonlinearity. The dispersion curve for the waveguide array corresponding to the nonlinear coefficient materials as shown in the figure 3. See, in figure 3a illustrate the nonlinear coefficient matrix gamma is equal to 1, 0, 0, and comparing to gamma matrix with the refractive index matrix as S is equal to 1, minus 1, and minus 1 is there. See, compared to nonlinear case, the flat band is dispersed towards higher and positive frequencies, shifting away from the 0. See, while seeing this figure, the flat band is we moving to flat band different shape. There we will get the corresponding to amplitude. We will get the
Excuse me, sir.
Hello.
Sorry to interrupt.
Hello.
Sir.
I'm audible.
Yes, sir. But your time is almost over.
Okay.
Could you please
may I move to the conclusion?
Okay.
Okay, just I will conclude within 1 minute. We theoretically investigate the dispersion relation of the metamaterial waveguides array using the graph Laplacian formal approach. The array consists of 3 waveguide unit cells with the diverse optical properties. Our model is based on the generalized nonlinear Schrodinger equation. Examine high intensity electromagnetic wave propagation, exploring variant nonlinear coefficient matrix combination, including defocusing nonlinearity reveals the significant impacts on the dispersion relation. Notably, a matrix of 1 yields decreased degeneracy, shifting the flat band. This research highlights the potential of high intensity like to tailor photonic lab lattice band structures in metamaterials. These are my some of the references. Okay, thank you.
Okay. Apart from one small graphical representation you mentioned in the presentation, what is the role of graph theory in your study?
Yeah, this is actually, we used this equation, that is the equation system 1. This is developed from the graph Laplacian operator. From this system, we generated the matrices. We just, this system is generated because of the this unit cells. And this is the generalized part of that unit cell. This is the nth cell, general focus of that part. And from there, we developed this system of equation. From this system of equation, we created all other parts of the study.
It's only a small network. Even if
Yeah.
without the idea of graph theory, I think the study can be carried out, right?
Yeah, so somewhat it is possible. And we are trying to cope up with the graph theoretical things, but we are not fully successful on that part. We are trying to collaborate with this one. We have the nonlinear Schrodinger equation, have a discrete Schrodinger equation is there. With that, we are trying to cope up the graph concepts.
Okay, Nisha.
Thank you.
Thank you. Thank you very much.
Here we come to an end to the paper presentation sessions. Thank you, judges and
Actually, I should thank the organizers for giving me this opportunity, because all the 3 days I could listen to many new topics in graph theory and motivate the young researchers. And I think this is God Almighty's blessings on me to come here and be a part of this. Thank you so much once again for the organizers. Thank you.
We'll be circulating the feedback forms now. I request everyone to please fill the forms after the end of all sessions. You're requested to submit the form after the valedictory function in the registration desk where you will be collecting the certificates. I repeat, we'll be circulating the feedback forms now. I request everyone to please fill the forms and submit the form after the valedictory function in the registration desk where you will be collecting the certificates.
now it's time for lunch break. We will reconvene at 1:30 for our next session. Enjoy your lunch. Thank you.
Welcome back, everyone. We hope you had a refreshing lunch and some engaging conversations. We are excited to start our session. We have with us Professor Dr. G. Indulal to engage us on the topic spectral characterization of graphs. Dr. Satyanarayana Reddy will be chairing this session. Welcome, sir.
Yeah, so good evening to all of you. So first of all, I'm privileged chairing the first session as well as last session in a conference. I think it may be unique, and in future also I may not get this opportunity. And also great speakers, both Shahul, Hamid and Indulal sir. Okay, so it is great pleasure to invite Professor Indulal. So Dr. Indulal, currently Principal St. Aloysius College, Edatwa, is known for his contributions in the field of graph theory. He acquired MSc, MPhil, PhD from top university and has dedicated himself to teaching and monitoring students, fostering a strong understanding of mathematical concepts and their applications. He has made significant impacts through his 40 plus research publications. His main research project was on topic studies on distance spectrum of graphs. He has collaborated with many renowned personalities from all over the world. Dr. Indulal has published numerous papers in reputed journals and is actively involved in collaborative research projects. His commitment to education and research continues to inspire both colleagues and students alike. Yeah, so it is pleasure to invite Professor Indulal. So we are eager to get something from his research experience. Thanks.
Thank you, sir, for the nice introduction. As at the outset, let me thank the organizers for giving me an opportunity to come over here and interact with the scholars in graph theory. Also, this place is significantly, historically, very significant because being the birthplace of Madhava. Actually, on Madhava's work and the contemporaries Kerala mathematical works, we stand like this. Okay, anyway, thank you, the organizers, once again. See, these 3 days, we suppose witnessed several interactions, presentations, crossing of other fields of graph theory into other branches of mathematics and other branches of science. So we feel that these kind of platforms is very fruitful in enhancing the knowledge level, broadening, deepening our knowledge level. So to add to this, let me present some thing in inverted commas regarding the spectral characterization of graphs. See, this forms a part of spectral graph theory, where the studies mainly focused upon the computation of spectrum, and the other side of the problem is the characterization of graphs. So even though when we hear this, it seems to be the two parts of the same coin, computation of spectrum and computation of the graph from the spectrum. Spectral characterization means characterizing the graph from the spectrum. So let me tell you that it is not as easy as we hear that. One side is a direct problem. Given a graph, compute the spectrum. Then the question is, which spectrum we are going to compute? So spectrum is associated with a matrix. So corresponding to a graph, there should be a matrix. But during these years, see, the spectral graph theory began its research very effectively during 1940s through the work of Ernest Haeckel in molecular orbital theory. So this spectral graph theory, it may have, before that also there may be some kind of results there, but a strong research started only after 1940s. And during this 60 plus 24, 84 years. This area witnessed very unexpected results, positively and in some way negatively also. So because a graph can be represented by a matrix. Which matrix we use? See, the first primary matrix coming to our mind is the adjacency matrix, because the graph stands as like based on the adjacencies of vertices. So something which reflect this adjacency nature through a matrix, because during these years graph theory finds applications in almost all walks of life, which this Leonhard Euler wouldn't have dreamt. In 1736, when he conceived this idea, graph theory, I feel wonder that he might not have dreamt that after 288 years, in 2024, this much kind of elaboration, growth, development, crossing to other branches of life, other walks of life, he might not have dreamt. So when these practical problems are addressed, we may come across a graph, but that graph may not be as simple as we expect. It contains several large number of vertices and large number of edges. So manually handling a graph is not practically possible. So there should be some tool, possibly with the help of a machine, which we use it as a computer. We need some language to decode a graph into the computer language, and the primary idea coming to our mind is a matrix. And the matrix is a that matrix should tell what the graph is, and graph is based upon vertices and adjacencies. So that matrix should tell us which are the adjacencies, which are the vertices, what are the adjacency connections between them. So the natural matrix coming to our mind is adjacency matrix. That was the beginning of spectral graph theory, the theory of matrices related with the graphs, the study of concepts of matrices related with the graphs. But as I told you, during these 84 years, during these 100 years, more than 156 different kind of matrices have been defined in connection with a graph. See, the primary matrices coming are distance matrix, Laplacian matrix, signless Laplacian matrix, then distance complementary matrix, distance complementary, like that, Zagreb matrix, like that. Several kind of matrices have been defined, and studies are based upon, are going on, which connect the spectral properties and the graph structure properties positively. And I told you that some negative also, because the study of matrices go in one way, which may or may not have any connection with the corresponding graph structure. But we cannot, we cannot ignore that, because maybe centuries after, or maybe after 10 years, some connections might have been found. That is how mathematics goes. So this problem, how we represent a matrix through adjacency matrix, and the ijth entry is 0 or 1 depending whether the corresponding vertices Vi and Vj are adjacent or not. And you can see that this adjacency matrix is defined based upon a labeling. See, am I audible? No, I am not asking whether I am audible, but I am asking whether I am going like a super fast express or nothing. See, the graph can be represented by means of a matrix, the adjacency matrix, whose ijth entry is Vi or 0 or 1, depending on whether the vertices are adjacent or not. Then these are the primary things coming to our mind. Given an n-vertex graph, we have a corresponding n by n matrix. There is a square matrix. So what can we study? The characteristic polynomial and the corresponding spectrum. So this is the conventional definition of the spectrum. The eigenvalues of the corresponding adjacency matrix form the spectrum. And this is the adjacency matrix of K2. This is adjacency matrix of K2, and the characteristic equation is found. The spectrum is found by solving the characteristic equation. But don't think that this part is also quite easy. See, I repeat, don't think that this part is also quite easy. Given a graph, we have the adjacency matrix, we have the n by n matrix. If find the characteristic polynomial, solve the characteristic polynomial, find the spectrum. So computation of spectrum is one aspect of spectral graph theory. Okay, but it is not so easy. That is why I think Sudev sir also asked whether we follow any computational tool to find the spectrum, because the graph is an n by n matrix, the characteristic determinant is an n by n determinant. Expanding that n by n determinant is a difficult problem, it's a complex problem. Even though we were able to find the nth degree polynomial, characteristic polynomial, solving an nth degree polynomial is the next hurdle. There is no easy way to do these two things. So the computation of spectrum of a graph is also somewhat a difficult problem, but we have some tools like MATLAB or Mathematica, but we cannot fully depend upon that, because that gives only numerical values, and the actual value may be different from that concept. For example, no adjacency eigenvalue can be a pure rational number. So for example, you cannot get 2.111 as an eigenvalue. There is no, if any eigenvalue is rational, then it should be an integer. But these softwares will give only some approximated values. So some people may feel that 2.1.1 is some 211 by 100 is a rational number, may be an eigenvalue, but no pure rational value is an eigenvalue. All rational eigenvalues are integers. So the computation of spectrum using some theory is still a difficult problem, but somehow we can manage that problem given a graph, because the way is direct. We have a graph, we can form the adjacency matrix. Anyway, we can expand a determinant, and we feel that we can solve that nth degree equation using the fundamental theorem of algebra is there. It guarantees at least. So one way is, even though it is difficult, one way is very straight. Now the question is whether the other way is okay. So can we address the other way? Given the spectrum, it is given that this is the spectrum of some graph, right? Then can we say that that is the only one graph with that as a spectrum? Means, can we characterize the graph from the spectrum? And two graphs are said to be co-spectral. In fact, isomorphic graphs have identical spectrum. So two graphs means two non-isomorphic graphs. We say two non-isomorphic graphs have the same, are said to be co-spectral if they have the identical spectrum. Isomorphic graphs are co-spectral. So this is the question, whether co-spectral graphs are isomorphic. See, suppose two graphs are co-spectral, whether they are isomorphic. Now we say we know that this is not true, but in the beginning it was believed that all co-spectral graphs are isomorphic. And see, this was in 1956, this was the first paper in which this problem was addressed. And in 1956, mathematician Pollack addressed the spectrum of a graph mathematically, and at the same year this problem was posed in this paper, whether co-spectral graphs are isomorphic. And we say a graph is characterized by the spectrum if any graph cospectral to G is isomorphic to G. So this is a problem. So this problem turns to the determination of isomorphic graphs. So we know that that is not an easy problem. To show that two graphs are isomorphic is difficult. If the problem to show that they are not isomorphic is quite easy, because you may find something in one graph which is not carried over the second one. You can conclude that. But even though you feel that these are same at every aspect, we cannot conclude that they are isomorphic. Is it clear? So this is the problem. So see, I would like to talk with very basic on this problem, so that I want you to do something on this. So I will give you very elementary thing, and if you have any doubt you can ask. So the mathematical community believed that all cospectral graphs are isomorphic and every graph is thereby determined by the spectrum. And 1 year after, Collatz and Sinkowitz produced a pair of graphs which are cospectral but not isomorphic. And this is, one is, see, actually one line is something is missing there in the presentation. See, in the PDF that C4 is there. The first graph is a C4 union K1 and the other is K14. See, these two have this identical spectrum but not isomorphic. So that belief collapsed. Every cospectral graph are isomorphic. That is not true. See, now this seems quite wonderful, because these are very simple graphs whose spectrum can be easily determined. But why then the mathematical community at that time waited for 1 year to find an example like this? That is quite wonderful, and actually that is the sourness, sweetness, bitterness of research. Now, so the search for cospectral graphs started. In the last example, one was connected and the other was disconnected. So now the question started whether we can find two non-isomorphic cospectral connected graphs. And this was the example on 3 plus 3 plus 6, 8 vertices, and some 1 year after on two cospectral non-isomorphic graphs with the 7 vertices were produced. So now you come to the question. Given the spectrum, how can we determine the graph? See, how can we determine the graph? If we can describe it fully. So we must say that the candidate is the candidate with this as a spectrum is him only, right? So for that we want to know what information we can have, what structural information we can have from the spectrum of a graph. So suppose the spectrum is given. That is a set of numbers, set of real numbers. See, because the adjacency matrix is symmetric, the eigenvalues are real. So we have a collection of real numbers. So with that set of real numbers, what information we can have? What information means what structural information we can have, so that you take a pencil, draw the graph, and you end up with a unique graph. This is the question. See, one thing we can have the number of vertices. If there are n vertices, n entries will be there because the corresponding matrix is an n by n matrix. It will have an n eigenvalues. So if there are n eigenvalues, the graph will have n vertices. So the number of vertices can be obtained from the spectrum, and some of the eigenvalues sum of the eigenvalues is 0. So that is very trivial. That is not at all a structural property, because this adjacency matrix being diagonalizable, there is a basis of Rn in which the matrix of this is diagonal, in which the diagonal entries are the eigenvalues. Sum of the diagonal entries is the trace, and the adjacency matrix is similar to this diagonal matrix, because these two are the same representation in two different bases. So these are similar, and similar matrices have the same trace. The trace of one matrix is sum of the eigenvalues sigma lambda I, and for the other trace is 0. So sum of eigenvalues is 0. So we can conclude that if there is a positive eigenvalue, there should be a negative eigenvalue. So if all eigenvalues are 0, okay, that is 0. See, otherwise the graph will have both positive and negative eigenvalues, but that will not shed much light into the structural design of the graph. Now the next one is the ijth entry of a raised to k. If A is the adjacency matrix, the ijth entry of a raised to k is the total number of vi vj walks of length k. So there is a result. You can prove it by mathematical induction that the ijth entry of a raised to k is the total number of vi vj. So consequently, trace of a raised to k is the total number of closed walks of length k. So that information we can get from the spectrum. We have the spectrum, then sigma lambda I raised to k, that is the trace of a raised to k. A raised to k is similar to that kth power of the diagonal matrix. So sigma lambda I raised to k is the sum of the diagonal entries of a raised to k. The diagonal entry of a raised to k, ith entry, is the total number of vi walks of length k, that is a closed walk of length k, and I runs from 1 to n. I think you people follow that. So the trace of a raised to k is the total number of closed walks of length k. So that information is vital. That information is significant in designing the graph. So at least we know what is the total number of vi walks of length k. So using this, see, when we apply this to k equal to 2, sigma lambda I square is equal to twice the number of edges. So the number of edges of a graph can be obtained from the spectrum, because the total number of vi walks of length 2, a vi walk of length 2 is obtained from an edge. Is it clear? A walk of length 2 is obtained from an edge. So if there is an edge, we have 2 vi walks of length k, because if vi vj is an edge, then vi vj vi is one closed walk of length 2, vj vi vj is another closed walk of length 2. So each edge contributes 2 to the closed walk of length 2. So sigma lambda I square is the total number of vi walks of length 2. Each edge contributes 2. So that is twice the number of edges, 2m. And similarly, this can be applied to higher powers. Sigma lambda I cube is 6 times the number of triangles, because when you consider a triangle vi vj vi vj vk, it will give 6 vi vj vi vi 6 vi vi vj vj vk vk walks of length 3. Pardon? 10 minutes? No. And sigma lambda I raised to 4. Thank you. Okay. Whatever thing I can tell in 30 minutes, I will tell. Sigma lambda I raised to 4. So that is a fourth spectral moment. These numbers are known as spectral moments. The second spectral moment is twice the number of edges. Third spectral moment is 6 times the number of triangles. But it is not easy to compute fourth or higher order spectral moments. So for that we have to go through the structure of the graph in a deep sense. So anyway, this is true, 2m plus 4s plus 8q and so on. Now, so these are the properties determined by the spectrum. We can determine whether the graph is bipartite or not. See, we will discuss it later if time allows. A graph is bipartite if its spectrum is symmetric with respect to 0. So corresponding to every eigenvalue, see if its negative is also an eigenvalue, we can conclude that the graph is bipartite. So slowly what happens is we are uncovering the secrecy of this graph very slowly. See, you have the number of vertices, number of closed walks, number of edges, number of triangles, whether the graph is bipartite or not, regularity. See, seeing up the spectrum, we can decide whether the graph is regular or not. That also we will discuss. And the number of components of a regular graph, that is actually the multiplicity of the greatest eigenvalue. But quite unfortunately, these things are not sufficient to describe the graph. Number of vertices, number of edges, closed walks, number of triangles, bipartite nature, regularity, number of components. See, all these things we can have from the spectrum, but we cannot determine the graph with these parameters. See, in some cases, if we have lesser number of vertices, or if we have a very comfortable structure of graph, then we can have. If we have a very comfortable structure, say for example, if the graph on n vertices has all its eigenvalues 0, then we have n vertices. Since all eigenvalues are 0, it cannot have an edge. So the only graph is the isolated vertex, because sigma lambda I square is equal to 2m. If all eigenvalues are 0, 2m is 0, m is 0. So it has no edges. So in such cases we can conclude. So suppose the G is a graph of diameter 1 and regularity n minus 1 on n vertices. If we don't know whether we get this information by looking on the spectrum. Suppose we got this. We have n vertices, regularity is n minus 1 and diameter 1. Then the only graph we can conclude that is the complete graph Kn. Like that we do. But these properties are not determined by the spectrum. See, whether the graph is connected or not, no information regarding the connectedness of the graph can be obtained from the spectrum. As you may remember the first pair of graphs. One is K14, the other is C4 union K1. One is disconnected and the other is connected. So connectedness cannot be obtained from the whether the graph is connected or not, that cannot be deduced from the spectrum. So since connectedness cannot be determined, Eulerian nature or Hamiltonian nature cannot be determined, number of cycles cannot be determined, even though the total number of closed walks can be determined, the number of cycles cannot be determined, because you see the first example. One is a C4 union K1, number of cycles is 1. The other one is a tree K14. So number of cycles is not a constant parameter based on the spectrum. Being a tree, one is a tree, K14 is a tree, the other is not. Diameter, you see the second or third example I showed. One graph has diameter 2 and the other graph has diameter 3. So diameter also cannot be determined. But yes, number of the distinct number of eigen. See, if G is of diameter D, then you should have at least D plus 1 distinct eigenvalues. So one thing we can have. So if the graph has only 2 distinct eigenvalues, the diameter cannot be 2. So this is our conclusion. Suppose the graph has diameter, say I am coming to that result. If the graph has 2 distinct eigenvalues, then it cannot have diameter 2 or more, because if it has diameter 2, it should have at least 3 distinct eigenvalues. So this is how we sort out and finalize that we got the convict. But that is not quite easy. See, the graph has one distinct eigenvalue of multiplicity n if and only if G is isomorphic to nk1, and the graph on n isolated vertices is thereby determined by the spectrum. And this is the result we discussed now. Suppose G is a graph of diameter d, then G has at least a d plus 1 distinct eigenvalues. See, almost all proofs in spectral graph theory has some 4 or 5 sentences. So it means almost all proofs are very easy to follow. So you consider, you suppose that the maximum number of distinct eigenvalues is d, and you consider the minimal polynomial. Then the minimal polynomial is a polynomial of degree at most d. So that starts with a raised to d plus etc. plus something equal to 0. So a raised to d can be expressed as a linear combination of lower powers of a. So every power of a can be expressed as a linear combination of lower powers of d. A raised to d minus 1, a raised to d minus 2, etc. the identity matrix. And you consider two vertices u and v at a distance d. That means there is a uv walk of length d. And there is no uv walk of length less than that, because that is the distance between u and v. So the uvth entry of a raised to d is at least 1, means non-zero. But a raised to d is expressed in terms in as a linear combination of I, a, etc. a raised to d minus 1, all whose uvth entry are zeros. So this do not tally. So it should have at least d plus 1 distinct eigenvalues. So the complete graph on n vertices is determined by the spectrum, because so the problem is like this. Given the spectrum of given the spectrum, we know that that is the spectrum of the complete graph. Our question is whether there is any other graph non-isomorphic to this but having this spectrum. So suppose H is a graph with the spectrum of the complete graph. See, this is the general type or general way to address this problem. We have the spectrum of a graph G. We want to know whether this can be determined by the spectrum, means whether this G is the unique graph with this spectrum. We suppose H be a graph with this spectrum. Then the number of vertices of H is known. Number of vertices of H is n. Number of edges of H is known. From the spectral values, number of edges is NC2. So from there itself we can conclude that a graph on n vertices with NC2 edges is nothing other than the complete graph. So H is identically equal to the complete graph. See, otherwise you see the spectrum of Kn. Spectrum of Kn is n minus 1 with the multiplicity 1 and minus 1 with the multiplicity n minus 1. So it will have two distinct eigenvalues. Then by the last result, it cannot have diameter 2 or more. So H is a graph. If H is cospectral with G, then H should be a graph with diameter 1 on n vertices. And that is then nothing other than the complete graph. N vertex graph with diameter 1 means every two vertices are adjacent. So, and this is the Perrin-Frobenius theorem for k-regular graph. If G is a connected k-regular graph, then k is an eigenvalue, and the multiplicity of k is 1. And if a is the, so how much time remain? 20 minutes. If a is the adjacency matrix and x is an element in Rn, then this number, this is what is known as the Rayleigh quotient, x transpose Ax divided by x transpose x. And the Rayleigh principle says that lambda 1 is the supremum among the Rayleigh quotient, and the minimum eigenvalue lambda n is the infimum among the Rayleigh quotient. And we have using by taking x as the all one vector, we can prove that d bar, which is equal to 2m by n, is always less than or equal to the greatest eigenvalue, because the greatest eigenvalue will be greater than or equal to the corresponding Rayleigh quotient Rx, because lambda is the supremum. If lambda is the greatest eigenvalue, then lambda is the supremum among Rayleigh quotient. You consider one particular Rayleigh quotient with x as the all one vector. So, do I need to write? My only aim is whatever we tell within this very limited time, even though it is short, it should be beneficial. See, otherwise it will like overhead. See, consider the adjacency matrix capital A. I think that is very easy to follow. You consider the all one vector x 1 1 1 1 1. So the Rayleigh quotient will be 2m by n. In that case, the corresponding Rayleigh quotient will be 2m by n. So 2m by n will be less than or equal to lambda. And the equality holds only when that x is an eigenvector. In that case, x transpose Ix by x transpose x, the Rayleigh quotient is in fact actually equal to lambda. So the equality holds if and only if G is regular. See, I am not giving you the proof in detail because time is not permitting me to do so. So we have this result. G is regular if and only if G is a graph with the greatest eigenvalue R, combining the previous one. G is regular if and only if R is equal to sigma lambda I square by n. Then given the spectrum, see, because sigma lambda I square is equal to twice the number of edges 2m. So the last result says the equality holds if and only if the graph is regular. Right? So the regularity can be immediately decided. Given the spectrum, we can say whether the graph is regular or not. That was described earlier. So this is one property we can determine whether the graph is regular or not. So the cycle graph Cn on n vertices is determined by the spectrum. So you consider the spectrum of the cycle graph, that is 2 cos 2 pi j divided by n. You should leave that. That can be taken from any elementary book. See, consider the cycle graph. Suppose H is a graph having this as the spectrum. Then H is a graph on n vertices. The cycle graph has 2 as its eigenvalue because 2 is its regularity. And the multiplicity of 2 is 1. So H is also a graph which is having 2 as the greatest eigenvalue with multiplicity 1. And from the spectrum, you compute sigma lambda I square by n. Sigma lambda I square is twice the number of edges. Twice the number of edges is 2n divided by n, that is 2. So H is also a 2 regular graph. So we have this information. H is a graph on n vertices. It is 2 regular. Multiplicity of 2 is 1. If multiplicity of 2 is 1, then it cannot have cycle components. If there are more than one cycle component, then the multiplicity of 2 will be that much. So this is the information on H. H is an n vertex graph. Regularity 2 connected. So the only graph is Cn, no other choice. So H is also Cn. So the cycle graph is determined by the spectrum. Now, this is an interesting question. See, suppose G and H are determined by the spectrum. Whether their union can be determined by the spectrum. We may feel that if two graphs are determined by the spectrum, then their union has the union as its spectrum. If G and H are two graphs, then spectrum of G union H is spectrum of G union spectrum of H. G is determined by the spectrum, H is determined by the spectrum, so the structure is known, but that is not true because C4 is determined by the spectrum. Cycle graphs are determined by the spectrum. K1 is determined by the spectrum. But their union, C4 union K1, is cospectral with K14. So this is not true. So this is also an open problem. Under what conditions union of two graphs which are determined by the spectrum can be determined by the spectrum? And this question can be asked to other operations also. See, suppose G and H are determined by the spectrum. Under what conditions G join H, G Cartesian product H, G other NEPS product of graphs are determined by the spectrum. And coming to regularity 3, there are no co-spectral cubic graphs up to 12 vertices. Up to 12 vertices, there are no pair of co-spectral cubic graphs. That means all cubic graphs up to 12 vertices can be determined by the spectrum. But on 14 vertices, there are 3 pair of co-spectral cubic graphs. And the number increases. With 16 vertices, there are more than 142 pairs of co-spectral graphs and one triplet of cubic graphs. One triplet of co-spectral cubic graphs. And 2 regular graphs are co-spectral if and only if their complements are co-spectral, because the spectrum of the complement can be well determined from the spectrum of a regular graph. So if 2 graphs are co-spectral, then their complement also have the identical spectrum. So an irregular graph is determined by the spectrum if and only if its complement is also determined by the spectrum. So that immediately gives us the cycle complement is determined by the spectrum. And a graph is bipartite if and only if the spectrum is symmetric with respect to 0. That is an easy proof. If lambda is an eigenvalue with an eigenvector, you can prove that minus lambda is also an eigenvalue. So the spectrum of the bipartite graph is symmetric. So seeing the spectrum of the graph, we can decide whether the graph is bipartite or not. And so the complete bipartite graph KMM on 2m vertices is determined by the spectrum. And this is the definition of interlacing of eigenvalues. And B is a principal submatrix of A. The adjacency matrix of any induced subgraph will be a principal submatrix of the adjacency matrix. And so by interlacing theorem, the spectrum of the induced subgraph will interlace the spectrum of the original graph. And these are some preliminary data needed to prove that the path graph is, so far we have discussed regular graphs, cycle graph, complete bipartite graph, KMM. And unfortunately, this is not the case with the general complete bipartite graph, KMN. KMN cannot be determined by the spectrum. And see, using this in a graph without cycles, in a graph without 4 cycles, the number of closed walk of length 4 equals twice the number of edges plus 4 times the number of induced path of length 2. Closed walks of length 2. Each edge contributes 2 closed walks of length 4. Each induced P3 contributes 4 closed walks of length 4 as described here. So using this, we can show that the path graph is determined by the spectrum. See, we have the spectrum of the path graph. See, suppose H is co-spectral with the path. Then from the spectrum of the path is Pn is 2 cos pi j divided by n plus 1. So no eigenvalue will be 2. All eigenvalues are less than 2. So our immediate observation, the interlacing theorem says, cycle cannot be an induced subgraph of H, because cycle has 2 as its eigenvalue. So interlacing theorem rules out the possibility of a cycle. So our immediate observation is H is acyclic. H is acyclic, has n vertices and n minus 1 edges, because path has n vertices and n minus 1 edges. So any graph co-spectral with the path must also have n vertices and n minus 1 edges, because these are the properties we can deduce from the spectrum. So H is acyclic with n minus 1 with n vertices and n minus 1 edges, and an acyclic graph with n minus 1 edges on n vertices is a tree. So our immediate conclusion is H is a tree. Now K14 cannot be an induced subgraph, because K14 cannot be an induced subgraph because K14 also has 2 as its eigenvalue. The eigenvalues of Kmn, the complete bipartite graph Kmn, are plus or minus square root of Mn and zeros m plus n minus 2 times. So you consider K14. The eigenvalues are plus or minus square root of 4, plus or minus 2. So 2 is an eigenvalue. But path graph has all its eigenvalue less than 2. So interlacing theorem says this K14 cannot be an induced subgraph. That means H cannot have a vertex of degree 4 or more. So all vertices of H are of degree less than or equal to 3. Now we can show that there cannot be more than 2 vertices. There cannot be more than one vertex of degree 3. Suppose it has a vertex 2 vertices of degree 3. Suppose H has 2 vertices of degree 3. I will use this board at least once. So if H has 2 vertices of degree 3, then it should have a structure, an induced structure like this inside H, if it has 2 vertices of degree 3. But then we can see that the spectrum of this particular graph contains 2 as an eigenvalue with the eigenvector 1 1 2 2 2 2 1 1. With this eigenvector, this particular graph has 2 as an eigenvalue. So this cannot be an induced subgraph of H. So H cannot have more than one vertex of degree 3. So what we are doing is we are chiseling out all other possibilities on this H. We don't know what H is, but we have some information on H. H is a tree. H cannot have 2 vertices. H cannot have a vertex of degree 4 or more. H cannot have 2 vertices of degree 3. So now suppose H has 1 vertex of degree 3. So H will look like something like this. But the total number of closed walks of length 4 in Pn should be same as the total number of closed walk of length 4 in this graph also, because the spectrum are identical. So sigma lambda I raised to 4 is constant for both Pn and this H. For Pn, we have that formula, the total number of closed walk of length 4, that is 6 into n minus 1. When we apply that here, you count the total number of closed walks for this structure, then total number of closed walks for this structure plus total number of closed walks for this structure plus the total number of closed walks generated from this structure and this one. That amounts 6n plus 6. 1 is 6 into n minus 1. So that is impossible. So H cannot have a vertex of degree 3. So you write down all these. H is a graph on n vertices with n minus 1. It is a tree having no vertices of degree 4, have no vertices of degree 3. What else then? H is Pn. So this is how, see, now this problem is gained momentum. It is not as easy to say that the isolated vertices are determined by the spectrum, complete graphs are determined by the spectrum, cycle graph is determined by the spectrum. It is not as easy as saying as that. Now, using the same, tree is said to be star-like if it has exactly one vertex of degree greater than 2. A tree is said to be star-like if it has exactly one vertex of degree greater than 2. And Gutman and Lepovic proved that no two star-like trees are co-spectral. So using this, and also the fact that we have already characterized the path graph using it as a spectrum, we can show that this graph Zn obtained by attaching a K2 at the second vertex or attaching a K13 at the end vertex of Pn. The graph Zn, this is determined by the spectrum, because this is a star-like graph and no two star-like graph trees are co-spectral. Already path is identified by the spectrum, so using that Zn is also determined by the spectrum. So these are the kinds of problem. Given a graph, can we determine the graph uniquely? See, a general version of problem recently seen is that given the spectrum, at least can you determine what is the total number of graphs having this as a spectrum? So what is the total number? So given the spectrum, can the k graphs be determined by the spectrum? We are addressing the problem when k equal to 1. Right? Now in 2010, these people conjectured that the friendship graph Fn is determined by the spectrum for every n greater than or equal to 1. The friendship graph is join of nk2 with the k1, or n triangles identified at a single vertex. And after 5 years, they proved that the friendship graph is determined by the spectrum except for n equal to 16. For n equal to 16, friendship graph and this graph are co-spectral. See, K3 join with the 5 isolated vertices, and these 5 isolated vertices are then next join with the 5 remaining isolated vertices, and a perfect matching is removed. So this is the construction, and 10 K2. So K3 join K5, a perfect match removed join with the K5 complement, union 10 K2. This is the graph. See, F16, the friendship graph F16 consists of 33 vertices. 2n plus 1 vertices are there in the friendship graph with the Fn. Now, so this is how the problem goes. So the open problem is which graphs are determined by the spectrum. This was the problem raised by Hammers in his 2003 paper, while addressing a problem raised by Alan J. Schwenk in 1973, and he conjectured that almost all trees are co-spectral. Means no trees can be determined by the spectrum when you go to the collection of trees with the specified number of vertices. Okay, thank you. These are the references.
Yeah, we are very thankful to you, sir. Nice presentation. So he gave very good motivation to work in this particular area. So first of all, are there any questions from the audience? If you have any questions, then.
Thank you, sir. It was a wonderful session. Sir, I have a small doubt. In the beginning of the session, you said spectrum cannot be a rational number other than the integer. Suppose if we are finding the spectrum of a graph using some software, say SageMath.
Yes.
And if I got the spectrum as a rational number, which are not integers, then how can we find, we won't take those values, no? If they are not integers, if the spectrum, if they are not integers, then we won't consider it as spectrum, no? Then how will we find the spectrum of that particular graph?
So that is why the problem is difficult.
Okay.
Okay. So we have to develop some tools.
Okay.
See, this question can be answered only when the adjacency matrix took a nice form, a comfortable form, or some nice block form. We have several reduction techniques if the adjacency matrix is in a block form, Or there is another technique is the eigenvalue eigenvector technique.
Okay.
So you have to predict the eigenvector and then compute the eigenvalue.
Okay.
See, anyway, no rational eigenvalue. All rational eigenvalues are integers.
Okay.
See why? Because the answer is simple. Because you consider the characteristic polynomial, there is a monic polynomial.
Yeah.
If p by q is a rational number, q must divide 1. So there is no pure rational numbers of the type of p by q with q not equal to 1. So we see why I tell this particular problem here it is. I got a paper for reviewing. So in that energy is computed after computing the eigenvalues using a MATLAB or something like that. So okay, see we can assess or we can predict the neighborhood of the eigenvalue.
Yeah.
So suppose you get 2.11 and if you are interested in that problem and not in the exact eigenvalue, you can use that software.
Okay.
So suppose you want to tell that the eigenvalues lies between say 2 and 3. And you are getting eigenvalues 2.1, 3.12, etc. And you are then you need not concentrate on that specific values. You just only want to say that the eigenvalues lies between 2 and 3.
Okay, sir. So can I say if the eigenvalue that I got from software is say 2.111? So can I take the eigenvalue as
No. You can write it only as an approximation of the eigenvalue, not the eigenvalue.
Okay. Okay. Thank you, sir.
Any other questions? I think you are come across that sir told that rational root theorem. That sir gave proof also. Oh, yeah. Any other questions?
So thank you, sir.
Thank you, sir.
So see that you are presenting say a graph is there. You are constructing adjacent matrix, and then from that adjacent matrix you are preparing a polynomial, and then you are solving that polynomial by using certain methods, and then you are finding the eigenvalues. Then you are coming back to identify the nature of the graph. No.
Yeah.
So from simple things you are going to the harder one, and then you are again trying to find out which the characteristics of the graph like that. So basically I'm joking about this, but if the eigenvalues are given, then we are trying to identify the type of graphs or nature of the graph like that. No.
Pardon?
So from the if the eigenvalues are given,
yes,
then from that set of eigenvalues we are trying to identify the type of the graphs.
Yes.
But if we consider the adjacent matrix or graph, then we are going to construct a polynomial. Then we are trying to solve that particular polynomial and then finding the eigenvalues and then coming back to identify. So this is not the way. If the eigenvalues are given, then we are trying to find out the nature of the graph or like that. Okay, I am just joking with this. So this is the problem, but I just want to talk regarding the computational part. So see that if you use the MATLAB actually you are using only the numerical values. But if you go for Mathematica or MapL, that kind of software, that software you are using your symbolic computation. So if the graph is given, then from that graph you can construct the polynomial in terms of variables, in terms of lambda or x like that. So you can construct the polynomial using MapL or Mathematica. Okay, so integrate polynomial that particular software will give. But see that all these software based on the numerical methods. So if you read the numerical method to construct the polynomial, so we are using the determinant of a minus lambda. That one is the conventional method to find out the characteristics polynomial. Okay, but there is another method, numerical methods. That method you directly construct that particular polynomial, and using the numerical methods you can find all the eigenvalues, whatever may be the degree of the polynomial. It may be 100, it may be 200. So that numerical methods gives the eigenvalues for any graph. Also MATLAB also determines the eigenvalues for any. If you give the your graph as an input in MATLAB, then that MATLAB directly gives the eigenvalues. Just write EIG of G. If the graph is given, adjacent list or adjacent matrix, then EIGG gives the all eigenvalues of the graph. That comment is available for the recent development of the MATLAB. The new version of the MATLAB gives the eigenvalues. But what is the difficulties is that he has already mentioned that one, that eigenvalues are approximate eigenvalues. It may be say 16 digit correct up to 16 digit. It may be correct up to your 32 digits or 32 bits or up to 64 bit, but it's is the these eigenvalues are the approximate of the original one. So this is the drawback of the software. The software computes all the eigenvalues. There are a lot of numerical methods, but that eigenvalues are not exact. So this is the main difficulties. Yes. So for that reason, we are characterizing the your different type of methods or characterizing the graphs like that. But MATLAB actually findings all the eigenvalues. But better to use Mathematica or MAPL. That one computation computes the symbolic operators also.
See, that can be used. Suppose you are dealing with a chemistry problem or a physics problem or a vibration problem or some electron energy problem, and you want to have only an approximated value, then you can use Mathematica or MATLAB to get the approximated value. But as Sir mentioned, Mathematica will give you symbolic values of eigenvalues if you give that matrix properly. See, for yes, in logical, in symbolic notation. See, usually people what they are doing is they are drawing a graph, writing the adjacency matrix there, and inputting that in MATLAB and getting the results as approximations and producing papers claiming that this is the eigenvalue and this is the energy. That I mentioned earlier. I got a paper for reviewing, and the paper itself says that the graph is having rational energy, and they computed that some rational number p by q as energy. See, no rational number can be an energy, only integers. If the energy is a rational number, it should be an integer. Because somehow this energy is also an eigenvalue of a certain kind of graph. You take the Cartesian product of several copies of some particular graph. This energy will be there an eigenvalue. Then that rational number cannot be an eigenvalue. If the rational number is an eigenvalue, that is an integer. So don't get confused. When you use non-symbolic numerical computation, so you treat that these are the only approximated eigenvalues, not the real eigenvalues. So for example, you may get 1.414, something like that as an eigenvalue, but the actual value may be root 2. So irrational numbers can be eigenvalue, no issue. Yes. Right? But you cannot say that 1.414 is the eigenvalue. We cannot say like that. Thank you.
Yeah, thank you very much. Are there any other questions? If
Any questions?
Yeah, if not, we'll thank the speaker one more time for his wonderful motivation. Thank you.
Thank you, Satyanarayana sir, for chairing the session. Now I invite Satyanarayana sir to honor the speaker and Indulal sir to accept our token of gratitude. Thank you, Satyanarayana sir and Indulal sir. We have come to an end to this session. The valedictory function will start soon.
Good evening, everyone. We are about to begin the valedictory function of International Conference on Graph Theory and its Applications, ICGTA 2024. Let us invoke divine blessings as we begin with a prayer. I invite Ashwati and Naseem for the same.
ദേവപാവനമാക്കൂ ഞങ്ങൾ തൻ ജീവിതമെന്നും ഈ വിധം കൊച്ചു പൂവിലും പുഞ്ചിരിക്കും അത്ഭുതമാമി കൈകളാൽ ദേവപാവനമാക്കൂ ഞങ്ങൾ തൻ ജീവിതമെന്നും ഈ വിധം ജ്ഞാനം സംസ്കാരം സ്നേഹമെന്നിവ നീ അരുളുക ദൈവമേ അന്ധകാരത്തിലാണ്ട ഞങ്ങളെ പൊൻതിരി നീ കൊളുത്തണേ ദേവപാവനമാക്കൂ ഞങ്ങൾ തൻ ജീവിതമെന്നും ഈ വിധം കൊച്ചു പൂവിലും പുഞ്ചിരിക്കും അത്ഭുതമാമി കൈകളാൽ ദേവപാവനമാക്കൂ ഞങ്ങൾ തൻ ജീവിതമെന്നും ഈ വിധം.
Thank you. To officially commence the function, I now invite Dr. Tintimol Sunny to deliver the welcome speech.
Respected Principal, Reverend Father Dr. Julie Andrews CMI, our esteemed advisory committee members and resource persons of this conference, Professor Sudev NK, Professor G. Indulal, our plenary speaker, Professor Ayman Badawi, Head of the Department and Convener of ICGTA 2024, Dr. Sinavi, Professor Madhu Mangalpal, Dr. A. Satyanarayana Reddy, faculty members and participants around the country and dear students. Good afternoon to all. It's with great pleasure and honor that I stand before you today at the closing ceremony of this International Conference on Graph Theory, organized by Postgraduate and Research Department of Mathematics, Christ College, IRINJALAKUDA. Over the past 3 days, we had the opportunity to immerse ourselves in the fascinating world of graph theory. I believe this seminar has greatly inspired the participants by deepening their understanding of recent advancements in this area. Since becoming a research department, this is the second consecutive international conference organized by our department. Now, none of this would have been possible without the unwavering support of our management. I take this opportunity to welcome our principal, Reverend Father Dr. Jolie Andrews CMI. His visionary leadership and support have been pivotal in making this conference a reality. Father, your commitment to fostering academic excellence continues to inspire us all. It's with great pleasure that I welcome you, Father, to this event. I'm delighted to extend a warm welcome to Professor Sudev NK, the advisory committee member of our conference. The success of this conference, from the selection of this group of outstanding resource persons to all its facets, is largely attributed to the invaluable suggestions and support from Sudev sir. We are also thankful for your enriching sections and discussions that have inspired all of our participants. Welcome you, sir. Next, I would like to express my gratitude to Professor G. Indulal, the principal of St. Aloysius College, Edathua, to this valedictory function. We understand the demands on your time as a principal, and we are truly grateful for your presence today. Your invaluable suggestions and support have greatly enriched this conference, and we are especially thankful for the engaging academic sections you conducted. With immense pleasure, I welcome you, sir, to this gathering. I'm honored to welcome our distinguished plenary speaker, Professor Ayman Badawi from Sharjah, to be with us these 2 days. Thank you for crossing borders to share your expertise at our conference. Thank you and welcome you, sir, to this gathering. It's my pleasure to extend a warm welcome to the convener of ICGTA 2024 and head of the Department of Mathematics, Dr. Seena V, whose leadership and vision have been pivotal in the success of this international conference on graph theory. Your tireless efforts in organizing this event and bringing together such a distinguished group of resource persons and participants are truly commendable. With great pleasure, I welcome you, Seena Miss. Next, I would like to take a moment to acknowledge and warmly welcome our esteemed resource persons, Dr. S. Satyanarayana Reddy, who has been with us throughout this conference, and Professor Madhu Mangal Pal, who have shared their invaluable knowledge with us. Their contributions have elevated this conference and provided us great insights. Welcome, sir. Next, I take this opportunity to welcome all the participants who have joined us from different parts of our country. Your enthusiasm and active engagement have enriched the discussions and making this conference meaningful in spirit and scope. Now, I would like to welcome the faculty members and students of our department. Their hard work and dedication, meticulous planning, and tireless efforts have ensured the success of this conference. Once again, I warmly welcome each and every one of you to this valedictory function. Thank you.
Thank you, ma'am. I also welcome Tindimol Miss to this gathering. Next, I invite our esteemed principal, Reverend Father Dr. Jolie Andrews, to give the presidential address.
Dr. Ayman Badawi from UAE, Professor Dr. Sudev, Professor from Christ Team to be University, Bangalore, Professor Dr. Indulal G, Professor and Principal of St. Aloysius College, Edathua, Dr. Seena V, the HOD and the General Convener of the Department of this National International Conference, Dr. Tindumolti, who gave the welcome address, all the dignitaries, research scholars, and my dear friends. We are nearing the end of this International Conference of Graph Theory and its Application, ICGTA 2024, which has been organized by Postgraduate and Research Department of Mathematics in collaboration with Kerala State Higher Education Council and Kerala Mathematical Association. So here I would like to specifically congratulate the Department of Mathematics, Dr. Sinavi, the HOD, Dr. Joju, KT, the coordinator, all the faculty members of Department of Mathematics for organizing this international conference. This is the second year, consecutively the second year. So I hope that we will be having an international conference in the next year too. As I said in the inaugural address, as we say in Malayalam, രണ്ടൊത്താൽ മൂന്നൊക്കും എന്ന് പറഞ്ഞ പോലെ. So we think that by getting the insights all which we have gained by this international conference, rightfully we will be having a third session of this international conference probably in the next year, almost in the same time. I know the Department of Mathematics would do it in a wonderful manner because of the able leadership, joint coordination, and the wonderful teamwork which they have been exhibiting all through the time. I especially place on record my special appreciation towards all the plenary speakers and resource persons. Many have come here in the offline mode and some have engaged in the deliberations in online mode too. A special appreciation to each one of them. I especially thank Ayman Bedawi, who was here with whom I chat and I talked about different aspects, who is at present who is teaching in the Department of Mathematics and Statistics from American University of Sharjah, UAE. Dear friends, as we come in this back end of this conference, I would always say the intellectual deliberations which we had may have its outcome as research publications, perhaps. It should help us to come forward with a new and, I would say, some practical applications in which we can place our graph theory in an ingenious manner. Only if we have such a reasonable output and outcome as a result of this international conference, because of these deliberations, I would say the real success will really matters. So my humble request to all the participants of this international conference is that by all these deliberations, may you not be just satisfied with a poster or a paper publication. Rather, you work more about it as you engage the different scenarios and different aspects of this graph theory by getting yourself immersed in this international conference. May you, with the enlightenment which you gained by this participation in this international conference, be able to produce an avalanche of, I would say, publications, research, I would say suggestions, and I would say even, I would say, if in the practical realms, that may lead even to patents if it has been given to the practical considerations. So what really counts would be the output which you give, because you got such an insightful inputs which are received by these 2 or 3 days. So let us count on the outputs, because that has been very important. So get to my word, let the wonderful interactions, the friendships, I know you would have enjoyed the Christ campus. Campus were more than around 34 feature films, not just in Malayalam, have been more than 2 days have been were here. You would have seen the different aspects of the campus, different, I would say, initiatives of this campus, well and good. The friendship which are developed to the faculty members with one another, all should help you to work together jointly more and more, so that as a result of this conference there may be more deliberations, joint collaborations, more research outputs, more, I would say, creative outputs that would be given, especially to the education scenario, to the research scenario, and one step more in the wonderful, I would say, ocean of this graph theory, which I would say has got a wonderful surplus of wealth hidden there in this graph theory dynamics. So may you be able to do that. My special appreciation to every one of you. Enjoy the evening. Let what you cherished here may live for a long time, and may it be there as a wonderful research outputs. Have a wonderful time. Congratulations once again to Department of Mathematics. We have got aided and self-financing, both working together hand in hand. To all of you, all the research scholars who have been here, all the, I would say, big plenary speakers and resource persons who interacted with you. Have a wonderful time. Thank you. Thank you so much.
Thank you, Father.
To address the gathering, we are honored to have with us Professor Ayman Badawi. I now invite you, sir, to share your thoughts with us.
Usually my voice is so loud, I don't need this, but anyway, I will use it. Thank you very much for having me here. I start thanking Dr. Sina for inviting me. This is my first time in this college. I think I mentioned to some of you that in the last 7 months, I visited Kerala 3 times. One time in March, one in May, and now I'm here. So it's good to be here. And if I have to say something about this conference, it's very well organized. That's definite. I mean, there is no two will disagree on that. It's very organized, and people are friendly. I have students come to me, either talk to me about their research, or they want to take a picture with me. When I eat, he's not here. He always come and can we bring you something more, sir? And you feel like, you feel like you are loved to be here. And this is nice. And also another thing different, the number of the postgraduate. This conference has many postgraduate students. Because usually other conferences, I will be talking to people like me. We are well established and, but here like you have people like me, but we have more postgraduate. And I think if you think about it for a minute, what we need, I want postgraduate to listen to me so they know what we're doing, and this is how they help themselves in their career and what to do, what kind of problem we work. I don't want somebody to listen to me who's in my area. I mean, we talk. So that I find this is kind of interesting, the number of the postgraduate student in this conference. Thank you again, and congratulations. And it seems to me, I heard the principal that you're going to have a third one. Thank you.
Thank you, sir.
We are equally delighted to welcome Dr. Sudev N.K., who has been a guiding force throughout the conference. I now call upon Dr. Sudev to speak to the audience.
Respected dignitaries on end of the dais, dear teachers, distinguished resource persons, and my dear researchers. Of course, this is one of the best conferences I have ever attended, participated as just a participant and as a resource person. The arrangements, ambience, the hospitality, I heard that the accommodation also, all were really outstanding. So congratulations for the organizing team and especially the management for the support for organizing such a nice, wonderful conference. And advance best wishes for the 3rd edition of International Conference on possibly graph theory and applications. Right. All the 3 days I were here, I have seen all the proceedings of, I have witnessed all the proceedings of the conference, and it was really, academically also, it was really wonderful. All the almost 30 contributory papers were amazing, and I have a little bit of comments about that also. Right now or after that? That time. Okay. So once again, congratulations and best wishes for the future activities of the department. Okay, thank you.
Thank you, sir, for your warm words.
We also have the privilege of hearing from Dr. Indulal ji, a distinguished member of the Conference Advisory Committee. I now invite you, sir, to address the gathering.
Respected principal, Ayman Badawi sir, and other dignitaries on and off the dais. So even though I came very late by today, I too endorse the comment by Badawi sir and Sudev sir that this conference was arranged in a very meticulous manner. And that is why the principal offered that the third international conference is also, we are also hosting the third international conferences. See, when such conferences are organized, our primary aim is to motivate the audience, the students, the researchers, and propagate the message that mathematics is the essential thing to run the world. Like Galileo remarked in the 16th century that the book of nature is written in the language of mathematics. Mathematics evolved from the very primary, primitive, practical applications. Now, as I mentioned in my talk also, crossed all limits and crossed all boundaries, and mathematics stands at the top of the world. The world is driven by mathematics. Like I think some people know Malayalam. In Spadigam film, Tilagan, the character Tilagan says, Bhugolathinte Spandanam, mathematics-ilana ennu parayunnu. The heartbeat of the world lies in mathematics. See, we cannot feel wonder when we see the infinitude applications of mathematics in practical walks of life. Some mathematicians believed that whatever we are going to find will not find any application, and it should not find any application. One among them was G.H. Hardy, the godfather of Srinivasa Ramanujam. He invented, researched, and found some mathematics. He believed that it will not find applications in practical life. But after just 10 years, the genetics people used his theory to mathematically model their results and other predictions. So this is how mathematics goes. So I really congratulate the Department of Mathematics for choosing graph theory as the main theme of this conference, because graph theory, Leonhard Euler sowed the seed in 1736. Wouldn't have dreamed that this kind of a vast ocean of result is dancing, making waves in the world of mathematics. Because graph theory, I think Satyanarayana Reddy sir also mentioned in his talk or in chats that graph theory can be used to solve complicated problems in number theory. See, as we have seen the proof of Fermat's little theorem using very few sentences in graph theory, and like that. So this is how what I said is the joining of hands between branches among mathematics and branches outside mathematics. And so I really congratulate the department for choosing this as the main topic, as the topic of this seminar. Also, being researchers, teachers, experts, participants, it is our main mandatory duty to propagate the significance of mathematics to common people. Based upon that aim, the Kerala Mathematical Association emerged. And Kerala Mathematical Association uses their almost all platforms to popularize mathematics. So in order to popularize mathematics, we should know the applications of mathematics we are studying, teaching, and propagating. So this kind of platforms, we hope that this kind of platforms will help us in enrich ourselves in such fields also. So I am personally thanking Dr. Sina and Shindo sir and Tintu Miss for giving the support. See, I am not here for the first time. Even though I am physically coming here for the first time, I virtually came here once at the Chakramakal Endowment Lecture Series in the last some couple of years back. So anyway, I thank the organizers for giving me a chance to share some ideas with you, and also to interact with Satyanarayana Reddy sir and Madhu Pangal Pai sir, because these people are very celebrities in the field of graph theory and number theory. But this is for the first time I am seeing them. So this platform, also Ayman Bedavi sir also, we have acquaintances, but this is for the first time we are seeing physically. So this platform gives that opportunity also to see, to interact, to acquaint more with the dignitaries, experts of this field. So thank you once again. Thank you, and I wish the third international conference, as Sudesh sir also said, on graph theory will be inaugurated next year. Thank you.
Thank you, sir.
Now we have come to one of the most anticipated moments of the conference, the announcement of the Best Paper Presenter Award. To do the honors, I would like to invite Dr. Sudev NK to the stage. He will be announcing the winner. Over to you, sir.
Before announcing the results, I would like to call Dr. Satyanarayana Reddy also. Sir, come. Anjali madam is not here now. She has left. All the 3 days we three were together discussing and sometimes fighting to find out. So when you were enjoying the delicious lunch there, we were under the fight here to decide the first spot. Mathematics, actually I remember one quote, life is good only for two things. Life is good only for two things: for learning mathematics and for communicating mathematics. Why communicating mathematics is important? Because do we have any universal language? Father, you are not from English department, right? It's okay. Do we have any universal language? That also differs. Mathematics is the only universal language. Mathematics is the only universal language. Don't agree? Because it doesn't have any accent, doesn't have any regional differences. It has the very particular, rigorous, meticulous representation, symbolic representation, right? It has its own advantages and disadvantages also, right? The advantages, anyone can take up that. But while communicating, we have to be very particular about the grammar and structure of mathematics clearly, very well. So while doing research, communication in the sense writing, presenting, anything, any type of communication, we have to follow the meticulous grammar of mathematics. How can we gain that? How can we gain that? Research is, I usually say to my scholars, 80% plus is reading, intense reading. Only 20% or less will be innovation. So you have to read in a very intense manner, keep on reading. We have an advantage, we have a fortune that we carry our laboratory together with us, right? Wherever we go, while sleeping, while eating, while traveling, every time our laboratory is with us, right? Isn't it? So utilize it very carefully, learn, read, and finally only the innovation comes. So you have to read a lot. By reading, you will improve your writing, writing skills, presentation skills, mathematical communication in general, isn't it? So that part, all as mathematics researchers, you all have to take care. Then only you will be good presenter, you will be a good presenter, you will be a good communicator, and after all, will be a good mathematics enthusiast. And mathematics enthusiast is the apt word. And finally, the mathematicians, right? Yeah. So all 27, 28 presentations we have very meticulously, very carefully analyzed, and it was so difficult for us to restrict to 2, and sometime we asked also, can we have 5 or 6 prizes, but the organizers did not agree. So after a long fight, as I said, when you were enjoying lunch there, we were fighting here, and after a long fight, and finally we reached a conclusion. Shall I announce? Only 2, right? Still? The second prize goes to Farzana Praveen. The presentation was very confident, the topic was interesting, and almost all necessary procedures, official procedures were followed in the presentations. It was a little application oriented.
I now invite Professor Ayman Badawi to give away the Best Presenter Award. Second Best Presenter Award.
And the Best Presenter Award goes to Jinu Mary Jameson. She is working as a faculty member in SB College, Changanashwari. The other person, Farzana. Farzana, are you working somewhere or doing research? You have started research in Nirmala College, Coimbatore. And yeah, one thing is that she is working under Dr. G. Indulal in spectral graph theory. Yeah, that's also a pleasant thing. So one or two points I have to mention to all researchers is that you have to be very particular about giving due credits to the existing works. That part I found missing in almost all presentations. Whenever you extend some existing studies, please do recognize the original contributors by giving due citations. Okay, thank you. And be very particular about, be very meticulous about communicating mathematics in its own way. Since as I told earlier, mathematics is the only universal language exists. Right? Thank you.
Congratulations to all the winners and thank you, dignitaries.
Insights from the participants is invaluable to us. We invite you to please come forward and share your feedback about the conference. Please feel free to express your views on what you have enjoyed and any suggestions that you may have.
Good afternoon, everyone. I am Sinimol from Alappuzha, Kerala. Actually, I feel it is an honor to be a part of this type of an exceptional international conference in my place, organized by the PG department, PG and Research Department of Mathematics, Christ College, IRINJALAKUDA. Here in this conference, I highlight that the simplicity, humility, and the warm hospitality displayed by the organizing committee. It is appreciable. The coordinator of the program, the coordinator at the department head, Dr. Sinavi, and the dynamic team behind her, really appreciable because their tireless effort made this international conference a grand success. Also, about the talks, we are enriched with the innovative ideas shared by our resource persons, engaging sessions and open problem sessions, and also memorable events, especially in the Sneha Thiram beach visit, the cultural programs provided, the conference dinner, and the campus visit. Also, I have to say about the organization also, from the reception to accommodation, food, the anchoring teams, the technical team for presentation, photography, etc., are well organized. Also, I have to say the selfie spot outside this hall helped us to capture the cherished moments with the resource persons and with the participants and also with the coordinators. Okay. As everyone said, I also wish in the coming years the department may take the opportunity to host next events. Once again, I appreciate the convener and the leader, of course, the principal, for their dedicated works, and also for the students, I congratulate them. Also, I am grateful to the resource persons for sharing their insightful thoughts. Once again, thank you to all.
Thank you for your valuable feedback. Is there anyone else to share your feedbacks?
Good afternoon, everyone. And yeah, first of all, let me thank and also congratulate the organizers and the entire team and the college, the management for organizing such a wonderful conference, international conference. I have, really, I'm very much pleased to see this conference because I've taken part in many conferences in my working experience, including in my college. I come from Manipal Institute of Technology, although I'm from Kerala, Chalakudi itself, but I'm working there for many years. So there also I have seen many international conferences, and there is someone there who has very exacting standards for how a conference should be organized. And I have even been part of the team there, and I've seen how much work goes into it and how difficult it is to make everything go smoothly, how easily things go wrong. Okay, so at the moment we will test everything. At the moment of the presentation, something or the other will go wrong. That is, I've seen that many times, but here nothing like that happened. Everything went so smoothly, and especially I want to congratulate the technical team also, because it was really wonderful. I've gone and asked them how they did it, because we also want to do that. So I've actually asked them. It's been very wonderful, and of course, technically, as far as the talks are concerned, subject-wise also, we had such wonderful experts, and we were all got the opportunity for some valuable interactions here. They were all very open and welcoming to us to speak, very approachable. So we could talk to them very easily. So that is also one thing that sometimes it's missing in conferences. We hear their talks, but we may not be able to have personal interactions. But here that is not the case. We were all able to interact as much as we want, and especially the open problem discussion also I'm seeing for the first time. So that was very useful. Thank you again. Thank you once again. I did not take the accommodation, so I cannot speak about it, but everything else, all the arrangements, food, hospitality, everything was really great. Thank you again. Thank you.
Thank you for your feedback. Anyone else to share their feedback? Please feel free to come forward.
Good evening, everyone. I'm Mitra, pursuing research at VIT Vellore. So first of all, I would like to thank Christ College IRINJALAKUDA and the Department of Mathematics for arranging such wonderful conference for us. And I would also like to take this opportunity to to express my gratitude to all the speakers who has given us enormous knowledge in various topics of graph theory, as well as gave us many suggestions during the paper presentation sessions. And I'm sure that all the research scholars have taken many insights from their valuable comments, as well as from their talks, and so that they can carry forward in their future research work. Now, coming towards the arrangements, coordination, and everything of the conference. So I have taken accommodation here. So from the beginning itself, they have made a group for the accommodation. So it made us very easy and convenient to communicate with them, and it helped us to reach here very properly, correct time, everything. So the accommodation team, all the coordinators have done a fantastic job, I must say. And then reaching here, we were bombarded with so many surprises. In the first day itself, we were surprised hearing about the mini trip they have planned to Snehathiram, and I'm sure that all the persons who have came in that trip have enjoyed to their maximum limit, because all the faculties, all the coordinators, everyone, we had a very good, nice time. They were very friendly and very nice to us, and that made us really enjoy the trip very much. And the next day, we were amazed with this wonderful talent of this whole college, the dancing team, the music team, everything, the technical team, and as well as the Chendamelam that they have organized. It was just like the cherry on the cake. So I'm sure that everybody have enjoyed very much. And now, speaking about the food, the sadhya that you have provided, staying outside Kerala, it was like a heartwarming experience for all of us. So that was also wonderful. And so altogether, and also I would like, we also got an opportunity to visit some of the departments of this college. And there was also, we were surprised to see how they have managed to put everything, all the departments. It was very wonderful, and how they have managed to put everything in under one roof. It was very well organized, managed, and everything. So altogether, it was a very wonderful experience, and I thank and appreciate the whole team. I'm not taking names, and appreciate the whole team for all their efforts. And we are also eagerly waiting for this ICGTA 2025. So please make that possible. Thank you all. Thank you so much.
Thank you for your feedback. Anyone else to share their thoughts? Please come forward.
Good evening, everyone. I am Magima, doing research in VIT Vellore. So, my native is Tamil Nadu, and first time I'm attending an international conference in Kerala. So, I have friends from Kerala, and they'll be talking about their culture, their hospitality, their food, and everything. So, I got a chance to experience everything here. So first of all, I would like to thank the Department of Mathematics, HOD, and all the organizers who have planned such a wonderful international conference. And it was very well organized that we didn't even experience any bad things or like any inconvenience. And the technical team was very good because I'm first time seeing such an arrangement like these presentation and everything. So it was very good, and the cultural events, the beach trip, everything was unexpected. And I have attended the conferences before, but this was really very exceptional. And coming to the resource persons, they are very humble, and their lectures were easily going into our brains actually. And it was very well understanding, and we got many opportunities to interact with them, and that was a really great opportunity. And I thank you all, and I congratulate to make this event success. And as all of us expecting, I also expecting to attend the conference next time here in Kerala. And the culture and the hospitality here is again remarkable, and it's very good to be here. Thank you.
It will be our pleasure if the speakers also share a few thoughts. Madhamangal sir, please.
So thank you, organizer, including the principal of the college. So I'm very happy to come here. This is my first visit in this college. So everybody is saying that the organizer are very good and their food, delicious food I have taken today. And also I have attended 2 lecture today, and I myself enrich a lot from these lectures. And basically I would like to say that the graph theory is basically a very important tools. And apart from your subject, I can say graph theory is a tools to represents almost all real life problems. That means any mathematical expression, algebraic expression can be represented with the help of graph theory or graph. So your dictionary, the soft dictionary, which are using during your WhatsApp typing or any other type of typing. So entire dictionary is represented by a graph. That one is particularly called the AMOA search graph. So lot of examples are there which are modeled with the help of graph theory, and computer scientists, they are using the graph theory to solve the real life problems. Okay, so for that reason the topics is very interesting and useful. And actually I have missed a lot of things, your cultural program, your other programs, that one already happened in first day, second day like that. So thank you very much for your invitation.
Reddy sir, please.
It is an advantage, means all the people already told very. So now nothing to add much, but okay, 1 or 2 points I just want to say. As rightly pointed out, it is meticulously, very nicely organized. I really impressed with the teamwork. I myself am learning so many things actually. How to organize things. There are many things to learn from here. That is what I want to add. For example, they divided the work hours very systematically. Some people, for example, Jojo sir, Shinto sir, they are for a travel part, they are taking care of that part. Some team like Agnes and all, they are taking care of how paper presentation will go. Like that, I am observing each and every aspect. And some people are there, MSc first year student, they are taking care of our food. Are you taken fully? One more, one more? Yeah, like that. So, very systematically planned, very well organized, and as Vinay pointed out, one after the another. There are many conferences, but each event after another, very systematically planned. For example, today, somehow the paper presentation is completely little early, right? That is a problem to me because I forget about, I am thinking it 2 o'clock, but actually they already mentioned it is 1:30. They want to save that time also. Whatever it is, everything try to reduce, optimize. We can say that optimize the correct thing. Each and every aspect they done wonderfully well. And also, other aspect I want to say, inaugural is over, next day in YouTube, that is available. Okay, first day over, then they take the snapshot systematically and they make one video about that. And even in Sneha Theorem, whatever you are talking, you all standing at that side and jumping, that photograph also already there here. Yeah, so I'm sorry, I'm not saying that. Actually, now mathematicians are good salespersons also, they showed it. Yeah, yeah, so they sell the product very nicely. Selling, it's not selling. My point is that the way how they included, the thought they put it, at the same time they want to enrich the entire college also. Whatever they are giving, and they are giving back also to the college. Department of Mathematics done a wonderful job. So as other people, I'll also hope that it will again come one more time here. Thank you very much. And finally, as Ayman Badawi sir told, many young researchers. Is one of the largest number of participants gave talks here. They accommodated each and everyone. That is a very nice thing, unique to this particular conference. I'm very thankful to everyone. Thank you very much.
Thank you all for your kind words. Finally, to conclude this event, I request Dr. Seena V, convener ICGTA 2024, to deliver the vote of thanks.
Actually, words are not enough to express my gratitude. Anyway, as a formal, respected Principal, Reverend Father Dr. Jolie Andrews, CMI, distinguished advisory committee members, Professor Sudev N.K., Professor G. Indulal, plenary speaker, Professor Ayman Badawi, Satyanarayana Reddy sir, Madhumangal Pal sir, former HOD Tindumol Sunny, other invited speakers, dear teachers, research scholars, and my dear students. Good afternoon to all. The mathematics department has a legacy of over 60 years and was elevated to a research department in 2023. As mentioned earlier, this is second international conference since becoming a research department. The success of last year's international conference, convened by Dr. Seena Varghese, along with the support of the college management, has inspired us to hold another international conference. It is with immense gratitude I stand before you today at the close of International Conference on Graph Theory and its applications, ICGTA 2024. As the convener of this conference, I am truly honored to have witnessed such a vibrant exchange of ideas, research, and collaboration over the past few days. First and foremost, I would like to extend my heartfelt thanks to our principal, whose unwavering support made this event a reality. You have consistently inspired us to aim higher and embrace new challenges. Despite the challenges we faced in organizing the conference, Father's constant encouragement and guidance have been a source of strength for all of us. On behalf of organizing team and all the participants of ICGTA, I extend our most sincere gratitude to you, Father. Thank you, Father. Now, I would like to extend a heartfelt thanks to Professor Dr. Sudev N.K., a cherished member of our advisory committee. From the very beginning, he has been a constant source of advice and suggestions, helping us at every stage of organizing this event. We deeply appreciate your contribution as a session chair and for delivering an insightful talk during the event. We are truly grateful for everything you have made to make this conference not only a success but also a memorable experience for everyone involved. On behalf of the entire organizing team, thank you so much for the invaluable contributions. Thank you. I would like to extend our heartfelt thanks to Professor Ayman Badawi for serving as a section chair and delivering an insightful talk that enriched the conference. Your presence and contributions have made a lasting impact, and it has been an honor to have with you, sir. We look forward to continue our collaboration with you in future. Thank you, sir. Now I express sincere gratitude to Professor G. Indulal, Professor of St. Aloysius College, Edutwa. We are deeply grateful for your invaluable contributions to our conference. As a distinguished member of our advisory committee, your guidance and support have been instrumental in shaping the success of this event. Also, thank you for delivering an enlightening section that engaged and inspired our participants. Thank you, sir. I extend my heartfelt thanks to Professor A. Krishnamurthy, President of KMA, for inaugurating this function, and Professor Dr. Vinod Kumar PB, General Secretary of KMA, for his incredible support and facilitating collaboration with the KMA, which has greatly enriched our initiative. Thank you. I sincerely thanks Dr. Satyanarayanan Reddy sir for serving as a resource person, chairing sessions, judging paper presentation, and leading the open problem session successfully. Your constant presence and invaluable contributions have truly elevated this conference. Thank you, sir. I would like to extend my heartfelt thanks to Professor Madhu Mangalpal for serving as a resource person and chairing sections with great expertise. Your valuable insights and leadership have significantly enriched the conference. Thank you, sir. I extend my heartfelt thanks to Professor D.B. West, Professor J. Baga, Professor Eunice, for being esteemed plenary speakers of ICGTA 2024. Your insights have been invaluable. I sincerely thank Professor Shahul Hamid and Dr. Sunil Matthew for their insightful talks and chairing sections with great expertise. I also thank Professor Sister Germina, who is also a member of advisory committee. I also thank Dr. Anjali Kishore, who joined us to evaluate the paper presentation sections. Now I take this opportunity to remember and thank each one of the eminent members of the advisory committee of this conference for guidance and support. Now I extend my deepest gratitude to our bursar, Reverend Father Dr. Vincent N.S., whose vision and dream has been the cornerstone of this event. His aspiration to see an annual international conference during this time has become a reality. Thanks to his unwavering support, his guidance through every challenge has been the driving force behind our success. Thank you, Father, for your invaluable leadership. Actually, words are not enough to express my gratitude to you, Father. Now, I would like to express my heartfelt thanks to Dr. Tindumol Sunny, former head of the department, for her continuous support through this conference. Thank you, ma'am. Now, I thank each participant of ICGT 2024 for your invaluable contributions and active engagement. Your enthusiasm and dedication have made this conference a remarkable success. I sincerely thank Dr. Shindo KG, IQSC coordinator, for all the support he has provided throughout this conference. Thank you, sir. I take this moment to thank all the vice principals, all the deans and head of the various department, teachers for joining us and being a part of this conference. I extend my heartfelt thanks to Dr. Joju KT, Coordinator of Mathematics Unaided, for all the motivation and support he has provided throughout this event. Thank you so much, sir. I extend my sincere thanks to Program Committee conveners Dr. Seena Varghese and Ms. Mary Polly. Dr. Seena Varghese, who provided invaluable guidance for this conference and offered immense support at every point, while Ms. Mary Polly assisted me in every manner and kept me on track with reminders. Your contributions have been essential to our success. Thank you both. I extend my heartfelt thanks to Ms. Agnes Boathingal for expertly managing the paper presentation and anchoring sections, Ms. Ameya for leading accommodations, Mr. Anand for heading the food committee, Ms. Shivagami and Ms. Sonia Babu for their invaluable contributions to registration and publicity. Your effort have greatly enhanced the sections of this conference. Thank you all. I take this opportunity to thank Kerala State Higher Education Council and Kerala Mathematical Association for their academic collaboration which has nurtured this conference. I also thank all the non-teaching staff of our college for their support with special mention to Vinjo, Hariharan, Prajesh, Jixan, Abhijit and all other technical and media team along with Vaishak, the cultural program coordinator. I sincerely thank each student of our department who contributed to organizing this event. Your hard work and dedication made all the difference. Once again, I thank you, each one of you, making ICGTA 2024 a success. Thank you so much.
Thank you, ma'am. Once again, thanking you all the dignitaries and participants for your presence and involvement. It is an honor to gather here today for a very special occasion. As we conclude our conference, we are excited to celebrate one of our own alumnus of Christ College, Sri Ramachandran TN, who has made significant contributions awarded the Global Awards for the Best Mathematician of the Year in recognition of his outstanding performance and contributions in Vedic mathematics, comprising of mental maths, math magics, speedy maths, lightning maths and electra maths to students from preschool to postgraduate level in molding them with flying colors in academics as well as career life. We are privileged to have with us today distinguished guests, each of whom has made an indelible mark on both academia and public service. Please join me in welcoming our beloved principal, Reverend Father Dr. Jolie Andrew CMI, the URB Global Awards team, and our esteemed alumnus, Sri Ramachandran TN. I also take this opportunity to welcome Guinness Anish from Universal Record Forum. Welcome all. To begin this special occasion, I now welcome the URB Global Awards team for the official proceedings of the award. I request Guinness Sunil Joseph sir to start the proceedings.
Good afternoon, respected principal. And Christ College teachers, students, and friends. Once again, warm welcome to the program. Okay. എൻ്റെ പേര് സുനിൽ ജോസഫ്, ഗിന്നസ് റെക്കോർഡ് ഹോൾഡറാണ്. ഞങ്ങളുടെ ഓർഗനൈസേഷൻ യൂണിവേഴ്സൽ റെക്കോർഡ് ഫോർ URF കൽക്കട്ടയിലാണ് ബേസ് ചെയ്തിരിക്കുന്നത്. ഞങ്ങളുടെ ആക്ടിവിറ്റീസ് സമൂഹത്തിലുള്ള വ്യത്യസ്ത കഴിവുള്ള ആൾക്കാരെയും സ്ഥാപനങ്ങളെയും കണ്ടെത്തി അവരെ റെക്കഗ്നൈസ് ചെയ്യുക എന്നുള്ളതാണ്. അങ്ങനെ ഇരിക്കുന്ന ഒരു അവസരത്തിലാണ് ഇരിഞ്ഞാലക്കുടയിൽ ഒരു പ്രോഗ്രാം ചെയ്യാനായിട്ട് ലാസ്റ്റ് വീക്ക് ഞാനിവിടെ വന്നപ്പോൾ മിസ്റ്റർ രാമചന്ദ്രൻ സാറിനെ ഞാൻ പരിചയപ്പെടുകയും അദ്ദേഹത്തിൻ്റെ കോൺട്രിബ്യൂഷൻസ് ടു ദ മാത്തമാറ്റിക്സ് ആൻഡ് ടു ദ എൻ്റയർ വേൾഡ് ഇതുവരെ ആരും കണ്ടെത്തിയിട്ടില്ല. കണ്ടെത്താത്ത കുറേയധികം ഇന്നോവേഷൻസ് എന്ന് പറയാം മാത്തമാറ്റിക്സിലെ കാര്യങ്ങൾ കണ്ടെത്തിയിരിക്കുന്നു. അത് വെളിയിലേക്ക് ഇതുവരെ ആരും കൊണ്ടുവന്നിട്ടില്ല. ചെറിയ ചെറിയ പോക്കറ്റ്സിലൊക്കെ ഉണ്ടാകും എന്നേ മാത്രമേ ഉണ്ടായിരുന്നുള്ളൂ. പക്ഷേ അദ്ദേഹം ഈ നമ്മുടെ നാടിന് ചെയ്ത സംഭാവന ശരിക്കും പറഞ്ഞാൽ ഒരു ജൂനിയർ രാമാനുജൻ തന്നെയാണ് ശ്രീ രാമചന്ദ്രൻ എന്ന് പറയുന്നതിൽ എനിക്ക് സന്തോഷമുണ്ട്. കാരണം അദ്ദേഹത്തിൻ്റെ ഞാൻ കോളേജിലും സ്കൂളിലൊക്കെ പഠിക്കുന്ന സമയത്ത് നമ്മൾ ഏറ്റവും കൂടുതൽ പേടിച്ചിരുന്നൊരു വിഷയമാണ് മാത്തമാറ്റിക്സ്. മാത്തമാറ്റിക്സിനെ പേടിക്കേണ്ട കാര്യമില്ല. മാത്തമാറ്റിക്സ് ആണ് ഇവിടെ ഇൻ്റർനാഷണൽ കോൺഫറൻസിൽ സാറ് പറഞ്ഞ പോലെ തന്നെ യൂണിവേഴ്സൽ ലാംഗ്വേജ് എന്ന് പറയുന്ന പോലെ നമ്മളുടെ ജീവിതത്തിൻ്റെ സ്പന്ദനം. പണ്ട് തിലാന പറഞ്ഞ പോലെ തന്നെ ഇതെല്ലാം മാത്തമാറ്റിക്സ്, ഭൂമിയുടെ സ്പന്ദനം തന്നെ മാത്തമാറ്റിക്സിലാണെന്ന് പറഞ്ഞ കണക്കിലാണെന്ന് പറഞ്ഞതുപോലെ തന്നെയാണ് ഇദ്ദേഹത്തിൻ്റെ ജീവിതം തന്നെ കണക്കാണ്. ഓണത്തെക്കുറിച്ച് ചോദിച്ചു കഴിഞ്ഞാൽ മാത്തമാറ്റിക്സിനെ കുറിച്ച് പറയും. ക്രിസ്തുമസിനെ കുറിച്ച് ചോദിച്ചാൽ പറയും. തൃത്വത്തെക്കുറിച്ച് ചോദിച്ചു കഴിഞ്ഞാൽ അതും മാത്തമാറ്റിക്സ് ആണെന്ന് പറയും. അതിനെക്കുറിച്ച് പറയാനായിട്ട് അദ്ദേഹത്തിൻ്റെ കയ്യിൽ ധാരാളം കാര്യങ്ങളുണ്ട്. അതുകൊണ്ട് ഞാൻ കൂടുതലായിട്ട് അതിനെക്കുറിച്ച് വിശദീകരിക്കുന്നില്ല. ഞാൻ മനസ്സിലാക്കിയിടത്തോളം അദ്ദേഹം നിങ്ങളുടെ ഇവിടുത്തെ ഒരു ഫാക്കൽറ്റി ആയിട്ട് തന്നെ ജോയിൻ ചെയ്തിട്ടുണ്ട് എന്നാണ് ഞാൻ മനസ്സിലാക്കുന്നത്. എനിവേ അദ്ദേഹത്തിന് എല്ലാവിധ ആശംസകളും നേരുന്നു. സാധാരണ ഞങ്ങൾ ഈ അവാർഡിനൊക്കെ ഇതെടുക്കുമ്പോൾ എനിക്ക് ധാരാളം ക്രൈറ്റീരിയാസൊക്കെ നോക്കി അതിനൊക്കെ ചില ഇതുണ്ടാവും. പക്ഷേ ഇത് 100% അദ്ദേഹത്തിൻ്റെ കഴിവിനെ മാത്രം ബേസ് ചെയ്തുകൊണ്ട് ഞങ്ങളുടെ റെക്കോർഡ് മാനേജ്മെൻറ്റ് ടീം വളരെയധികം റിസർച്ച് നടത്തിയതിന് ശേഷമാണ് അദ്ദേഹത്തിന് ഇങ്ങനെ ഒരു ഇതിലേക്ക് സെലക്ട് ചെയ്തത്. ടോട്ടലി ഞങ്ങളുടെ ഭാഗത്തു നിന്നുള്ള ഒരു റെക്കഗ്നീഷനായിട്ട് തന്നെ ഇതിനെ കണക്കാക്കുന്നു. ഞങ്ങൾ 100% ഫ്രീ ഓഫ് കോസ്റ്റ് അദ്ദേഹത്തിന് ഈ ഒരു അവാർഡ് നൽകാനായിട്ട് ഞാനിവിടെ എത്തിയിരിക്കുന്നു. എന്തായാലും വളരെയധികം സന്തോഷമുണ്ട്. നിങ്ങളുടെ എല്ലാവരുടെയും അനുഭവത്തോടുകൂടി യൂണിവേഴ്സൽ റെക്കോർഡ് ഫോറം URF വേൾഡ് റെക്കോർഡ്സ് പ്രൈവറ്റ് ലിമിറ്റഡിൻ്റെ അവാർഡ് വിങ്ങായ യൂണിവേഴ്സൽ റെക്കോർഡ് ബുക്കിൻ്റെ ഗ്ലോബൽ അവാർഡിന് ശ്രീ രാമചന്ദ്രൻ അവർകൾ അർഹനായിട്ടുള്ള വിവരം വളരെ സന്തോഷത്തോടു കൂടി ഞാൻ നിങ്ങളെ അറിയിക്കുന്നു. വിത്ത് യുവർ പെർമിഷൻ I just try to hand out the certificate. Universal Record Book Global Award. This award is presented to Mr. Ramachandran TN, the best mathematician of the year 2024, Vedic Max. The description I will explain later. Okay, thank you.
Thank you for that inspiring announcement. Thank you, Sunil sir. Thank you, Father, and thank you all. I now invite Father Dr. Jolly Andrew CMI, our principal, to address the gathering and honor Sri Ramachandran TN.
പ്രിയമുള്ളവരെ, ആദ്യമേ തന്നെ രാമചന്ദ്രൻ സാർക്ക് പ്രത്യേകിച്ചും വേദിക് മാത്തമാറ്റിക്സിൻ്റെ കാണാപ്പുറങ്ങൾ ഇരിഞ്ഞാലക്കുടക്കാർക്കും കേരളത്തിനും തന്നെ ഭാരതത്തിനും തന്നെ പരിചയപ്പെടുത്തുന്ന രീതിയിൽ വലിയ സംഭാവനകൾ നൽകിയിട്ടുള്ള രാമചന്ദ്രൻ സാർക്ക് ഈ അവസരത്തിൽ ഉള്ള പ്രത്യേകമായിട്ട് ഈ അവസരത്തിൽ അനുമോദനങ്ങൾ അർപ്പിക്കുന്നു. URB ഗ്ലോബൽ അവാർഡ് അതിന്ന് കരസ്ഥമാക്കിയിരിക്കുകയാണ്. സോ വി ആർ റിയലി പ്രൗഡ് ഓഫ് യു. ഈ വലിയ അംഗീകാരം അങ്ങ് സ്വന്തമാക്കിയതിലുള്ള എല്ലാ ഭാവുകങ്ങളും നേരുന്നു. ഇവിടെ ഗബ്രിയലച്ചൻ്റെ അരുമ ശിഷ്യനായിട്ടുള്ള RK രവി സാർ അടക്കമുള്ളവർ ഇവിടെ സന്നിഹിതരാണ്. അപ്പോൾ തീർച്ചയായിട്ടും ഗബ്രിയലച്ചൻ്റെ ഒരു സാന്നിധ്യവും പരമഭൂഷൺ ഗബ്രിയലച്ചൻ്റെ ഒരു സാന്നിധ്യവും ഇവിടെ ഉണ്ട് എന്ന് ഞങ്ങൾ മനസ്സിലാക്കുന്നു. തീർച്ചയായിട്ടും ഇനിയും ഒത്തിരിയേറെ അവാർഡുകളും നേടിയെടുക്കാനായിട്ട് രാമചന്ദ്രൻ സാർക്ക് സാധിക്കട്ടെ എന്ന് ആശംസിക്കുന്നു. ഇതൊരു ടെക്നിക്കാണ്. ആ ടെക്നിക്ക് ഒരു സർട്ടിഫിക്കറ്റ് കോഴ്സായിട്ട് നമ്മുടെ ക്രൈസ്റ്റ് കലാലയത്തിലെ വിദ്യാർത്ഥികൾക്ക് രാമചന്ദ്രൻ സാർ നൽകുന്നുണ്ട്. അപ്പോൾ അത് ഏറ്റവും മനോഹരമാകട്ടെ. ഇനിയും തുടർന്ന് ഇതുപോലെ വലിയ നേട്ടങ്ങൾ കൈവരിക്കാൻ ഇടവരട്ടെ എന്ന് ആശംസിച്ചുകൊണ്ട് പ്രത്യേകിച്ചും ഏറ്റവും ആപ്റ്റായിട്ടുള്ളൊരു പേഴ്സണാണ് URB ഗ്ലോബൽ അവാർഡ് മാത്തമാറ്റീഷ്യനായിട്ട് നിങ്ങൾ തിരഞ്ഞെടുത്തത്. ഇതിൻ്റെ ഭാരവാഹികൾക്ക് എല്ലാ അനുമോദനങ്ങളും ഏറ്റവും ഉചിതമായിട്ടുള്ള തിരഞ്ഞെടുപ്പായി എന്ന് മാത്രം പറഞ്ഞുകൊണ്ട് സോ വി ആർ വെരി പ്രൗഡ് ഓഫ് യു. ഇങ്ങനൊരു അവാർഡ് രാമചന്ദ്രൻ സാർ കരസ്ഥമാക്കിയതിന് പ്രഖ്യാപിച്ചുകൊണ്ട് എൻ്റെ വാക്കുകൾ നിർത്തട്ടെ. നന്ദി, നമസ്കാരം.
Thank you, Father. Now we have the privilege of honoring our esteemed alumni, Sri Ramachandran TN. For this, I request Father
നമ്മുടെ ക്രൈസ്റ്റിൻ്റെ അലുമിനിയിലുള്ള എല്ലാവരും ഒരു മിനിറ്റ് മുമ്പിലേക്ക് വരാണെങ്കിൽ ഈ ഫോട്ടോയിൽ വരും. അപ്പോൾ എല്ലാവരും ക്രൈസ്റ്റിൽ പഠിച്ചിട്ടുള്ള എല്ലാവരും ഒന്ന് മുമ്പിലേക്ക് വരാണെങ്കിൽ നമുക്ക് അടിയിലേക്ക് ഇറങ്ങാം.
അദ്ദേഹത്തിൻ്റെ കഴിവ്. ഇങ്ങനെ ഒരു ബഹുമാനവും അതുപോലെ തന്നെ ഗ്ലോബൽ അവാർഡും നേടുന്നതിന് വേണ്ടി അതിൻ്റെ സംഘാടകർ അദ്ദേഹത്തെ വന്ന് ഇൻ്റർവ്യൂ നടത്തിയ സമയം വളരെ ആറ്റിറ്റ്യൂഡായിട്ട് കൃത്യമായിട്ട് അതിൻ്റെ തിയറിയും രേഖകളും എല്ലാം സബ്മിറ്റ് ചെയ്ത് വളരെ നല്ല രീതിയിലുള്ള ഒരു വിന്നറായിട്ടാണ് അദ്ദേഹത്തിന് തിരഞ്ഞെടുക്കപ്പെട്ടത്. അതിൻ്റെ പിന്നിൽ പ്രവർത്തിച്ച വ്യക്തികളെയും അതുപോലെ തന്നെ ഈ രാമചന്ദ്രൻ സാറിനും ഇനിയും കൂടുതൽ കൂടുതൽ ഉയരങ്ങളിലേക്ക് മാത്സിലും മറ്റു കാര്യങ്ങളിലും എല്ലാവിധ ഭാവുകങ്ങളും ഉണ്ടാകട്ടെ എന്ന് ഈ അവസരത്തിൽ ആശംസിച്ചുകൊണ്ട് നിർത്തുന്നു. നന്ദി, നമസ്കാരം.
Thank you for your inspiring remarks. Finally, let us hear from the man of the moment himself, Sri Ramachandran sir, as he offers his reply to the honors bestowed upon him. I welcome you, sir.
Respected and beloved Principal of Christ College, Reverend Father Dr. Jolie Andrews, Guinness Sunil Joseph, CEO and International Jury of Universal Record Forum, the delegates of national and international delegates of the International Mathematics Conference, which was held during the last 3 days here, distinguished personalities on and off the dais, എൻ്റെ സുഹൃത്തും വളരെയധികം എന്നെ സ്നേഹിക്കുന്ന ആളുമായ മിസ്റ്റർ MP ജാക്സൺ, മിസ്റ്റർ രവി എൻ്റെ ക്ലാസ്മേറ്റും കൂടിയാണ്, ഗബ്രിയേലച്ചൻ്റെ സ്വന്തം എന്ന് തന്നെ പറയാം, മിസ്റ്റർ രവി, മിസ്റ്റർ നന്ദൻ, എൻ്റെ കുറച്ച് റിലേറ്റീവ്സും കുറച്ച് ഇവിടെ ഉണ്ട്, എൻ്റെ സിസ്റ്റർ വന്നിട്ടുണ്ട്, മാഡം ജിഷാജൂബി ആൻഡ് എൻ്റെ എല്ലാ വെൽവിഡേഴ്സും. പിന്നെ പറയുന്നത്, ഈ അവാർഡിന് ഈ പ്ലാറ്റ്ഫോം തന്നെ തിരഞ്ഞെടുത്തത് എനിക്ക് വളരെ ഉചിതമായി തോന്നുന്നു. കാരണം I was a student of this college for the pre-degree and degree, that's BSc Mathematics, and about 52 years back, ഞാൻ 65-71 ബാച്ചാണ്. അത് കഴിഞ്ഞതിന് ശേഷം ഉടനെ ഞാൻ അന്ന് ഒരു ജോലിയില്ലാതെ തരമില്ല ജോലിക്ക് ജോയിൻ ചെയ്യുകയും അവിടെ നിന്ന് മാറി ഞാൻ ബാങ്ക് ഓഫ് ബറോഡയിൽ ജോയിൻ ചെയ്ത് 40 വർഷം സർവീസിന് ശേഷം വിരമിക്കുകയാണ് ഉണ്ടായത്. ഇതിനിടയിൽ എൻ്റെ ജീവിതത്തിൽ കുറേ പാഷൻസ് ഉണ്ടായിരുന്നു. അതായത് മാത്തമാറ്റിക്സ്, കൂടൽമാണിക്യം ടെമ്പിൾ, ഇരിഞ്ഞാലക്കുട പിണ്ടിപ്പെരുന്നാൾ, ദെൻ അത് കഴിഞ്ഞതിന് ശേഷം ക്രൈസ്റ്റ് കോളേജ്, ഇതെല്ലാം എൻ്റെ ജീവിതത്തിലൊരു പാഷനായിരുന്നു. അന്നൊരു ജോലി ആവശ്യങ്ങളുണ്ട്, ജോലിക്ക് ചേർന്നു. അതിൽ നിന്ന് വിരമിച്ചതിന് ശേഷം വീണ്ടും ഞാൻ എൻ്റെ മാത്തമാറ്റിക്സിലുള്ള ആ പാഷൻ വീണ്ടും അത് തുടങ്ങി വെച്ച് ഞാൻ എല്ലാ ഈ ജനറലായിട്ടുള്ള സബ്ജക്ട്സ്, കണ്ടംപററി സബ്ജക്ട്സ് വിട്ട് വേദിക് മാത്സിൽ റിസർച്ച് ചെയ്യുവാനും സ്പെഷ്യലൈസ് ചെയ്യുവാനും തുടങ്ങി. അതിനൊരു പ്രധാന കാരണം, ഞാൻ ഒരിക്കൽ അമേരിക്ക വിസിറ്റ് ചെയ്ത് ഞാൻ മാത്തമാറ്റിക്സ് അസോസിയേഷൻ ഓഫ് അമേരിക്കയുടെ ഒരു ടഫസ്റ്റ് കോമ്പറ്റീഷനിൽ എനിക്ക് അവരുടെ മെമ്പർഷിപ്പ് കിട്ടി. അതിനുശേഷം ഓരോ 3 മാസവും അവർക്കൊരു ബ്ലോഗ് തയ്യാറാക്കി കൊടുക്കുവാൻ വേണ്ടി റിസർച്ച് തുടങ്ങി. അങ്ങനെ റിസർച്ചിൽ ഒരുപാട് കാര്യങ്ങൾ എനിക്ക് ഡെവലപ്പ് ചെയ്തെടുക്കുവാൻ പറ്റി. അതിൽ നിന്ന് അപ്പോഴാണ് എനിക്കും മനസ്സിലായത്, ഞാൻ ആദ്യം വിചാരിച്ചത് മാത്തമാറ്റിക്സ്, ശരിക്കും പറഞ്ഞാൽ മാത്തമാറ്റിക്സ് വെച്ചാൽ എന്താണ്? മാത്തമാറ്റിക്സ് ഈസ് എ കോമ്പിനേഷൻ ഓഫ് മെമ്മറി, ആക്യുറസി, ടാലൻറ്റ്, ഹാർഡ് വർക്ക്, എന്തോസിയാസം, ഇൻ്റലിജൻസ്, ക്ലവർനെസ് ആൻഡ് സിൻസിയറിറ്റി. ഇതാണ് എനിക്ക് പറയാനുള്ള മാത്തമാറ്റിക്സിൻ്റെ നിർവചനം. അന്ന് ഈ പക്ഷേ ചില കുട്ടികൾ മാത്തമാറ്റിക്സ് ഭയങ്കര ടഫാണെന്ന് വിചാരിക്കും. അവർ വിചാരിക്കുന്നത് MATHS മാത്സ് എന്ന് പറഞ്ഞാൽ മെൻ്റലി അഫക്റ്റഡ് ടീച്ചേഴ്സ് ഹരാസിങ് സ്റ്റുഡൻസ് ആണ് ചിലർ വിചാരിക്കുന്നത്. അതിൽ നിന്നെല്ലാം വിഭിന്നമായി മാത്തമാറ്റിക്സിനോട് ശരിക്കും ഹാർഡ് വർക്ക് ചെയ്ത് നമ്മുടെ വേണ്ട വിധത്തിൽ പ്രിപ്പയർ ചെയ്യുകയാണെങ്കിൽ വളരെയധികം മാർക്ക് വാങ്ങുവാൻ ഉതകുന്ന സബ്ജക്റ്റാണ് മാത്സ്. മാത്സ് ഈസ് ദ വണ്ടേഴ്സ് ഓഫ് ദ സം ഓഫ് ഓൾ വണ്ടേഴ്സ്. ഇപ്പോൾ പറഞ്ഞ മാതിരി ഇവിടെ ഇത്തിരി മുമ്പ് പറയുണ്ടായി മാത്തമാറ്റിക്സിനെ പറ്റി പല നിർവചനങ്ങളും. പക്ഷേ മാത്തമാറ്റിക്സ്, ഈവൻ ഗോഡ് കാനോട്ട് റൂൾ ദ കൺട്രി വിത്തൗട്ട് മാത്തമാറ്റിക്സ്. കാരണം ഡെയിലി ലൈഫിൽ തന്നെ മാത്തമാറ്റിക്സ് ഇല്ലാതെ ഒരു കാര്യവും നടക്കില്ല. പക്ഷേ ഞാൻ പ്രത്യേകിച്ച് ഇപ്പോൾ റിസർച്ച് ചെയ്തുകൊണ്ടിരിക്കുന്നത് വേദിക് മാത്തമാറ്റിക്സിലാണ്. ഈ വേദിക് മാത്സും മാത്തമാറ്റിക്സ് ജനറലും തമ്മിലുള്ള ഡിഫറൻസ്, വേദിക് മാത്സ് ഈസ് ദ ഫാസ്റ്റസ്റ്റ് വേ ഓഫ് സോൾവിങ് മാത്തമാറ്റിക്കൽ പ്രോബ്ലംസ്. നമ്മൾ കണ്ടു കഴിഞ്ഞാൽ തന്നെ നമുക്ക് ആൻസർ ചെയ്യുവാൻ തക്ക രീതിയിൽ അതിനെ നമുക്ക് പാകപ്പെടുത്തി എടുക്കുവാൻ സാധിക്കും. അതിൽ കൂടാതെ ഈ റിസർച്ച് പ്രകാരം എനിക്ക് 1-2 നല്ല കാര്യങ്ങളുണ്ടായിട്ടുണ്ട്. ഞാൻ ഈ പൈത്തഗോറസ് തീറത്തിന് ഒരു ഓൾട്ടർനേറ്റീവ് തീറം സജസ്റ്റ് ചെയ്യുകയും അത് ഇൻ്റർനാഷണലി അപ്രൂവ്ഡ് ആവുകയും ചെയ്തു. അന്ന് അത് അപ്രൂവ് ആയതിനു ശേഷം അവരെനിക്ക് തന്ന ഇമെയിൽ, ദിസ് പൈത്തഗോറസ് തീറം ഈസ് മോർ ദാൻ 3000 years old, so it cannot be dispensed with. So your theorem will run into side by side with the original theorem എന്നാണ്. അപ്പോൾ ഇത്രയും എത്തിക്കഴിഞ്ഞതിന് ശേഷം പിന്നെ ഇങ്ങനെ ഇരിക്കുന്ന സമയത്താണ് ഞാൻ മിസ്റ്റർ സുനിൽ ജോസഫിനെ കണ്ട് അത് ഇങ്ങനെ സംസാരിച്ചപ്പോൾ എൻ്റെ മാത്തമാറ്റിക്സിലെ ചില കാര്യങ്ങൾ പറയുകയും അവരെ ഒരു 2 ആഴ്ച മുമ്പ് ഇവിടെ ഒരു തിരുവാതിരക്കളിയുടെ ഫംഗ്ഷൻ നടക്കുന്ന സമയത്ത് എൻ്റെ വീട്ടിൽ വരികയും ഞങ്ങൾ തമ്മിൽ ചില മാത്സിൻ്റെ കാര്യങ്ങളെപ്പറ്റി എന്നോട് ചോദിക്കുകയും സംസാരിക്കുകയും ചെയ്തു. അതിന് ശേഷമാണ് ഈ ഒരു തീരുമാനത്തിലെത്തി അവർക്ക് ഈ അവാർഡ് സമർപ്പിച്ചത്. ഈ അവാർഡ് ക്രൈസ്റ്റ് കോളേജിൽ നിന്ന് ഈ പ്ലാറ്റ്ഫോമിൽ നിന്ന് വാങ്ങുക എനിക്ക് അതിയായ സന്തോഷമുണ്ട്. മാത്രമല്ല ഞാനിവിടെ ജോയിൻ ചെയ്യുന്ന സമയത്ത് ഗബ്രിയലച്ചനാണ് ഇവിടുത്തെ പ്രിൻസിപ്പൽ, ആൻഡ് ഫാദർ കലിസ്റ്റസും ഫാദർ ഡിസ്മസും എനിക്ക് ക്ലാസ് എടുത്തിട്ടുണ്ട്. ഈ ഗബ്രിയലച്ചൻ്റെ ആ വിഷൻ, ആ ഫോർവേഡ് വിഷൻ, അത് വാസ്തവം പറഞ്ഞാൽ എത്ര പ്രായമായാലും ശരി നമുക്കതൊരു പ്രശ്നമല്ല. നമുക്ക് അഭികാമ്യമായ സബ്ജക്റ്റിനോട് നമുക്ക് ശരിക്കും നല്ല നിലയിൽ കൂറ് പുലർത്തി പോകാം. അത് ഞാൻ റോൾ മോഡലായിട്ട് എടുത്തുകൊണ്ടാണ് ഈ റിസർച്ചിലേക്ക് കടന്നത്. ഇത്ര വരെ എനിക്ക് വിജയിക്കുവാൻ സാധിച്ചു. അപ്പോൾ ഇതിവിടെ വേദിയൊരുക്കി തന്ന ഈ ഇൻ്റർനാഷണൽ കോൺഫറൻസ് ഇൻ മാത്തമാറ്റിക്സ് നടക്കുന്ന ഈ സമയത്ത് ഇതിൻ്റെ വൈൻഡിങ് അപ്പ് സെറമണിയോടുകൂടി എനിക്ക് ഈ അവാർഡ് തരുവാൻ വേണ്ടി എല്ലാവിധ സൗകര്യങ്ങളും ഒരുക്കി തന്ന ഈ ക്രൈസ്റ്റ് കോളേജ് മാനേജ്മെൻറ്റ് ടീം, ഈ പ്രിൻസിപ്പൽ അച്ഛൻ, ബർസാർ അച്ഛൻ, മിസ്റ്റർ വിൻസൻ, എല്ലാവർക്കും എൻ്റെ അങ്ങേയറ്റത്തെ നന്ദി രേഖപ്പെടുത്തുന്നു. ഇവിടെ സന്നിഹിതനായിട്ടുള്ള എല്ലാവർക്കും 1000 നന്ദി. നമസ്കാരം.
Thank you, sir. Next, I would like to invite Thank you, sir. As we Ashwati and Naseen for the national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उज्जल जलधितरङ्गा तव शुभ नामे जागे तव शुभ आशिष मागे गाहे तव जय गाथा जनगण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे.
Thank you all. A refreshing tea is arranged outside. I request everyone to enjoy the tea.